Morning. Special remarks from me? Yeah. Okay. Okay. Please seat. I have one for the here. Presentations, it's for 10 minutes each. 25 for each one. 5 minutes for Q&A, 25, so it means half an hour for each one. Just to.
Check your questions.
Okay.
That goes to the center. So, we have, how we have no, and,
We have virtual attendee. Some.
Yes.
Okay, chair, right, small. Thank you. Each show today.
there's questions.
That is. Thank you very much. Or we can let's say long weekend. Ça va? There's Maria. Sure. Really the issue, I'm super sure. Yeah, yeah, I think.
Good morning, ladies and gentlemen. My name is Milica, and I'm here with the Litvent Group, and I would like to warmly welcome all of you to the conference Floating Solar PV. We have gathered here to experience an intense 2 days of the conference where our distinguished speakers will present their cutting-edge strategies to you. I would like to thank to all the speakers for their support and for making time to come here today and share their knowledge with us. I would also like to thank to our sponsors, Fred Olsen, Vivek, and Spera, for their support. All the presentations will be followed by Q&A sessions. So please, if you want to raise a question, just raise your hand. And for the maximum interactivity, you will have an opportunity for further networking during the coffee breaks, afternoon tea, and lunch. The welcome coffee and all coffee breaks will be held here in front of the conference room. And for the lunch, we will go to the restaurant on the left. In the evening, after we are finished with all the sessions, we will have a cocktail reception here in front of the conference room. So please stay and have some more time for networking. In the agendas which you have received from my colleagues, you can find the list of participants, evaluation forms, and I would like to ask you to fill in these evaluation forms at the end of the event and hand it to my colleagues at the registration desk. Your feedback is very important for us, and it enables us to improve our events and services. The presentations will be available after the conference, and you will receive an email with a link to all the presentations. So as the speakers have interesting things to say, I would like to finish with this. Please just turn off the sound on your mobile phones. And finally, I would like to introduce to you our chairman, Antonio Duratev from Solaris Float. Enjoy the conference, and Antonio, the floor is yours. Thank you.
Hello, good morning to everybody. My name is Antonio Duarte, as Milica said. Welcome all of you to this conference that I'm sure that is going to be a very interesting one, like the ones that we have already in the past years. So I'm not going to talk a lot. We are in the middle of people that knows what the floating solar market is, challenges and good news and not so good sometimes, but the idea is for us to discuss, as usual, let's say, all the matters that are important for our industry and for our business. So I will not take long. We are going to have a very good morning and later on the afternoon continuation of the discussions and presentations and so on. So we are going to start now with, and I'm not going to take long, so I believe that there's not much more to say to start. I'm going to ask Kim Wissinger from BayWa to do his presentation. He's going to speak about the floating solar strategies, offtake strategies, and shaping the future of floating solar markets, an outlook and development. Kim, please, the floor is yours, okay?
Thank you very much for the introduction, and good morning, everyone. It is a pleasure to be here, actually for the first time, and also quite an honor to be the first speaker of this conference. Before I start, I would like to give a special thanks to the Litvent Group for organizing this insightful event. So today I will present about policies and offtake opportunities for floating PV, focusing on the European Union. So for the agenda, we will start with a short introduction of BayWa, followed by the economic feasibility and offtake strategies for floating PV. Afterwards, we will dive in the European policies and regulations, and we will end up with the conclusions. So BayWa is a leading global renewable energy developer service provider, distributor, also energy solutions provider. It was founded in 2009, and since 2018, it has been focusing also on floating PV. BayWa has the highest track record of floating PV with 283 megawatt peak installed across 20 projects. Most of these projects have been developed here in the Netherlands, but we also have projects built in Austria, Germany, and Thailand as well. In addition, we have 31 megawatt peak in construction in this year, and also a control pipeline of over 600 megawatt peak. In this slide, we would like to showcase BayWa's largest operational floating PV plant, which is located in a sandpit in Sellingen here in the Netherlands. With 41.1 megawatt peak, it is the largest floating plant for BayWa and one of the largest within Europe. It was only constructed in 7 weeks. It has been operational since 2021. In this slide, we can also find information regarding the number of modules installed, also details regarding floating structure, such as number of solar boats, inverter boats, transformer floaters, and also on the lower side, details regarding energy yield and CO2 reduction. Now moving on to the floating PV economic feasibility and offtake strategies. So floating PV in general is more expensive than ground-mounted PV, mainly because the additional hardware and also balance of system, such as anchoring and mooring, floating structure, among others. There are 3 main factors that are closing this gap between these 2 technologies. Techno-economical optimization, also the increasing competition and economies of scale. But these factors alone will most likely not eliminate this gap completely. In addition, for floating PV specifically, there are uplifts in terms of energy yield and also in terms of lower lease cost in certain cases, but these are usually minor and cannot compensate this gap. In addition, we also have unquantifiable benefits for floating PV that are virtually impossible to reflect and to translate into a business case and into the LCOE of a developer or for an investor, such as safe water from evaporation and also algae control. Now, focusing on the graphic on the right-hand side, we have an indicative LCOE comparison between ground-mounted PV and floating PV in terms of increased percentage. So on the first column, we have the reference of ground-mounted PV set as 100%, and afterwards we have different factors, plus and minus factors, such as CapEx, development costs, yield, and also lease costs. And this translates, and we end up with the floating PV values that represent around 12% higher LCOE costs than ground-mounted PV. Therefore, it is quite important and quite crucial, especially for floating PV, to find the right offtake and also to find the right business case. So in here we have some options of offtakes, and we in general can agree that financial incentives such as contract for difference, auctions, and tenders are still the most profitable offtake option for floating PV. Then also PPAs in terms of floating PV are still only viable in certain cases and only in certain conditions. Then for self-consumption opportunities, they are quite positive and are usually linked to dual use of water and also less market exposure. And finally, hybridization, which I'm sure everybody's more or less acquainted with. is gaining a lot of traction and is becoming quite relevant right now. So, such as building floating PV in hydro dams and also combining floating PV and storage. So now that we have seen how important it is for floating PV to find the right business case, the right offtake, now we move on to see how is the floating PV outlook in terms of policies and in terms of regulations. So first of all, in general, on EU level, there is a push for renewables and also for dual use, but there are only limited floating PV initiatives. Here we have a couple of examples. First, there was a public consultation from the European Commission to propose regulatory best practices. And also the Renewable Energy Directive in 2023 introduced the concept of renewable acceleration areas, where basically permitting could be streamlined, could be simplified for floating PV. And this includes also inland water surfaces. In addition, they are also promoting multiple use of space, which for floating PV could be quite helpful. Then we also have countries with financial policies, such as CFD auctions, like I mentioned, or feed-in tariffs, with dedicated segments, special segments for floating PV, or with an additional scoring that could help floating PV balance the competition against other PV technologies. But these policies are not uniformly spread, uniformly implemented across the European Union. Also, there are some countries that are still lacking floating PV-specific regulatory regulations, frameworks in general, and on the other hand, we also have countries that have regulations in place, but they are too restrictive or too conservative. So the questions that arises are mainly three. First, are these regulations and policies actually helping? Then, what are good and bad examples? And finally, what can and should be improved? And to clarify this, we will focus here and we will dive in some countries. So we will have Austria, Italy, Germany, France, and Spain. So starting with Austria, we have the EAG, the Renewable Energy Expansion Act, which is a legislative framework with various measures, also including financial incentives to support renewable energy transition. It was implemented in 2021, and they usually follow a CFD auction. Usually these contracts are 20 years, and they are based on a reverse-based auction scheme. They support several technologies, including photovoltaics. There is no specific floating PV auctions. However, standard ground-mounted PV technologies have a 25% reduction on their awarded price, which is not applicable to floating PV when built in artificial bodies of water. So this way, floating PV can better compete and better address these differences in CapEx and could access this scheme. Then, in general, also, Austria has a specific floating PV regulation and specific framework for floating. And as we have seen, they also have quite a positive financial incentive with, I forgot to mention, with a max bidding value for the period of 2024 and 2025 with around 90 euros per megawatt hour, which is quite positive. Then moving on to the second country, we have Italy with the FER-X Transitorio, which is a temporary financial support mechanism until the full framework is finalized. It is applicable until this year only, and supports technologies like photovoltaics, wind, and also hydroelectric. On the financial side, similar to Austria, they do not have a floating PV specific auction. However, they have set a 5 euros per megawatt hour bonus specifically for floating PV. And in addition, for PV in general, they also have zonal awards that mainly is used to compensate the differences in yield. So, and this is applicable to northern Italy and also to central Italy. Then, as a reference, the highest strike price for this was 95 euros per megawatt hour, and also follow a 20-year contract duration. Regarding framework in general and restrictions, they have set a water coverage limit based on region by region, and these usually range between 50 and 70%. And also they have set a 10-meter distance from the floating PV plant from shore, which is actually very reasonable. And now that we have seen quite a good policy and good legislation, now we also wanted to give, let's say, not so good or inadequate financial scheme. So in parallel of the FAIR X in Italy, they have the FAIR 2, which was proposed and implemented in 2024. It covers until the year of 2028, and it also includes innovative renewable energy sources. And however, this is considered fully inadequate, mainly because the contingent, so the volume auction, is very low, only 50 megawatt peak. And also for inland PV, this is. And in fact, there was a proposed 200 megawatt for offshore floating PV, which was completely scratched when it was approved recently. And also regarding the strike price, it is even lower than the FAIR X, so 20 euros per megawatt hour less than the FAIR X. So it is not very it's not very good, and it's not a very good opportunity for floating PV in this case. Then moving to the second batch, we have Germany, where we'll focus on two topics. First, the EEG Solar Packet 1, and also the Water Balance Act. So for the EEG Solar Packet 1, to give some context, the EEG is a framework to support renewable energy transition, and it includes auction schemes such as CFD auctions. The Solar Packet 1 was a proposal change and proposal reform that was made in 2023 that included very positive changes that could help floating PV development in Germany. And this included changing and increasing the size capacity for floating PV projects from 20 to 50 megawatt peak, also including a specific sub-segment auction for special solar PV, such as floating, agri, among others. And the max bidding value was set in 95 euros per megawatt hour, also quite positive. This proposal change was expected to be approved by the first semester of this year. However, some elements, such as the ones that I've mentioned, have been delayed and are still pending approval from the European Commission. And now the earliest that it is expected to be approved is the first quarter of 2026, hindering several projects until then. Then we have the Water Balance Act, which is a law that supports protecting and managing water bodies sustainably in Germany. And in this law, floating PV is only allowed in artificial or heavily modified water bodies. Also, the maximum coverage ratio is only set in 15%, which is extremely limited and with no real and with no adequate backing behind. And finally, the minimum distance to shore was set into 40 meters, extremely limiting, especially in small-scale projects. So here we have a clear example of having regulations present, but quite restrictive. Now for France, we have the PP2 PV Sol, which is an auction scheme for the construction of solar PV in general. It is managed by the by the CRE, the French Energy Commission in France, and it covers the range 2021 until 2026. It has already been going for quite some years, and similar to the other countries, they do not have a floating PV specific auction, so all PV in general compete against the other technologies. For floating PV in general, it can be the case that they can be part of the so-called category 3 within the auction that is applicable for floating PV when located on degraded lands. And they also do not have a capacity limit. Then the ceiling price for reference started in 90 euros per megawatt hour on the first rounds. And for France in particular, they do not have floating PV specific regulations or permitting procedures. So they basically just follow standard ground-mounted procedures for permitting. And this could be detrimental in generally speaking. However, we have seen quite a good traction of floating PV developments in France, which I'm sure we will see on the following presentations today. And here we have also a case of regulations missing or unclear, but having included financial incentives. Now moving on to the last country, we have Spain with the Royal Decree 662, which was proposed and implemented in 2024. It is a regulatory framework applicable specifically for floating PV. And within this decree, we want to highlight the maximum coverage limit, which they have set. And basically, they differentiate two water body types, so non-eutrophic and eutrophic. Non-eutrophic, meaning usually healthier and more balanced ecosystems, they have set a maximum of only 5% coverage ratio, extremely low. And on the eutrophic type water bodies, which are usually high nutritious water bodies, which leads to lower water quality, they have set a maximum coverage of 15%. So similar to Germany, we see in Spain a clear case of having regulations present, but quite restrictive. And also in Spain, we currently do not have any incentive schemes, especially for floating PV. Now moving on to the conclusions and takeaways. First, in general, floating PV CapEx and LCOE is decreasing, but they are still higher than ground-mounted PV. Then, while PPA capture prices are still challenging for most of floating PV projects, self-consumption opportunities and, as we have seen, incentive schemes are quite viable. Then, floating PV needs technology-specific auctions or some sort of leveling round of scoring, so floating PV can compete and can have the tools to better compete against other technologies with different maturity levels. Then current policy and regulatory landscape still remains fragmented within the EU countries. So there is a need for greater collaboration, also uniform implementation across technologies, because we have seen several and quite harsh differences between the countries. And to wrap up, for full-scale commercialization of floating PV, it would only be successful with adequate and reliable policies on EU and also within national level. Thank you very much.
Thank you, Kim, for your excellent presentation.
Thank you.
I don't know if there are any questions from the audience. If there isn't, I have one, okay?
Yes, sure.
I know that you have been doing some studies from independent universities and other, let's say, research and development institutions here in the Netherlands regarding the environmental impact of floating PV and your installations, etc.
Yes.
Can you talk us a little bit about that kind of subject, because you don't mention it, and it's very, very important, because I believe that, in fact, we can have a positive impact in terms of environment in our installations. So I believe that that is also very, very important.
Yep.
And more than that, because it's not possible yet to have, let's say, an economical value on that kind of interventions. Can you speak a little bit about that, Kim, please?
Yes, yes, of course. So in general, as you have mentioned, we have performed several research within our floating PV plants. And we also have covered one of the topics I mentioned here, so different coverage ratios, which is one very important topic for floating PV. So recently we have also included several water body coverage ratio within the Netherlands, for instance, with up to 30, 40%. And we haven't seen any significant changes on the water quality. So this is quite contradicting for some countries, for instance. And especially, I believe there doesn't need to be just a specific number threshold for all floating PV projects. So every country is different, every project is different. So I believe there needs to be some flexibility in the water percentage coverage, for instance. And yeah, basically.
Okay, thank you very much, Kim.
Thank you.
So, and moving forward, I would like Alexis Constant to come here to the stage. Alexis is a sales manager for EMEA from Ciel and Terre, and he's going to make his presentation regarding the French market developments. Alexis, the floor is yours.
Can you hear me? Yeah. Hi, everyone. I'm happy to be there. It's like the second time I'm speaking in front of you. So don't judge me if I'm a bit stressed, but it will be okay. So I'm Alexis. I'm working for Ciel et Terre for the last 6 years now. I started in 2019, where the market was quite evolving quite fast. And I will speak about our main market, which is France for now, even if we developed a lot in Asia first and then in other subsidiaries in other countries. And we'll focus on the biggest floating PV project in Europe and based in France near Champagne region. So just a word on the history of Ciel et Terre. We were created in 2006, and at the beginning we were doing rooftop and ground mounted, and then in 2010 we only specific on the floating PV, and the first megawatt scale project was in Japan in 2013. So it's been 15 years that we are doing floating solar. And we became a gigawatt player in 2020 with big milestones of a big project that represents 280 megawatts in two phases in 2020 and 2022. And in India also, we have big subsidiaries with our own laboratory and big projects installed and coming also. We have now 330 projects, which represents 1.3 gigawatts installed, grid connected, and around 2 gigawatts in the pipe also. So as you all know, the applications, I will not spend a lot of time on it. It's on irrigation ponds, quarry lakes, storage, water treatment, and dams, even if dams for now it's not the main part. And in France, it's mainly quarry lakes and irrigation ponds that is coming. On the market trends, so a few numbers. The floating PV power capacity compared to the ground-mounted PV or total PV, not only ground-mounted, but total PV, it's only in 2024 0.2%. So it gives a good impression of the potential of floating PV, even if we see that's increasing in global PV. We see also on the right that, sorry, there is not a title, but it's the installed capacity cumulative and per year. So the last year of 1.3 giga is 2024, and we reach around 9 giga of floating PV. So we see the increasing power capacity within the years. So this is the right slide, yeah, sorry. And in terms of European countries, so we know indeed that Netherlands had a big boom in the 2019, 2020, 2021. Then for some reason it decreased a bit, maybe also a grid connection quite full. And we see that France also is increasing, so the black one. And last year we installed 110 megawatts, which represent, as you see on the right, which represent half of the total installed capacity. So in 1 year, France installed the half of the total installed capacity. We see on the map that the projects are based more in the south, but coming more and more in the north of France. We see on the clear blue the project we have at Ciel et Terre. The orange one we have also, but still under construction. And the other one are not with our technology. The last one we've done, as you can see on the right, so is the Longchamp project, we say Les Îlots Blandins, that I will introduce just after. The Leutenheim project also. Saint-Savin is also a pit, sand pit, Quarry Lakes, 11 megawatts, and Piolenc, as you all know, which was the first one in France. The under construction one, there's one in Martinique. It's a 3.2 megawatt on the water reservoir. And I will come back after on it, but a lot of algae growth was there, and we really think that it will reduce this algae. And two ones also, it's Guignon, center France, that we just finished, and Saint-Élix, south of France, that we are starting the construction now. We finished the anchoring and starting the construction. So those are the last project. Let's tell you a lot of it. Just a word on the French market. So Kim spoke about it, but you have to know that France is 45% of agricultural land, which each land has also a big value. We know right now we are speaking, there is a big agricultural crisis in France. So it's really important to avoid to go on ground mounted on lands. Lots of artificial lakes, and we think at Ciel et Terre and our client developers think also that it makes sense to go on this kind of lakes to give a second life of these artificial lakes. We think it's low estimation, but the potential could be around plus 10 gigawatts, even if personally I think it could be much more. But a lot of regulations or associations or not permitted obtained are making it quite restrictive. The grid is well connected in France, even sometimes there is new connection point that needs to be built, so it takes more time to the developer to finish his project. The period of time is between 3 to 6 years. So needs to be patient as a float manufacturer. And the environmental process is also 1 year. The building permit is also 1 year, and it goes through the French administration. And I think we'll speak about it after, but the issue is that those DREAL, DDT, and this for fire, they are quite lack of knowledge of floating PV. And they don't know how to give the authorizations. It's not their priority. And just an idea of the tariff evolution. In 2022, it was 65 euro per megawatt hour. Then that we all know that everything increased in terms of raw material, and the project capex was really high. So French regulation of energy increased also those tariff, and we see it's a bit decreasing also Not a lot, but still decreasing. But the projects are coming, so it's on the ground-mounted category. There is also innovation category, but we see a project more and more coming in France. So Les Îlots Blandins, typical French name. It's a 74.3 megawatts. It's 72 megawatts of floating and 2 megawatts of ground-mounted. So it was a consortium of three companies, Perpetuum, Solution 30, and Ciel et Terre, to answer to the clients, the developer Q Energy, former RES, that were bought by Qcells. The project is, so it's 6 years of development. It's 7 lakes on the former quarry, located in northern France. It's 127 hectares, and the floating power plant is 45 hectares. It was commissioned maybe more Q2. Q2, it was connected a few weeks ago. So we finished our execution and installation on the mechanical part, anchoring, delivery of floats a few months ago, and now they did all the electrical parts, and now it's connected. It's 18,000 tons of avoided CO2, so it's quite a interesting project to give a second life. And what is important to minimize the impact, it's that it's a former quarry, but was finished few months or years ago, so the biodiversity didn't have time to come and grow. And a lot of algae, as we see a bit in the picture. And we think it can decrease this algae growth also with an important, as you see, coverage ratio. So how we work on this project, we need to optimize, of course, each design, each power plant, and it's to provide the best LCOE, for sure, as you all know. It's a 6 floating island between 8.5 and 17 megawatt peak. It's not a really windy area, so we could do quite big islands. There are different design, and we took each lake as one project, as one design, with its own anchoring, for instance. We talk about 135,000 modules from Dasolar, 56 inverters from Sungrow, and 16 transformers from GAIL. On the scopes, we are not only float manufacturer, and as you may know now, we are doing also the installation of the anchoring and the mounting of the system to increase the value chain and to master this value chain also. We think that the float manufacturer knows its products, and it's important to have the good inputs data of the sites, and then you are the most able company to install it. So we take now the liability and responsibility of the mounting and anchoring. In terms of project preparation, of course, you need to prepare your site to have, but as you can see, the site was perfect for floating PV, good shape of the reservoir, space also, because it was a quarry, so trucks were going all around. So need to prepare the civil works, the site base, phasing works, planning, it's project management at a huge scale. We thought it was maybe more risky to go on a big project like this. We say big project for us, maybe in Asia it's a small project, but for us it's a big project. We thought it was more risky, but at the end, the project was well done by our team, and no major problem happened. The good thing is that we are producing in France, so locally, so we could also decrease the price of transportation as it was really close from our factories. In terms of works, it was 15% per team. It was a ratio around 3.6 megawatts per week. And it was like an open roof factory with a lot of workers on the site, and we put three main mounting areas. What is important with a high standard quality client and project is to have a strict quality control per each production, so in each lake, because we really delivered in terms of logistics, each lake as a single project. In terms of launching of water, we have our own boat. So there is a dedicated team internally, but also with our partners. And also the important point is safety. It's important to have the safety jacket and to understand the rules of safety. We did a big work on this also at Celeta the last 5 years. And we respected the planning of the client. Then, of course, it's connecting, as you see, the idea is to connect to the expected marine line. The cabling works. It's not really our part, but we worked on this also. It gave us a lot of experience also on the add-on, as we are more on the mechanical part. We install also string inverters around 110 kilo on the main maintenance alley. And also there is all this cabling management done and also going to the shore. So we are able now to do this route cable to the shore. We signed also a contract of maintenance, long-term contract, 30 years, sorry. So the idea is to do the cleaning with robots, is to inspect the plant, to do more preventive maintenance in floating PV. We really think that if the plant is well mounted, it's more preventive maintenance than curative maintenance. I will not go a long time on this as Kim did it just before, but I think just a small map. You didn't spoke about Portugal. I think Portugal will come, but we don't know when. Public tenders are going on, but it's under Anvero licensing and takes time. And then the different regulation we expect, and in other country, here it's only Western Europe, but we really think also that Eastern Europe may play a role also in floating PV. So we really think there is a big potential still in inland lakes. I will not speak about offshore lakes, offshore PV, as it's not our target. And I think there are some conferences today presentation that will speak about it. Thank you very much. Don't hesitate if you have questions.
Thank you, Alexis. I don't know if there is any question from the audience.
Maybe you have.
Earlier in your presentation, you mentioned about one of the project where it took up about 45 acres compared to 127 acres of the land. So which means the coverage ratio is more than 15%. I think it's about 35%. So any particular restrictions or what are the steps being taken to have bigger coverage ratio when earlier our friend mentioned that there is already a framework where they're limiting the coverage ratio of 15% maximum. But in your case, you went up to 35. And
even more.
Yeah.
Even more on some lakes, but 15% is in Germany. In northern Italy, there is 50%, 50. In Spain, it's between 5 and 15. In France, there is no rules on it. It's no rules. It's a result of environmental impact assessments during 1 year and maybe more of ecological associations and engineers that are coming, that are seeing which species are there. How is the lake, understand how lived the lake also before, how long was the extraction, when it was finished. So, and as I said, it was finished few months or years ago, so the nature couldn't reborn. So it's not, there is no, in France there is a corpus, but it's administration, it's really understand the site itself. And then the administration will say, okay or not, or you need to decrease, or no, there is too much biodiversity here, or you can't go anchoring on the shore. It's what we've done here also. We anchored just below the water level, some on the shore, but just below the water level with a barge, floating barge. So you are not on the shore itself, you are on water and you anchor it directly in the bottom where there is no much biodiversity. So we had also to give answer to our client that gave answer to the administrations. But yeah, there is no coverage ratio rule in France. It's between, I think, 30 and 65%, more or less.
I believe we have one more question.
Yes, thank you. On the Blandin project, you were talking about, having a look at what will be the impact on biodiversity. I was thinking about, do you have like sensors, or how do you manage to quantify those impacts?
No, it's more before the project, they are looking at the potential impact. During the project, there are some measures that the developers give us and during the construction and the works. So we respect, of course, this measure. Some barriers for the animals during the works, for instance, or a lot of this kind of restriction of measures. But as float manufacturer and mechanical parts and anchoring, floating, mechanical floating installation, we are not developers, so we don't go into those studies. It's more our clients that does it, and I think a lot of studies are in place on some projects. I think Q Energy will do it in this support, but we are not part of this of the studies.
We have one more.
It seems the biggest project in, in Europe is quite interesting.
And I'm going to have another one at the end.
Okay, okay.
Thanks for the presentation, Alexis. Quick question regarding algae growth. You mentioned that on several projects you have algae. What is the impact on the design? Because it probably adds some weight on the float or on the mooring system. And what's the impact also on the maintenance and inspection?
Indeed, it has an impact, and that's why it's really important to have the site data and to understand and to do site visits. And when we were to the site, we saw a lot of algae, and we said, okay, but how we'll go with the boats? How we'll go to install it with the lines and coring lines? It can twist, it can have a big impact. It depends also of the species of the algae. There are several species, invasive, and those on the site were invasive. So we had to add additional works to remove those invasive algae to finish the work properly, to install it. I'm not a specialist in algae species, but it was a work before the installation of the anchoring, indeed, because it was so dense that it was impossible to move with the barge or with the floating barge or the boats. We had to, and this we discovered it during the site visit few months before. So it was additional work that we had to do in the rush.
And does it have any impact on the inspection plan, maintenance plan?
In the maintenance plan, yeah, it's something that you put in your OPEX as you need to check if there is no algae regrowth there, and to remove also. But as we've done it before, we know more or less the price of days to do it.
Okay, thanks.
So to finish my question, I had to ask one anyway. The question is, you mentioned that there are some lack of knowledge of the authorities regarding the environmental impact studies, et cetera, of the floating PV. Is there any plan to share the conclusions of your installations, let's say that way, the results of your installation in terms of environmental impact to the authorities? Is there a plan to let them know what is happening, or that is still also a lack of knowledge on that?
Yeah, there is a plan. In France, we are part of the Syndicat of Renewable Energies, so the Association of Renewable Energies in France, of PV. I was in Bordeaux last week, and the idea is to do a working group to say to the government, okay, floating PV is really a pillar of PV. It has a very good sense to do it on unused lakes and unused lands. So there is a working group on the technical part, but also on the financial and for sure the political one. So not a lobby, but to push to increase to the government and administrations as they are not trained, and they said it takes long time to have all the authorization because the people behind their desk in France, they don't know, they have a very long list of projects to authorize, and they don't know how to do. They fear, okay, I don't know this project, I don't know floating. They just sum up quickly, but it's a lack of training, of knowledge. So the idea is with the experience, with float manufacturer, with developers, with EPCs also, the idea is to do this working group and to push the administrations. Yeah.
No more questions, Alexis. Thank you very, very much for your presentation.
Thank you all.
So, and now, moving forward, I would like to ask Fabrizio Bizarrif, that is the head of solar innovation from Enel Green Power, to come to the stage and to do his presentation regarding the floating PV experience and innovation from a utility company. Fabrizio, the floor is yours. Thank you very much.
Hello to everyone. So first of all, just one slide about Enel. I hope that you know Enel is leading the renewable energy, the transition, and in all over the world. We are present in 28 countries, and we are at least more than 66 gigawatt, well distributed. You can notice that for hydro, that is important for PV floating, we have at least more or less 33 gigawatt installed worldwide, mainly in Italy and in Spain. For sure, we want to increase our presence, and so we have a strong program of investment in the next 3 years, 12 billion, mainly in wind and solar, you can see, and mainly also in Italy and Iberia. It's important that because we want to invest a lot in the photovoltaics, and also PV floating is an important sector for us. What we did in the last 5 years, we work a lot, even understanding which are the best solution that we can implement. There is an issue of competitiveness of this kind of technology, and so we try to improve the existing technology, even making some adjustment at a lab level. We have in Catania, in Sicily, a laboratory with a small lake in which we tested this different kind of solution. So you can see there are a solution that is prefabricated, so cubic floats that are typically prepared assembly in a factory and then sent in the site. There are a solution, and you can change for sure the tilt of your plant and put in the modus, for example, in landscape or portrait. The second solution that is more traditional, you can find the tube everywhere, is a solution in which we tested the east-west configuration. And then finally, we test also as a prototype, because at the beginning was no one doing this kind of tracking system, with a tracking system just to understand which is the behavior. And finally, we have some agreements, especially one for this kind of solution for monoaxial tracking system. So, but it's important to understand that all the benchmark is made from the single activities with a reference of PV ground that is in the same area, in the same labs. We also had, as I told, some new solution just to increase the production. One of that was adding a sprinkler system to the modules just to increase the cooling effect that we know is already present in PV floating, and we obtain even a good results. The production increased from 12 to 14, but finally we have had even some issue in terms of landscape films on the panel. So is a solution that we have to consider for the big plant is not the best appliance. But nevertheless, we try to do that. And another thing that we try to do is to increase the albedo. You know, the albedo for the PV floating is not the best that we can have. And so considering that the plant in operation, typical plant with tracking system with the on ground, has also disadvantages coming from the adoption of bifacial modules, we try to put also some system to increase the albedo. The results was good, but for sure the bolts decrease the reflectivity during the lifetime. So it's something that we have to manage exactly better, to considering also an additional O&M cost. So finally, the results of the test are good in terms of solution. We can recover even some producibility that we lose due to reduced albedo, and so we demonstrate that the producibility is this kind of solution with a low tilt is more convenient for short latitude sites, and we obtain also a 6% more production respect to fixed installation, thanks to the cooling effect that typically giving from 3 to 6% depending from the solution. The bifacial gain, we obtain also the bifacial gain that is even higher depending from the kind of solution. So if we consider the first solution with cubic system, we can have also up to 5% of increasing in the production. For sure, we don't have the maximum if you use tube system. If you put modules in the landscape position versus portrait, we can also gain something in terms of producibility, around 1.5%, sometimes even 2%. This is an evidence at our latitude in Sicily. In terms of albedo, I already told about that. For the tracking structure, we have this agreement in which there is even a benchmark test outside of Italy, in which there are solutions, typical tilted solution with a tracking system, and the results for the buoy system, that is the second system, was very good. Also respected to the results that we obtain in our laboratories. Is quite from the gain in terms of producibility is quite from 11 to 25% more, and this due to for sure a cooling effect that can help a lot this kind of solution. So in terms of bifaciality gain, we also obtain some advantages, but for sure is due to the second solution, in which there is a white equipment below the modules that can help to improve this kind of solution. Is good even also the approach of hydrostatic, that sometimes is important because we don't have any gear, and so eventually some losses of oil that can bring an issue to manage the basin that sometimes is potable water. So finally, we also make a lot of tests, putting a lot of instruments, a lot of sensor in the water to understand the impact in terms of environmental. Also demonstrate that there is not relevant impact for the water temperature in terms of eutrophication or dissolved oxygen, and also other parameters are not relevant. So this is important also for the materials. We use different kinds of materials, and we don't have any evidence of leakage of heavy metals. And in terms of biodiversity that is present from a long time in that lake, we don't have any negative effect. For sure, we found that there is a good reduction of evaporation. And finally, we developed, together with the University of Catania, even a simulation tool to understand in all our lakes, in all our dams that we have in our hydroelectric plant, which are the best solution in terms of percentage of coverage to obtain the evaporation that we want. So finally, we demonstrate what is written also in some scientific paper that I repeat just to share that. That finally, depending from the surface occupied, so considering 30% or 50%, obviously we have more effect depending from the solution. And this solution is between a ratio from 0.5 to 1, that it means that we can have for 1 hectare, for example, about up to 10,000 cubic meter of water savings each year, depending obviously from the size and from the solution. So let's go ahead. Finally, after this kind of experimentation, we built the first plant in 2023 in Venaus, in the north of Italy, where we put 1 megawatt of solution with cubic HDPE cube. And finally, we try to build this plant very quickly, and thanks to that, thanks to the sharing of the project with the community, we authorized the project in 3 months. The construction took 3 months too. And finally, after 1 year, we obtained even a good results in terms of performance ratio. So we increased the performance of about 1% more, demonstrating that is a good solution also for this kind of small dam that we already manage. It's important to underline that the best results of this first plant was finally the hybridization with the existing hydroelectric plant. So we know, we understood well that you can have also a lot of advantages in terms of permitting, in terms of cost of connection. So finally, the capex will be lower if you use the existing connection of hydroelectric plant. You can also have a lower O&M cost due to the fact that you already have people that are managing the plant for hydroelectric system. And also we can leverage a lot this kind of plant also for technological adaptation of the hydroelectric plants. So we use this kind of plant also for digitalize or not only the PV floating, but also the hydroelectric plant. This is not enough, because after this first experience, we decide to doubling this plant, also adding another 1 megawatt, but considering also the advantages that we have foresee. So the possibility to empty the tank for the scheduled activities for the desedimentation. So thanks to that, we have had a cost reduction for the global works of about 10%, also a reduction of the time, some advantages in terms of permitting. And finally, you can see, I don't know if it is possible to show the video. Is a photo with a video, but I don't know. It's a pleasure to show because in the meantime you can see that we build this first plant. Yes, exactly. Without water. So because it was exactly made together with other works. And this is a great advantage because we build the plant in only 2 weeks. And we have also risk reduction, safety risk reduction too. And we can put together these two kinds of activities. This is not enough too because we build this kind of plant also considering a new kind of solution for the desedimentation. I can show you. So using the same floating system, floating platform, we had an integrated desedimentation system. So this kind of hybridization gives us the opportunity to even to obtain a continuous desedimentation. And so finally, we can reduce in the future also the O&M activities due to the desedimentation. And this kind of desedimentation that is made by some agitators that are installed below the floating plant and maintain a sort of dredge raft that then can move the sediment, and then with a pump we suck up the sediment, and we bring this sediment or directly to the turbine or outside of the dam. This was made continuously thanks to the energy available also from the plant, but also thanks to the presence of the floating that help us to build and to maintain that system. So this is how it works. We don't have so much time, but finally you understand that is an experimental system that we want to add also in other dam. It can have even a lot of advantages and give us even the opportunity to improve also the maintenance of hydroelectric plants. So finally, thanks to these first activities, we are now in a phase of evaluation of a strong pipeline in Italy, in Spain, and also in Brazil and Portugal. We have just a plant that we want to build of 42 megawatt. And we already make some evaluation thanks to a tender that we launched last year. And we are evaluating also new solution, launching some challenges for our plant in Italy. So what we learn from this kind of experimentation, for sure, the first things that are important is that hybridization is not only the connection, so the presence of the dam, so using the same basin, but also the connection point, the electrical point, and all the other things like sensor automation, connectivity, monitoring, that you can add at the existing hydroelectric plant, and also to the grid ancillary services. For example, we are now considering a plant which there is also the storage, so PV, storage, and hydroelectric plants give the possibility to have an hydroelectric plant that can give some services like primary and secondary regulation, even if are small plants sometimes. We can offer for the grid this kind of solution, and so the hybridization is something that add value, totally speaking, to the hydroelectric plant. So finally, the pro are for sure, in terms of permitting, could be more simple, especially if we consider that we build the PV floating not only in a lake, a natural lake, that is difficult and is right, that is difficult. So it's something that's changing also the environment. But especially for the dam is a solution that we can apply. It's possible to apply quickly too. There is advantages because there's not a land lease. There is an extra PV production that you can analyze depending from the solution. There are many advantages in terms of logistics, in terms of connection, medium voltage or high voltage too. The reduced evaporation is something that is very important, even in the last few years. We notice, and we have even a strong program to develop artificial lake just for avoid or to maintain the water. So just to avoid the evaporation is something that is very important. And so finally, we can improve, thanks to the digitalization that we had when we start this kind of work, improve the security, the civil safety, and also we can have IoT for hydro, for the PV plant, for the inverter, for the monitoring. So the cons for sure are that we are at the beginning of to consider the tracker solution for the dam. It's important tracker solution because you can increase the production of energy, so become more competitive respect to the ground system. Then we have to consider also the plant geometry that is not perfect sometimes. So we are also considering canal application of floating PV for canal, and so there are some constraints. Finally, there is some constraints in terms of tilt that is reduced, so you have a reduced production. And important thing is to underline is that the phase of design have to be considering from the beginning with the hydro asset. So it's important to understand that the know-how of operation and maintenance of hydroelectric plant, it's important to consider from the beginning. It's important that is a part of the design from the beginning. Just 1 minute, just to talk about Italy. We are pushing a lot the energy transition. Also, thanks to that, in Italy there is a legislation, PNIEC, that already was talked by my colleagues, by Ivar. So it's not important to repeat, but it's important that there is this small presence, only 50 megawatt, but it's important because it's just the beginning. And I'm sure that if we use these 50 megawatts, we can also produce more, demonstrating the validation of technology too. We are also working in Brazil, where there is a good opportunities for the plant below 5 megawatt, because there is a good price energy below 5 megawatts. Over 5 megawatts, the price energy is very low, so it's not convenient finally. And there is a potential of a pipeline of 6 gigawatt. Then finally, in Portugal, we have a plant that we will build the next year, that is 44 megawatt peak. This is something, finally, that is important. I already talk about that. It's important finally that if we want to build, we are to focus, in our opinion, on hybridization with dams, existing dams, to make even simple the acceptance by the community, sharing the production of energy. So the energy have to be produced and consumed even locally. And so the synergy with the CAPEX is evident with the hydro plant, and also with the O&M activities. Also, the digitalization using the same asset is something that is very good also for the PV. So finally, we work together with an approach of open innovability. So all together, we are available to have from you, from other company, with typical works with industrial partners, financial community, supplier, customer, institution. So we are open to accept a new solution and to evaluate also for a proof of concept in our asset. This is just something that you find in our open innovability sites. There are some challenges. One challenge is with artificial intelligence. The deadline is on June. Another is with a new kind of the design for a wind turbine. Thank you very much.
Thank you, Fabrizio, for your excellent presentation. I don't know if there are any questions from the audience. If not, I will ask one.
All is perfect.
Wait just a second, because there are people online, so with microphone, people hear us better.
All right. Okay. Thank you. So you shared about a lot of data information that you gathered over multiple tests across different case studies. One thing I just wanted to ask you that what is the future challenges which you are looking at, which you would like to address through floating solar, the technology-wise, what enhancement you look forward for in the present floating system, which you think can help solving the problems?
Okay, there are not specific solutions that we are underlying, because they are depending from the sites, typically from the sites. And so, for example, if we had for some site a high variation of altitude due to the water that is moving during the day, we consider different kind of solution. So finally, there is a lot of challenges regarding the mooring system, the anchoring system. So depending from that, we can choose a different kind of solution. For sure, now we are oriented with, thanks to the good results that we obtained the last years and even the installation, in the solution with Cube, that it seems good also for some gaining that you can have indirectly, because it is a solution that is ready, deriving from the increasing of the albedo. And also I know that will be presented also, but it's a solution that could be in the future even adapted with the tracking system. So, we know, just an underline, we have also a development of PV, not only in the dam, but also in the canal, sometimes as a floating, sometimes as a covering as PV. But finally, this kind of solution can adapt well, yes.
Thank you. Thank you so much.
Thanks.
If there are no more questions from the audience, I will ask one.
Yeah.
There are a lot of possibilities for investment in floating solar, as you've shown, with different possibilities and so on. Very, very, very short, let's say that way. What are the developments and your development plans for the next years in terms of floating PV?
Yeah. Okay, thanks for the question. So we have analyzed, just to give you an example, in Italy and Spain, we have a lot of them, more than 30 gigawatt. And we make an evaluation during the last year, and starting from more than 200 plants available, and at the first step, useful for the PV floating, that was about 7-8 gigawatt, considering a percentage of coverage. We arrive with a pipeline that could be sure, or is a solid pipeline that is half gigawatt. So it's not so much from the starting, but finally it's important because it's something that is possible to do considering all the constraints. So we are working on that direction, and also we are in phase of permitting in Italy for 20 plants. That is about 50 megawatt. That is more or less the availability of the tariff. But finally, these are the numbers, the road numbers. Yes.
Thank you very much, Fabrizio. It was a pleasure. Thank you for your presentation. Thank you.
Thanks.
And now, let's move forward. I would ask Conrad de Vries to come to the stage. He is the founding partner of Start Green Capital, and he's talking about the financing trends in solar, especially in floating solar. Okay. Thank you very much.
Okay. Well, I think you're next stop before coffee, so I will try to keep the time schedule right. From now, I will give some perspective on the finance part as an investor and as a financier of energy projects. To explain a bit the opportunities, but also the difficulties we have sometimes to finance floating solar. My name is Conrad de Vries. I'm the managing partner or founding partner of Start Green Capital. And to give you a bit of a glance of what we're doing, I'm not sure, you're the one who doing the technology or myself? Yeah, sorry, I find it. I have an idea, so it's working. So Start Green Capital. We are around almost 20 years. We are an investor and a financier in early stage or either clean tech companies or energy projects. And we do that as a company with approximately 40 people in the Netherlands. So we are sort of the early risk taker before the bank steps in. So we can do either junior debt or equity to make it possible. And then we invite banks to take the senior debt and do the whole financing round. So you could say that we are the early adapter of projects to finance. We manage approximately 650 million asset under management. And you can see here we have several funds or labels under management. Means we are a multi-asset manager, depending on the mission or the focus of the fund. And the general mission is that we want to make this world, take care of itself, so that we have a renewable energy system, and also in diversity that we can give everybody the opportunity to be themselves, and also make sure that they can perform the way they want. So diversity and sustainability have been our focus the last 20 years, and though there's some more political resistance, it doesn't matter, we just simply continue in our route. To say that, we are actually in energy transition, diversity and circularity. And today I want to give a bit of our projects in floating solar. This is our sustainability report last year. There will be next one, so I don't go into depth here now. Let's go to our floating solar part. So in general, you noticed, especially people from outside, that the Netherlands is a bit of a wetland. So we have a lot of water. Maybe it's all the other way around. So we have not much soil to build normal buildings. So it's more water than say solid soil sometimes. And that makes it really possible to have, of course, a lot of floating solar. And that's also what we saw is the market is growing, and there's a lot of opportunity to build even more floating solar. And this is because there is less space, but also because there's, and I also heard my foreign speaker in France a bit here on this side, there's also a political perspective change on agricultural use of agricultural land for solar. So, and that's also logical. So if you can use it a better way, even for biodiversity, that's also great. And then we can use the more, say, industrial waters for, floating solar. That will be a better way to use your land or your water surface. So that's one of the other reasons that we see more and more opportunities and also a bit political pressure to go to, say, industrial waters for your solar production. Another thing is that we have a good subsidy scheme. It's a bit up and down. The last 2 years, 3 years were not so good, but I expect that there will be new inventive schemes And also expect to the new political movement, say the Clean Industrial Deal, which now launched on European scale. We also expect coming years to have much more subsidy and grant schemes for even renewable projects, but also for floating solar. So in general, I think the Dutch market would be really interesting for project developers or technical parties to step into or do even more. And yeah, we as financiers see also the opportunities there. To go into the business case or the case we have produced, we have done the Bomhofse Plas. That's a Dutch word. It's a park, it's a East Mid-Netherlands, a bit north, it's nearby Zwolle. It has been for a while the biggest one, but that's the great thing about renewable projects, so there are now bigger ones, which is good. It's 27 megawatt, up to 7,000 households, 27,000 panels. So this is was a huge park, and we actually bought it. It was developed by BayWa, and we did here, and that's interesting to also discussion before. We always are, if we do a project, we want to have political and also civil implementation. So we want to have connectivity with the people living around the park. What we called burger participation, which you could say civil participation of people also investing in the park. So what we've done here is actually to one of our regional development funds, which we have managed, we actually pre-financed the sale of the park, and we make it possible that the people living around the park, living in Zwolle or nearby, could also step in with an equity share. So that we are now partly owner to a corporation of cooperative model in the park, together with us, you know, as a financier. And we also provided the junior debt. And then we asked ASM Bank, which is one of the largest sustainable banks in the Netherlands, to step in with the senior debt. So it's sort of the mix of 75% senior debt, 50% junior debt, and 10% equity. And where the equity and unit debt is shared with the people living around, so that you actually share the profits a bit with the people who are actually seeing the park. Although it's still not so, it's well covered on surveys, but still it's, you know, it's close in your area. So we arranged it. We arranged not only the financier, but also the civil participation, because we do a lot with crowdfunding platforms together. And we did all the other stuff you should do to make this sort of projects happen. But it will take a while if you do these sort of large projects together with civil participation, because you need to structure the deal a bit different, and you need to have a bit more time than you would do if you have a plain vanilla senior debt funding. We are, yeah, as I say, really happy on also reasons. The first thing is it's no land use. It is less visibility. If you would walk by, you could hardly see it, because sort of, you know, it's a how say that, it's a pit quarry, it's a sand pit. So it's not. It's still in use also. That's also nice. So it's not an old one. It's still in production. But also makes a lot of opportunities that I will go in later on. Yeah, as also explained by my previous speaker a bit, is that we see in our figures that it also gives a bit more production than land mount solar. So it's interesting to see the report, but I think the cooling part and the less shadow part makes these sort of projects have a better yielding. And we did, of course, because we are sustainable financiers, and we are, any fund we manage is according to Article 9 in the SDVR, so it's the Sustainable Finance Disclosure Regulation from the EU, meaning that we have to do a lot of ASD checks to make sure that if we do something, it should not only have a clean production and energy, it should also make sure that you don't harm the environment. So that's why we have a lot of biodiversity opportunities there, also by the park, which is sort of plastic, not plastic, bioplastic sort of framework, where you could also have growing of natural life under the solar field. Now, the learnings for us as financiers still, and though we are in this project now for approximately 5 years, is that the most difficult part is always that you want, if you are a debt provider, you want to, also as equity provider, but especially in debt provider, you want to have a sort of demonetization or steady cash flows where you can count your DSCRs on, your payback models. And in solar, that we know it now because solar has been there for ages. But for floating solar, there's still some maintenance issues which is hard to really predict on the coming years, which makes it sometimes harder to have a larger senior debt provision. And without a senior debt provision, your returns are actually declining. So you need a large part of senior debt because this is the cheapest form of financing, of course. So there's a bit of a struggle that we have to find ways to have a better prediction on the maintenance cost. As I say, the water-cooled panels, so we see a bit more performance and better performance there. Like I said, the maintenance costs are the hard part for us as financiers to get our fingers around, especially for the, say, coming decades, if you have a park for a longer period. The real learning we have, it is nature, and water is even more nature, which means that we had some problems because we had really inflow of money, so we had high waters, much more than we expected 1 year, which gives some problems from the anchoring, which is now solved, but that was an issue. We also noticed that the wind was different than we were expecting, more west than southwest. I don't know, but usually southwest is the determining part of that, but also gives some more stretch on the technology on some parts. Another funny thing is that the bird dropping was really something we should learn on, meaning that there's a lot of bird dropping, and also you have to make sure that you handle it well. So what we now have learned is that we have to clean it in the spring really well, because that's the moment where you have the best production. So you have to also manage your cleaning mechanism, your maintenance cleaning, the best way according nature, let's say it that way. So that was one of the technical learnings. We had this funny discussion in the Netherlands. I'm not sure if it's in other parts of Europe also, but that we had a discussion with the local authorities that is it property or is it floating of its boat, So if it's property, you have to pay property tax, but we're not expecting. And property tax would give a big hit on our returns. So we had a long discussion, even to court, that this is not a property in the sense of a building or it's like a floating system. We actually won that one, and I think it's an important one also for the next projects in the Netherlands that this is now recognized, because if you have to pay property tax, your whole KPIs and financial model will be significantly changing in the negative way. The last part is, I think, I also addressed a bit more, but also I think it's interesting to share here. We really believe in civil participation for actually all our renewable energy projects, especially for wind, solar-mounted projects, but it's also for floating solar. So we really like it if there's a cooperative. In the Netherlands, you have energy cooperatives, which are sort of the cooperatives established by the local people who want to do something with sustainable energy, to get them involved in these sort of models, which we've done here. And the nice thing is that they are actually giving voting power, so we also involve them in the decision making. Of course, we make sure that it's not a sort of, how you say that, dead block, so if possible, you can still move, but they are not only giving money, they are involved in the decisions. And you make sure that it is less NIMBY, in the sense that it's not in my backyard, which you all know NIMBY. And of course, I mean, if you have a civil participation, it's not that people suddenly, there's still a lot of people might be against it, but at the end, it's at least you have the financial returns shared with the local community. I mean, if you put it the other way around, it's even worse if you don't like floating solar in your face, in the sense in your environment, and then all the money goes to some sort of investment bank, I don't know, somewhere in the world. Then you say, okay, so I have all the negative effects here. So we see that it's helping also in political alignment and support. And there are some consideration here. I mean, if you attract financially, because it's an investment, money from people, you nearly have to go to professional platforms to make sure that everything is handled according to not only the financial laws, but also according to normal governance you would expect for a financial product. Meaning in sense of governance and know your customer and, anti-money laundering, and these sort of elements are all relevant because you are attracting money from individuals to invest in a project for 15 years or 10 years. So I think you should be aware that, in our experience, is that we only can do that if we do together with professional platforms to make this sort of civil participation happen. So this in general was my story about financial perspective. So there's some time for questions or discussions or.
All right, thank you very, very much.
Yeah.
I believe that there are questions. At least I saw some raised hands.
Yes. From a financial perception, how do you look at, as an investor, at the cannibalization effect of solar energy these days, especially in the Netherlands and Belgium, lots of negative prices, and also the market for CPPAs or VPPAs is really saturated, so it's hard to close the business case.
Yeah.
What's your opinion on that one?
That's true. I mean, negative prices are hurting in the Netherlands the business case. But we see that as a temporary effect, meaning temporary, not 1 year, probably 8 to 10 years. But projects are even are there for the longer period. So to be a bit more precise, if you look to the net congestion and negative prices, that's all, of course, supply-demand issue, where you have much, where you're ending in negative prices. And we see a lot of positive movement on the 3 elements to restore that. That will take time. The elements, of course, are connectivity. So I think there will be more connectivity, Netherlands to other countries, or even other countries in Europe. We see a lot of opportunity also for ourselves in creating more storage. So we do a lot of battery projects. Even Bomhof-de-Plas, what I just showed, will have a large battery project close by in their own project, which they can also use for their digging machines, because it's still a working sand grid, so they will be electricalized. So then you have all your electricity behind behind the meter. I'm not sure that's, but then you have still in your own, you use it yourself. So I think, connectivity, storage will be improved. And the other thing is that we really believe that that on the long run, you have a better demand system in the Netherlands or other countries, meaning that there will be pricing on energy, so you have less use on the moments that you have negative prices. So in general, as an investor, we are actually open to do more projects. We are buying projects now because I think they are sort of negative evaluate. Because if you look further than 5 to 10 years, then we all know that we need clean energy. Meaning, we all want to have less fossil energy, either for the climate or for our energy independency, given all the geopolitical issues. So you should not look at negative price for 1 or 5 years. You should look at 10 to 50 years. And that's also how we look at energy projects. So maybe a long story saying that I think there's actually an opportunity now to invest in parks. But that's our vision as investors. So that's a bit,
I believe we have 2 more questions at least.
Hi, good morning. One question, do you concentrate on project finance in the Netherlands or only, or do you look to other markets as well? What is your strategy for the upcoming years?
In general, you could say we could invest in Europe, but therefore I need good co-investors, because we would never invest in other countries outside the Netherlands without a good local co-investor or financial bank. In general, most of our projects are financed either Netherlands, a bit in Germany and Belgium, but we could co-brother. So we don't have a strict no-go area in that sense, but we would look to partnerships to go to other countries.
And we have another.
One last, then we have to go for the break.
Hi, morning. With regards to the project finance, what is the financial requirements and also the interest rate that we are looking at for the floating solar compared to the ground-mounted solar? Is become more stringent when it comes to a floating solar? Floating solars compared to ground-mounted. So ground mounted, shouldn't be much issues, or it's already matured, I would say, compared to floating. So how you look at it when it comes to financing requirements on the SCR and so on, and also the interest rate compared to the ground mounted solar?
Don't think we have another financial criteria than for other energy infrastructure projects. So we won't have the same returns we would have for any energy infrastructure. We look to the, actually, yeah, it's a bit project based. We look to the returns risk modeling. So for us, it's not that we want to have another return or say a higher return on floating solar. The only thing we would have is to have better prediction on the maintenance cost and the cash flow, so we could actually manage our risk side. Sort of helping you. So we don't, if we would look in Netherlands, we're now looking for 2 parks to finance. We don't have other financial criteria than that would be on mountain solar. And in the particular situation in Netherlands, there's not that much choice because mountain solar is not much there anymore because it's a small country and there's less agricultural land available. But we would not change our KPIs on the return side. Yeah.
And I believe that we have one more question behind you, if you don't mind.
Yeah. Yes, Saki from Sweco. Thank you for your presentation. My question is more or less about some places which you have problem with the grid.
Yeah.
You don't have grid capacity. So maybe you have the best case project, but you feel on the grid. Then the only solution is BESS. How you see this as a solution as an investor, and thinking of that you will increase the capex of a project and it will be much more expensive to have like battery storage or solution, or how do you see in this one? Will it be same interest for you to look at such a project, or just like, no, we don't invest where you have bad or you don't have the capacity to connect to the grid?
Yeah. Yeah, the grid capacity is of course a huge problem. So what we now do is we finance actually a lot of battery BESS projects on already running solar parks or wind. So as discussed in this Bommelsplas floating solar, we will have a large BESS project. So there will be a large battery storage developed besides the project for the use of energy. So in general, I think coming years we will invest in storage. That either in BESS or other ways, combined with the production parks which are already there, maybe in our own portfolio or portfolio from others, where we will help getting on battery energy storage systems or even other models to capture and store the energy. So the congestion problem will lead to more storage investment efforts from our, but also from other financiers. There, of course, we have to check a bit, because if everybody's doing storage, then somewhere there's no model anymore, no business model more for storage. So this sort of way where we have to find an optimum. But I think coming years we will do a lot of batteries.
Thank you.
And that is going to be the last one, because we have to go for the coffee break.
Yes, thank you. Very fast. Do you think that civilian participation could work well also in other countries, like I think Italy, Spain, Portugal? And in case, how do you analyze the locals?
The locals or
the locals? Yeah, the civilian. I mean, to understand if there could be a good participation from.
Yeah, I think it can be worked all around Europe. I mean, the funny thing is we have a lot of experience in local participation, because we also had our own crowdfunding platform, which we sold 2 years ago to Investdoor, which is a European crowdfunding platform. For instance, there's now in Belgium a large tender, I think that's the word, for an 80 million civil participation for a wind farm at sea. And I think if you look to the numbers, I'm not sure in Europe, but in the Netherlands, although all the crises and although all the opportunities, the savings went up every year. So the savings in private hands in households has been growing all these times. And the funny thing is, of course, this is a bit more risky than your saving account, so you should not take all your money. But if you, for instance, in the Netherlands, if you would say, I think there's 360 trillion savings in personal hand. So if they would do 10% of that, if people would use 10% of that in well-structured energy projects, either on offshore, on land, or whatever, then you will have 16 trillion money to invest. So I think the government is leaving this opportunity sort of, they don't understand it in a way, and I think it's a win-win situation because it's not only new money, it's also connectivity in the sense of that people are connected to the energy production, but also lead to a better understanding of the power and also the difficulties of sometimes sustainable energy. So it's also a way to get people involved in the energy decision, not only financial.
So, Conrad, thank you very, very much for your presentation. Thank you all of you for your questions and so on. Thank you very much. So, we reached the coffee break time. We have half an hour now of break. Please don't take much longer because otherwise we are going to be late for lunch, okay? So half an hour, have a good coffee break. Let's get back in half an hour, okay? Stage is yours. Lars. Who's missing? Who's missing? Who's missing? Who's missing? Andres is there.
There are four of us, yeah.
Alexis. Where is Alexis?
Nice to meet you. Oh, I thought it was a spotlight. I thought it was a spotlight, but it no, I like to be in the spotlight. You know, that was a. And my voice. I tried to inhale oil juice this morning at breakfast. Did you do good? Oh. No, at breakfast, you know, swallow it, but it went the wrong way. Oh, okay. That's the first time. I was coughing like a dog. Now my voice is even deeper this morning.
He was not in the conference call.
No, but he's like this. He had his mistake. He's French. Oh, oops.
Colombia. I'm actually born and raised in Colombia. I lived there 26 years, and then I moved to Spain. So I'm living in Spain.
Okay, you're based in Spain.
I'm based in Spain.
We're missing Alexis?
Yeah, Alexis is missing, but Alexis is coming. So, let's continue, let's say that way, with the panel discussion, where are market trends in floating solar PV heading? Alex is not here, but I believe he's coming, so he'll join his chair when he will return. We have Lars Brandt, we have Andres Franco, we have Daniel Reinhardt, and we have Joaquin, that is going to be the moderator of the discussion. So the floor is yours. Please go ahead. Thank you.
Good. Thank you very much, Antonio. My name is Joachim Ruppia. Very happy to moderate the panel on the market trends today with fellow panelists. And well, we got Alexis coming as well. So we are all hands on deck, or all men on board, as we say. So talking about market trends, just maybe to kick it off, a quick introduction. My name Joachim Rupp. I'm working for Apricum as a senior advisor. So that is on the strategy and transaction advisory side of things. And well, I leave the panelists up here to do a quick introduction as well. To start it off.
Well, hello. My name is Lars Brandt from Cflex, working with moorings of floating solar. So see you more later.
Hello, my name is Andres Franco. I'm the CEO of Isigenere. We are a manufacturer of floating solar structure and anchoring solutions since 2008.
Yeah, I already introduced myself, so Alexis from Celeta.
Hello everyone, my name is Daniel Reinhardt. I'm head of sales and project development at Swimsol. We're a solar integrator for tropical islands, and we have developed our own floating PV system for marine environments.
Maybe I keep the micro. Yeah, that might yeah.
We'll give it back to you.
I hope so, Andres.
Good. So let's dive into the topic. Yeah, the market trends. Yeah, we've heard already a few presentations. Yeah, this morning. Yeah, so what we would like to do, follow the agenda, give you some insights on the regulatory and policy developments. Yeah, to start off, also the role of technology advancements, efficiency, and scalability. Yeah, and then also some future projections. Yeah, so we're trying to aggregate and get this well, on a more global or at least a European level, yeah. So in terms of the regulation and policy, yeah, in the preparation, yeah, we talk quite extensively about that, yeah. So I think starting off with that topic, I guess, yeah, permitting is still a bottleneck, yeah. So maybe you can get started, yeah, on that, yeah, and develop, yeah, in terms of the regulatory side of things, yeah.
Sorry, it was a breakfast incident that changed my voice. I think what Alexis presented here this morning, I think it was with all these different regulations, was a really good summary. It was Alexis, right? And we see that it's very, very slow in the adaptation of these things in different countries. And like it was also said in the presentation, it's because of the low experience or competence out there that is taking too long time. But we see it slowly at least, but it's taking a long time.
The situation that we are seeing also in Spain, in Portugal, it's similar to what was described before, that regulation is slow. We believe what should be important is to somehow the industry try to come together to do things together, similar to what has been done, for example, in agrivoltaic, that there is more resources and there's more common work done at the European level in order to speed up the adoption of the technology. And right now there are a few things going on, but it's very mild. We believe we should try to do more to adopt faster and to show, because many times it's just the governments, they don't have enough data to feel comfortable with the legislation. So they are very conservative. That's what happened in Germany and also happened in Spain, that the first law, there's regulation, but it's really, really bad for the adoption of floating solar. And it's because they don't have good information. If we can collaborate and share some of the information to put that in front of the bureaucrats, we believe that it's going to be faster, the adoption.
Yeah, indeed, I think we are still in educative stage of floating solar. We are all doing this for a long time, and we work in our technology with our clients, etc. But we need to avoid forgetting that the people doesn't know it very well, that the administration doesn't know it very well. So we need still to push at national level, at European level, all together. I think float manufacturers, developers, investors, even if investors, we need also to convince them, insurers also. But we need to push with EPCs also that build the plants. I think, yeah, we need to push at a global level as each country at its own development rhythm. And they are also have its own demographic increase or its own agricultural land field and value. In Spain, there is still a lot of space, but also big reservoirs. So yeah, we need to look at each country, but also at European level.
So maybe I can comment a little bit on the marine floating solar side. So we as SwimSol, we're actually active mostly far away from Europe. We're active in the tropical regions of Asia and Africa. And one general development that we've seen in the last couple of years is that there have been an increasing number of public tenders coming up in different places like Maldives, where we're mainly active, and Seychelles. There's been a tender in Lakshadweep, which is an island region belonging to India. We've seen similar things actually in Dubai, and I think 2 years ago, the Greek government also started an initiative to fast-track marine floating solar pilot projects, which, however, also didn't really go anywhere, unfortunately. The biggest challenge that I really see when I'm in discussion with public utility companies, for example, in the areas that we operate, is that floating solar or marine floating solar is often benchmarked against conventional PV systems, ground-mounted PV systems, and they basically expect that the solar tariffs that you offer, the LCOE, is more or less equivalent to what you get for at a ground-mounted system somewhere in, I don't know, India or Sri Lanka, and that's of course very challenging for us. Of course, one other aspect generally is that the permitting process in the sea, I assume, is maybe even a little bit more difficult than in a lake, possibly. In many countries, there is absolutely no legal framework to obtain sea space, basically. A good comparison can sometimes be like offshore fish farms, so they do have some process where they can obtain the sea space, but I believe that's usually for a shorter period of time. So that's, I would say, some of the regulatory challenges that we mostly see.
Okay, so on the permitting side, I think that topic came up quite frequently. Anything else which would help in terms of policy and overcoming the hurdles from the regulatory issues you've got in mind? Example,
Well, one thing that we have seen that helps in the adoption, especially from the governments, is to start slow and move fast. And what do I mean by that? That sometimes there are these big projects, they're going to be a 50, 80 mega project floating solar. But the local authority that will, and we are seeing that happening in Portugal, that they had a big auction that was led by the government, by the central government, but now the local authorities are saying, no, I don't want that because it's too big and they have a lot of uncertainties. Our recommendation is to involve the local authorities and quickly get to build small project, can be 1, 2 megas, so you can get the authorities to measure, bring local universities, and with that data, you can also show it that there will be no problems, and then you can start thinking of a next phase, because legislators, in uncertainty, they tend to be conservative. So put data in front of them with a small project that probably is not going to take a lot of time to build, and then scale up.
Okay, so aggregated from the bottom up basically, and build the momentum.
Yeah, one thing that's also important, I think, is this common use standardization efforts from DNV. That's soon, I hope, will be some kind of a standard. There is a recommended practices already that we in the industry has helped together to build up. But that's now in the internal works of DNV to become a standard, the first standard in the floating solar. So I think that's a very good step forward. We just need to adhere to that now and work on that and see that also the legislators understand that this is a standardized solution.
Yeah, just to come back on this, I agree that we need standardization, but it's really difficult as each float developer, float manufacturer has its own technology with its own constraints and loads applied, etc. And its own way of designing also, because the idea is to know your product, to design it well according to the site condition, to the needs of your clients, south, east, west, etc. And standardize. Sorry, this it's quite difficult, but indeed it's good to have a more global framework to not do bullshit on technology. So it's really important indeed to go on the safe way. As we are speaking about projects for 30, 35, even 40 years of business plan. So yeah, it needs to be this, but it's difficult. So that's why I think personally it takes time to understand. And to be honest, we don't want to all disclose our own constraint of each product and loads applied, etc. So it's difficult. We are still in a business model of companies, so it's difficult. We want to share, of course, and to release some innovations and to move forward. But of course, we have confidentiality. Sometimes need to be clear on this.
I think that's good. We're moving already in terms of the topics. We are addressing into the technology readiness and commercial aspects. But Alexis, yeah, you wanted to comment, yeah.
Daniel, sorry. I just actually wanted to reiterate a little bit what my previous speaker said. So for us also, one key strategy is to build up some nice demonstration systems and to showcase this works and then to replicate this in other places, because I think if you can showcase that you've done something before, I know for inland floating, of course, there are already many references all around the world, so there's not so much to showcase anymore. But if you work in marine floating solar, which is still a very early stage sector, it helps a lot if you can showcase that you built a 1 megawatt, 2 megawatt plant somewhere, and that you can replicate this quite easily somewhere else. On the topic of standardization, yeah, I would say in a marine setting, this is also even more difficult because every marine area is completely different. So that is here even a bigger challenge than it probably is in inland water bodies.
So standardization actually might be difficult, yeah, to achieve, yeah, all together, yeah. How about scale? Yeah, how important is scale? Yeah, what kind of a market driver is that? So larger and larger projects, or we heard smaller?
Yeah, I mean, we've been seeing quite significant economy of scales from the mooring perspective. I mean, I'm not saying that it's linear on the panels and the floats, but it's more linear than the mooring system. We have examples with, going from 100, 200 kilowatt kind of test site to multi-megawatt. And we're seeing 80% cuts in only based on economy of scale from a geometrical perspective. I mean, the same prices. So that's extremely important that people understand this, because they cannot just extrapolate the high cost, relevant high cost on the small scale project and think that's the same cost, but because you can cut it in half, definitely, at least for the mooring system.
Yeah, on my side, I think it's better to go a bit higher than 1-2 megawatt. As you all know, that with volume, we can also decrease the capex with a lot of economies of scale in the production. So yeah, I understand, but I think projects are more profitable over 5 megawatts. It's what we see. I mean, in inland lakes, I don't know, maybe offshore you need more and more to absorb higher cost of capex. But yeah, it's a good idea to go small, but a bit more than 1-2, I think. But we need to scale up and to go bigger. What we see in Asia is that it's going fast sometimes. Maybe they need to be a bit slower sometimes, but we have to take the good ideas of what they are doing. They are developing fast, and they are maybe looking less points or constraints that we are looking in Europe, but it's symptomatic of what happened in Europe and in Asia. It's that in Asia it's going fast. In Europe it's coming 5 to 10 years after. Even in US also it's coming, and then Europe does the same. So yeah, but as you said, there are a lot of democratic but also bureaucratic society and countries. So it's difficult to have the permitting, but that's why we need to scale up, but bigger. Make fear maybe sometimes, but yeah, we are trying to move on bigger and bigger project. Even for our own company, it's better to work on a bigger project to save the economies also on engineering and all the human time you spend on it, and to manage it well. It's the same that you work on a 5 megawatt project on a 50 megawatt project. I mean, not exactly the same, but the idea is the same.
And I agree that in general, it would be better to have larger project, but it's like, okay, do you want to build a large project with a probability of success of almost 0% because it's not regulated, or do we start with regulation? And it's the fact that in Europe, it's all about regulation. So I think it's important to try to balance, to get the politician and the regulation comfortable so that it can move fast. And when it moves fast, I think it's happening in France. In France, on average, it has the largest floating solar projects, but it's a clear regulation. We also believe that you're going to get significant economies of scales on mainly on the services around the floating solar project. So that's engineering services, independent advisor services, legal services, all of that. And then also on the manufacturing, it's not the same to negotiate a small project or of large project. It's important when you have a big project to try to get good prices and to mitigate the potential fluctuation of the raw material prices. And when you have a large project, you can do that. You are not at the mercy of what happens with the market. So hopefully that's something that will happen. Definitely it will bring down the cost and improve the CapEx. And I think it's a matter of moving fast on that direction.
Yeah, from our perspective, I think that's for us a little bit the question mark. We're not 100% sure. Obviously, when you have bigger projects, you have lower overhead costs, that's clear. I think our biggest problem is that every project is quite substantially different than the last project, so we can't just replicate always one thing that we did at one place and just make it bigger at another place. We always need to customize certain elements, the mooring or anchoring system, for example. And from that perspective, we can't really say how high the economies of scale would really be for doing a project that we're now doing on a 2 megawatt scale on a 20 megawatt scale, for example. But yeah.
So, but that would be for your particular case, yeah. So more likely for offshore. I think we should well make a clear point, yeah, for all the standard systems, yeah, or inshore, yeah. Maybe it's different, yeah.
Yeah, I think it's really important. I mean, the offshore development is, of course, super important. And it's, all the lookouts are so good of those potential. But I think we need to separate these two very, very clearly, because I'm seeing with regulatory people, with lack of competence and understanding perhaps, and financing, that they mix these things together. And I think it's very important to see that the inshore and nearshore, which you also work with, is already fully commercial, fully tested, and you have so many examples and references out there. But, the real offshore with, 14-meter waves or 20-meter waves, that's a different animal altogether. The TRL levels on that is, significantly different. So there are so many companies here, of course, working on that, which is a separate thing. But we need to, separate them in a better way, I think.
Yeah, I fully agree. Often you hear these two categories, inland floating and offshore floating, but obviously it's kind of a spectrum with many things in between. I think Cieliterre did in Taiwan, I believe, like a floating system in a sea area, but like a kind of harbor area, which is fully protected. So this is maybe a hybrid between a lake system and an offshore system. We are working mainly in settings where you have waves of, let's say, up to 2 to 3 meter, which is, of course, a completely different story than if you're somewhere in the North Sea. But even if you look at a sea area with 3 to 6 meter high waves, this is also a completely different story than when you're operating in the North Sea. So I think you have to differentiate very closely between the specific settings that you're working in.
Yeah, indeed, just a word on the Taiwanese project. It's so I show it before, 280 megawatt project, and it's on a lagoon, industrial lagoon, with the tidal effect twice a day. But it's 2 meters of tide effect, and there is no big waves. High wind, but no big waves. High wind and high irradiation, but no big waves. So I'm not the best person to speak about offshore. You are more.
I think we did the tour, did the rounds. Yeah, Antonio, do we have time to do Q&A? Also, get some questions from the audience. Yeah, just a quick summary. We talked about standardization. Yeah, we talked about the importance of economies of scale. Scale is important, and the regulatory issues and the joint efforts. Yeah, to bring that up and educate, basically, the different bodies. Yeah. Any questions from the audience?
Hi, with regards to the regulator, especially recently, we heard that Spain encountered a national blackout, if not mistaken. And they said it's mainly due to a solar plant which it been isolated because of certain incidents. So what is regulators' acceptance on the solar, and also what are the mitigation actions that being taken for that issue?
Reality, like right now, nobody knows exactly what happened. So this is just fake news. If anybody says something, there slowly it seems like it start appearing information that the government or the organism that was in charge of managing the network in the previous day had done things in a different way. But it's just a speculation at this point. I believe that solar will continue being significant part of the energy transition. It might be that the systems and the networks will need to adapt. There will be more battery connected. I also see a trend in Europe of nuclear going back and betting that even Denmark, that in the past was one of the first countries to ban, it's talking about reintroducing nuclear. So I think in general, when you have a lot of investment in solar, you need to adapt other things in the system to make it work.
Yeah, just a word on this. In France, as you know, we have a lot of nuclear. And they said when this turnout came, they said, oh, it's the fault of solar. Because in France, they want to kill solar. Because we are competitive, it's fast, and there are investments in solar, so they want to have more money for nuclear, for sure, and it takes more time to develop a new nuclear plant. So yeah, lobbyists in nuclear in France are saying, no, we don't want solar. So they take this example of, yes, it's the fault of PV solar in Spain, but yeah, as you said, we don't know, yeah.
Just a general question on the permitting. Don't you think there's quite a big need to get more data also? Because now we say the coverage ratio, what's the impact on the wildlife ecosystem and so on? Don't you think that's something also the sector itself should take up to gather a lot more data, to do a lot more assessments, to help government to have data to prove, look, this is okay, this is not okay, because now it's really difficult. Just try to find some effective publications by a university or someone. It's almost impossible to find real good data and repetitive data.
Yeah, it's ongoing. I mean, at least at European level and France, and even in Germany with Constantin and IFE, that is doing a great job to push on this and to doing some research on this. In France also, some results will come in June of the University of Toulouse to CNRS, the Center National of Research. So they are pushing this and showing the administration. Yeah, that was my.
But still, I see that there are some universities and some countries doing a few things, but I think it needs to be more.
Yeah, sure.
And it needs to be more because if always statistically you will say if you have one data point, it's not going to be enough to draw a conclusion. So that's again another topic that if we can somehow, and maybe in that case it's not going to be proprietary data, but it's to try the universities to collaborate and to gather the data. That's something that we try to push in the project, to install monitoring devices that, yeah, they cost a little bit of money, but you get the data and you can use that data to understand what's going on with the impact in the aquatic life. And hopefully with that information and from other countries, you can also show the authority that, look, this is safe. And if you follow certain rules, you don't need to be over-conservative, like only 5% of surface coverage. That's super conservative. It's almost like no regulation. Yeah. So I think we still need to do more on that.
Yeah, and I think it's coming because there is the SHORE project also in Europe that they are looking and doing some groups of work for the environmental impact assessment of floating. But as you said, a lot of external factors make it difficult to standardize.
Yeah, I mean, working in the seaside, maybe surface coverage is not the big question, but we do, of course, often get queries about what is the impact on marine life. We actually have commissioned reports by marine biologists who visited our system, did a comprehensive study, and this definitely is like a good argument when you want to develop new projects, that you can showcase this and show that there is no negative impact. But of course, it always depends very much also on the site assessment. So when you're in the sea, there are areas where you have zero impact, and if you build such a system over a living coral reef, for example, this could have quite a negative impact. So that's maybe, yeah, perspective from the marine floating side.
Okay, so I guess any more questions?
Yes. So a transition to marine, on your belief, or I'm asking you, like, what's your vision in terms of timing? Like, it will be in 1 month, 1 year, 10 year, and what's the key to go from inland to sea?
Well, we used to analyze, and we were thinking and trying to get a product for offshore. And we decided a few years ago that we were not going to do that, because it's a complex situation, much more complex. We have built projects in places that have 2-meter waves, 80-meter anchoring, water level variation of more than 20 meters. And we have found solution and technology that works. But when you go to offshore, I think the conditions are even harsher. And we believe that the solution is going to be a completely different solution. There are companies that are looking at how to solve that. I don't know still the economics. That's the key question that I like to ask in any offshore presentation. Okay, what the cost of that project? And I have not been able to get a number. But I think it's several orders of magnitude on that one. So I have a lot of uncertainty if the business case will be there to speed up adoption, to make it economically feasible from a commercial point of view. With subsidies, you can make a lot of things with subsidies. I don't see that happening in the next 5 years for sure, but I'm sure there are other people here in the offshore, because I think nearshore is possible, but offshore, I think it's really complex.
Yes, I spoke about this spectrum earlier, and I agree, like, basically the rougher the conditions, the more open the sea setting, the more questionable it is whether this will ever work commercially. Technically maybe, but commercially. So there I'm also not that sure. We as SwimSol, we're working in this nearshore setting. I always say semi-sheltered sea areas where you have waves of maybe 2 to 3 meters. Arguably, we're working in a very niche market at the moment. We're working in tropical islands, basically, which simply don't have enough space on land, which have very high energy generation costs because they're mainly using diesel generators. I think our idea was always to kind of kickstart in these kind of settings where there's an obvious business case, scale of the technology. Right now, we have 5 megawatt peak of marine floating PV systems installed, and we're going to double this probably by the end of this year, beginning of next year. So we're building a lot of single megawatt scale systems at the moment. We have had many discussions in the past about larger systems in different areas. I can't really tell you when maybe a 10 or 20 megawatt system will come. We're working on it, but right now we're focusing very much on the setting where we know that our technology works, where it's commercial, and then we'll just see where we go from there. I can say that, for example, just in the Maldives, in the Seychelles, and a few other key markets, we have identified a potential of several hundred megawatts, actually.
Yeah, and to answer your question, I think same point of view of Andres at Cieleta. We are not doing the choice of offshore, but we think it will come here between 5 to 10 years. Maybe the solution could be first to have a good raw material. Because it's with the salt, etc., and the algae, we know need to have a good solution, but also to combine maybe with wind turbines. For instance, in France, Total Energy or EDF has offshore wind turbines, maybe to combine with it, so could be a solution also.
Yeah, Daniel, one last comment, yeah? Then maybe we can wrap up, yeah?
Of course. No, just because you mentioned this topic now, we've been addressed actually quite a few times to basically hybridize wind farms, maybe in the North Sea or something. And I always basically say I find it very difficult to imagine how this is going to be commercially viable. And then the argument is often, well, we already have the grid connection. okay, that's great, but if still your LCOE is going to be 30 or 40 cents, it still doesn't really make sense just because you have the grid connection. So that's my take on that. I think offshore wind farms are often in rather rough settings, and there again is the question whether you can really make this commercially viable or not.
Very good, yeah. Thanks a lot, yeah. I guess, yeah, we have to somehow wrap up, yeah. Maybe we can, yeah, have one last comment from Lars and then talk about the market as such also, yeah, to give a bit of an opinion, yeah.
I was just saying that there's 9 minutes left, and at the end we need to make the microphone to him. That's, you know, I didn't ask for the microphone really.
Yeah, no, we can make good use of the time. Yeah, so we had some questions already, yeah, from the audience. Yeah, where I would like to get to is obviously also, yeah, talking about the market. Yeah, we talked a lot about obstacles and hurdles and what needs to be done, and I think a really good discussion around that. Yeah, but let me turn that around and have a look at it on the other side. Yeah, given all these factors, yeah, would be solved, or all these issues would be solved. Yeah, where could floating PV actually go? Yeah, in terms of size, in terms of market, yeah, compared, yeah, to the total market, or compared, yeah, to what you have at the moment. Yeah, what do you think? Yeah, the next outlook for the next 3 to 5 years, maybe.
Yeah, it's quite a daunting question, of course, but I think all of us have seen those fantastic numbers out of so many sources. I mean, we have the World Bank, the McKinsey reports, and many others, DNV and others. And we have also seen, I mean, the graduation of growth in our sales pipe, I mean, which is just staggering. I mean, we're proud over that we installed 500 megawatts, which is, you know, a little bit. But I mean, the way gigawatts in potential processes out there in different stages. And that's promising, but we see this, you know, the hockey stick as it was looking for the World Bank is like this, and then it goes. That has been moving forward every year. So I think it's at least last year, it's a lot of projects out there, but not to the extent getting to finalization that we really thought. But I think it's just the market now, at the best thinking, is taking a fresh breath, and moving forward with a lot of these projects. That's what and we see a very big projections up ahead. I mean, tenfold in 5 years. That's what we're looking at.
Yeah, for sure. The idea is to have a reliable solution. As we always said, the importance of input data is the most crucial point to have a safe project for a long time. So of course, reliability, scalability, and durability for each product, but each country also, and then the industry will continue. I think there is still a big potential. We are looking, and we discussed before the countries that will come. It can be in Eastern Europe, it can be also in Western Europe. Still a lot of dozens of gigawatts. And as I said before, with demographic increase, electrification of use, I think, yeah, we need to avoid going on lands and going on water, near shore, inland waters, water reservoir, etc. So we have a good future, I think.
Yeah, no, I agree. I think there's significant potential. We believe that there are going to be 3 areas where floating solar will grow. So the first is that hybridization will happen. It will not just be...
We don't know when, but it will happen.
Yeah, it will happen. It's sure that it's going lower than expected. But I think the first good example was the auction last year in Portugal, where only in 6 water reservoirs owned by the government, they auctioned 250 megas of floating solar. And there were the EDP bid in that process, they won the 100 mega and bid with a negative price. So they actually paid to get the floating solar plant built. Why? Because in their business case, the hybridization of the hydroelectric facility that they already manage, Alqueva, with the 100 mega floating solar project, with a battery park and with a 80 megas wind project, made sense. And they're going to build that. They are still in the process of getting the permitting. So I think that's going to happen. There's a lot of, it was also mentioned by Enel, today that they have these hydroelectric facilities. They don't have land around. They have the connection point that it's a very low use. In Alqueva was only 36% of use of the connection point. So you can take advantage of that infrastructure. So that's one. The second, I believe it's floating solar has been already proven and a lot in former quarry lakes or artificial ponds, but now needs to move to other type of water reservoirs. So I think there will be legislation and growth on more natural type of settings with, of course, with restriction on the amount of surface cover, but that will also boost, and there's a lot of countries with lakes. I'm not saying to put this in the middle of Lake Como. Like you need to choose where to go. It's not just because you have a water reservoir you do floating. You need to choose wisely. And the third, I think there will be a growth also in artificial ponds, but not for, let's say, the large connection to the grid utility scale project, but more on the self-consumption behind the meter projects. So the same that happened with solar in the roof, that now you have a lot of smaller projects. That's something that I believe is going to happen. And that can also speed up the adoption for the big project, because when you are giving smaller project for an agricultural client that is putting it in the small basin that reduces water evaporation, doesn't use agricultural land, that's a good show of the use of floating solar that will help authority to say, okay, this is good for my constituents. It makes good sense. So I think that will be the third area of potential growth of floating solar in the coming years.
Yeah, to come back on hybridization, we don't speak about it, but also Africa may play a big role in it. And MENA, maybe on nearshore, quite big also areas.
Yes.
Very good. Yeah, last comment. Yeah, we're getting clear signs from Antonio. Yeah, to wrap up. Yeah, and close.
Sorry, okay. I think I already answered the question earlier where I see marine floating solar going. So I think it is something that will grow over the next years in the places where there's a case for it, basically. I don't think it will be utilized everywhere, simply because the cost is quite high, and I don't think you will get it on a low enough level that it's usable anywhere. Yeah, I think that's my conclusion to that.
Very good. Thank you very much.
Thank you.
There you go. My microphone. Have it back. I need it. Thank you. That one
is there. Yeah. Okay.
Okay. So thank you very much, guys, for the panel discussion. It was really good, in my opinion. I had no microphone, so I could not ask some questions because I had some to do, but I'll do that later. Because in fact, we are going to have other people speaking about the environmental aspects and of floating solar and so on, but it's okay. So now we are going to move to another intervention from Dr. David Bird, that is going to speak about modeling tool for floating PV water quality impacts. So, David, the floor is yours. Thank you very much.
So hello, my name is David Burt. My project to develop this tool is joint between Lancaster University, Innovate UK, which is a UK governmental body for sponsoring innovation, and Thames Water, which is one of our larger water companies. The agenda for my talk, I'm going to discuss a bit about how water companies have synergy with floating solar panels, floating solar arrays, specifically sort of British water companies. I'll then show a case study from a reservoir that Thames Water owned called the Queen Elizabeth II Reservoir, which has a smaller coverage ratio of about 5%. I'll go a bit more into my tool and how it's used and give a use case study for it, as well as going into how FPVs might support maintaining water quality under climate change, and then I'll summarize it to try to bring together a sort of a case study and a case for why FPVs could benefit water companies and how tools such as mine might help their adoption. So first, I want to go a bit into what water companies do and why FPVs would be beneficial to them. So focusing specifically on England and Wales, there are 16 water companies that each own regional monopolies which more or less follow river catchments. Thames Water specifically have about 16 million customers focused around London and the southeast of the UK. And they process between their waste and clean water 7 billion litres a day. So these water companies source clean water from nature, they treat it and then deliver it to homes and businesses at a potable water quality. And then they also then collect wastewater, treat it, return it to rivers. And these are ongoing, these companies aren't static. They invest in their infrastructure, including replacing our pipe network, because our pipe network is quite old, and also seeking to build new reservoirs to support future demand. I'll go a bit into drinking water reservoirs. So specifically, they're used to store water to ensure a supply during periods of high demand or during dry periods, such as droughts. They also serve a purpose within the water treatment net chain by allowing heavier particles to settle out. Sorry, give me a second. Shown by the diagram there very early on in the treatment net chain. Thames Water own about 30 of the reservoirs, which are not only used for water treatment, but also serve community purposes, allowing bird watching, sailing and fishing. However, because they are early on in the water treatment chain, the water quality within the reservoirs is highly important as it can affect it affects things further down the chain. So to discuss a bit about what I mean by water quality. So water quality refers to biological, chemical and physical aspects of the water. The graph shown are observations from one of the Thames Water reservoirs called Farmore 1, which is near Oxford, which shows temperature, oxygen, dissolved oxygen, and chlorophyll A, which is a proxy for algal concentrations. Specifically, temperature can be an issue as during winter, when there are lower temperatures, it can lead to increased pipe bursts. Algae can block filters within the water treatment works, so need to be removed. And one option is to control them within the reservoir. And dissolved oxygen can lead to negative chemical reactions in the reservoir that can lead to taste and odor issues leaching from the sediments. And specifically, by focusing on the summer of 2018, you can see a warm period of water, obviously during the summer, was met with an increase in dissolved oxygen, then followed by a sharp decline in dissolved oxygen. And this coincided with a chlorophyll A spike. And just to highlight that these events, water quality issues, are not static, they are changing, obviously seasonal. And each of these pose different water quality issues that require different treatments for each site, and these can drive up costs. So go a bit onto the water treatment side of the problem. Water treatment is a land and energy intensive requirement. Energy is Thames Water's second highest cost after labour. However, Thames use about 1,300 gigawatt hours annually. However, there is a drive to reduce the traditional energy production, with a goal for the entire water industry in the UK to reach net zero carbon by 2050. Thames Water is taking steps to expand its renewables. About 27.3% of their energy currently comes from renewable sources. And this is to minimise their energy costs and reduce the reliance on the UK national grid, which can fluctuate in prices and can lead to spikes. High energy costs that lead to large energy bills for them. However, Thames also do own quite a bit of land. However, this is often set aside for developing future treatment sites and to expand sites if needed be and to change treatment methods. And also some of it is set aside for nature reserves. So FPVs help offer a way for Thames Water, specifically in my case, to keep this land set aside for their future plans, and use reservoir services that are often underutilised And as shown by the diagram, by my map, the top white square is what is the Walton Water Treatment Works in southwest London, and the lower white square is highlighting the QE2's solar panel array, so they're very proximal and allowing for a short transmission distance. And next I just want to go into a bit about broadly what lake models are and why they are powerful tools. So lake models allow us to examine the interactions between the physical and ecological dynamics. This diagram is from one of my earlier studies during my PhD, which was just looking to model lakes under climate change. And you can see sort of the lining up of how the model is performing. And this allows us to engage in system scale knowledge understandings. So we can do this by changing climate conditions. So for this study, I ended up taking this model and forcing it with predicted climate change data to understand how this reservoir would perform in the future, specifically looking at its stratification, which is the process of when you have high temperatures in the top and lower temperatures in the bottom of the lake, which can cause restrictions of reoxygenation into the bottom of the reservoir. So as seen by the lower diagram, you have, during high temperature differences in the surface, in the water column, you have lower oxygen in the bottom. And this allows us to understand how lakes will respond to different climate conditions. And my tool is going to take this principle but apply it to solar panels. And to sort of discuss the need for this within the industry, water managers are cautious. They do not like any large changes to their reservoirs, because if it changes their water quality, this has negative impacts, or potentially has negative impacts further down. So there needs to be a case that FPVs will either benefit or have minimal impacts to the water quality currently within the reservoirs to support their adoptions. And models such as the one we're working on will allow us to test FPV designs under varying weather conditions to help show them that it will be beneficial or minimal. And using the tool, FPV systems can be tailored to each specific reservoir to reduce their risk and maintain their current desired conditions, or specifically to target problems that exist within one reservoir. An additional benefit could be that it allows us to cut down on expensive monitoring campaigns, which can be labor intensive and time intensive. So now I'm going to go on to explain the case study of the Queen Elizabeth II reservoir. So this is in the southwest of the UK. It's a typical reservoir for Thames Water in the fact that it's a non-impounding reservoir. So rather than block the river and build a dam, it's instead effectively built a bowl, and then water is pumped from the River Thames into the Queen Elizabeth II. It's about 20 metres at its deepest and covers an area of about 1.3 square kilometres. Its coverage of the array is less than 5%. It's a 6.3 megawatt array and can power around 1,800 homes and covers 60,000 square metres. It's noted that next to the Queen Elizabeth II are two other reservoirs. They are smaller, called the Knight and the Besborough. However, due to their proximity, they share similar climate conditions and are pumped from the same section of the Thames, so have similar inflow water quality. Another benefit of these sites is as the water body managers conduct ongoing water quality sampling at about every 2 weeks to ensure regulatory compliance. So this allows us to effectively have two controls for the Queen Elizabeth II reservoir to see if the FPV has affected any of the water leaving the reservoir. And I should note that this is for water. They usually take these samples from the outflow from the reservoir. So these are for conditions leaving the reservoir, not necessarily for conditions beneath the FPV array. So these graphs are show the frequency of measured values as a percentage for before and after the array. I should say, the array was installed in 2016. So these lines both represent about a decade of data being summarized. And just to explain it, for the top graph, before the FPV was installed, around 5% of the measurements taken from the QE2 were around 8 degrees Celsius. Broadly, you can see that for temperature, there's not been a meaningful change in the sort of the ranges measured, though for the QE2, there are now there's less measurements of higher temperatures taken within the reservoir. However, this could be due to sampling conditions. However, there are more uniform pattern is seen with the dissolved oxygen, where after the FPV has been installed, there are higher measurements of 100% oxygenation within the water column, and after the FPV rate has been installed, there are a larger increase in the amount of chlorophyll measurements nearer to zero, which suggests in the last decade there's been a reduction of the amount of algae present in all three systems. However, as these changes are seen in both the dissolved oxygen and the chlorophyll across all three reservoirs, including those without FPVs, it's unlikely that these changes are due to the FPV array. So based on this, we can say that the 5% coverage has not meaningfully impacted water leaving the reservoir in the last decade. And this is in line with other studies which have shown that smaller coverage ratios do not meaningfully affect the water quality. These changes are likely driven by shared meteorological conditions within both reservoirs, and there's also been changes to river conditions and the ecosystem. So by river conditions, Thames Water have been taking steps to reduce the amount of phosphorus that leaves our wastewater treatment plants. And also in the last few decades across the UK, but specifically within the Thames Valley, there's been a spread of mussels, which are filter feeders that can remove particles from the water and sort of clean and increase water clarity. So these could explain those changes. However, we do lack data for beneath this particular FPV array. So hopefully within the next month, we'll be working to install 2 monitoring chains, which will more some instruments beneath the array to get information on sort of dissolved oxygen, chlorophyll concentrations and temperature and light, which can hopefully sort of fill in this gap. So next, I'm going to go a bit onto the tool that I've been working on. So the tool is using a pre-existing 1D model. So this treats the entire water body as a single water column to sort of as the engine to build the tool around. And the inputs for this tool are as shown from the top graph, screenshot of the current tool iteration, meteorological conditions such as air temperature, wind speed, cloud cover, and the lower one shows sort of the tool requires sort of an idea of the lake's bathymetry and shape, as well as inflow conditions. So the tool we've been working on allows the user to customize forcing events to test specific events. So in the example shown here, I have changed the conditions so there is a meaningful heat wave in July where temperatures would reach around 30 degrees. And the lower one shows that the user can customize the FPV array. And we've done this by allowing you to change positioning. While not currently in the current version of the tool, I do plan to be able to subdivide the lake into smaller sections so you can get better measurements, better simulations of what's happening underneath the array compared to the wider water body. But the user can decide the positioning, the size, and we allow the user to reduce the amount of solar radiation and wind action underneath the panel. And this is to account for sort of differences in panel density, walkways, and different FPV design limitations. So it's a bit of a use case for the tool. I ran a simple experiment where for a reservoir, another Thames Water reservoir called Farmore, which is located near Oxford, I think I mentioned it earlier, we ran 10 simulations of increasing FPV coverage ratios from 0 to 100% at 10% intervals. And this highlights that the results are non-linear, particularly with this study, it's around 60% that the linear patterns begin to break down. Generally, as FPV coverage was increased, the reservoir cooled, and there were reductions in chlorophyll A concentration, so a reduction of algae. However, the effects are seasonal. So chlorophyll and summer temperatures represent the temperature sort of from June to September, and the winter temperature is from January, February, and December. And it shows that there are greater effects on summer temperatures than winter temperatures. And this could be useful for trying to sell this to FPVs to water companies, as they're more concerned about water temperatures during the winter, as this can lead to pipe bursts in the UK, which is a source of leakage and is costly to fix. And I think this underscores the need for tailored designs to maintain or improve water quality within different reservoirs, as these sort of acceptable reductions in temperature might be different for different sites. So going on to more broadly about how FPVs could help combat climate change and the effects of climate change. So I want to focus a bit first on how models are used broadly to predict the effects of climate change. So a common practice is to take models calibrated on modern day data and validated on modern day data and assume that the patterns that are true now will hold true into the future, and then force this with predicted climate change data from various institutions. I've obviously been from Britain, focused on the UK Met Office, who has a robust data set, which is the UKCP, so United Kingdom Climate Change Projections for 2018, which is the data set that I've used going forward. And they predict, they allow us to take air temperature across into the future, and broadly, so I've done from 2020, which was in the future when this data set was made, to 2080, and you can broadly see that, unsurprisingly, air temperature is increasing as we go forward. So using these two using models calibrated on modern day data and predicted climate change, we can predict future water quality and hopefully plan for, anticipate future challenges. So I'm going to go very briefly into what the current understanding of what climate change will do to lakes is, so we can better understand how FPVs are uniquely positioned to overcome these issues. So the graph shown here is another output from my PhD, which is future projections from the model I showed earlier. The top two show the surface temperature of the lake and surface temperature and bottom temperature of the lake, and the bottom two panels show stratification, which is the process I mentioned earlier, where you have differences in temperature between the surface and bottom, and that can lead to isolations of the lower and core sort of taste and odor issues within the water. So broadly, climate change is likely to raise surface temperatures and alter stratification patterns. It's less clear with bottom water because it's quite dependent on the lake. But warmer conditions may lead to increased algal blooms, which could disrupt ecosystems and also increasing water temperatures can change different species tolerances and might cause shifts in species dynamics. There's a prediction that it will change river flow patterns as it leads to alterations when rain happens, and this can impact water availability as well as water quality. So this could change when a water company has to pump water from the river into the reservoir. So broadly speaking, overall, climate change will alter water quality and may necessitate developments or expansions of treatments, which could cost quite a bit of money for the water companies. So we use, as another sort of use of the tool, I did a similar 10 different model runs, increasing coverage ratio from 0 to 100%, and then I modelled them for from the UKCP climate change data for the year 2000, 2014, 2080. These are shown by the heat maps, which are both for summer temperature and summer chlorophyll concentrations. And the blue lines on them show how much coverage is required to maintain conditions from 2000 going into the future. So obviously, broadly, the takeaway is that higher FPV coverage ratios help to offset climate change impacts by cooling the reservoir. This study showed that 65% coverage cooled the water to offset climate change, and 5% was required for chlorophyll. Just to summarize, water treatment is an energy-intensive process, and FPVs offer a nearby source of renewable energy. They can help maintain or improve water quality, but it's crucial that it's crucial that maintaining water quality in the drinking water reservoirs is maintained. Models can help to test FPV designs to ensure that they have a neutral or beneficial impact on water quality. And FPVs have the potential to support water security under future climate change. If you have the time, we're trying to collect sort of input for a UK reservoir research group via a survey, and that's the QR code for the survey. Thank you very much.
Thank you, David, for your presentation. I don't know if there are any questions from the audience. If there isn't, I will have one.
Thank you for a very nice presentation. I was wondering if you have taken potential changes in the wind speed into account in the model due to the floating PV system?
So not directly. The user can increase the wind speed going into the model if they want, but obviously that does require somewhat understanding of how FPV arrays will increase wind speed. So that's something I haven't considered yet, but is worth including if possible. I will look into that. That's a really good point.
No more questions? Yes, there is another question. Wait a moment, please.
You look now statically at what the influence of a FPV system might be. Well, one type of system, because I think the geometry might even have an influence. But do you also consider at checking what mitigation you can also have add-ons to change, to adapt to possible negative impacts?
Again, not something we've considered. Like I know you can use, for instance, biohuts to sort of counteract some of the effects of biohuts to combat some of the effects on biodiversity considerations, and obviously you can also make it so that the panels have gaps in them, which might allow more light through. Sadly, using a 1D model does limit some of that understanding because for considerations of area effects, 3D models are more beneficial. That said, 3D models can take a lot more processing power and time to run. So the tool that we're developing is more of a plan for a 1D model, so fast simulations of large scale, of multiple different FPV arrays. I know there is work done at Lancaster University by a PhD student who's looking more specifically at 3D modeling that might allow for better understandings of sort of some of the mitigation strategies in the design. We're attempting to sort of capture design by changing the light and wind that makes it through the array. So the way that my tool would adapt to sort of, if you put in gaps or spaced out the solar panels more, to sort of offset those effects would be by like increasing the amount of light that makes it through.
So I have another question that I believe it's important in the middle of all of this, that is the economical impact that your simulations can have, especially on costs and also on benefits, because we heard this morning that the capex of the floating solar is a little bit higher than ground-mounted. Yes. So the costs are something that is important, or if you can measure other benefits that we can have, how can be your impact in the situation? So
I think the main potential for benefiting sort of saving costs is by reducing the amount of field work that is needed beforehand. Obviously, this requires the tool to be prove that it can be effective on covering FPV designs, but particularly for water companies, I think it requires more robust data sets. So there's still a need for fieldwork campaigns now, but hopefully in the future, when we've been proven and the tool's been proved to be effective, we can help water companies sort of cut back on costs in order to understand how the water quality would be. Sorry, I sort of forgot the rest of your question.
That was mainly the question. It wasn't that. It was how they can profit from the investment of having the system.
Yeah, so I would say the main cost to saving would be sort of a reduction of the required planning by sort of the tool is very simple to use and you can do lots of simulations fairly quickly. And we'll also cut down on a water company's need to do water quality studies leading up to the building of the array if they fully understand how it will affect the array, how it will affect the water quality.
Okay. Thank you very much, David.
Thank you.
So, and now we'll continue with the environmental aspects in a certain way. So I would like to ask Konstantin Ilgen to come here and to do his presentation about the hydrological and ecological effect of floating PV in Europe. Konstantin is from Fraunhofer Institute for Solar Energy Systems. Good morning. Please, go ahead, go ahead. Thank you.
Yeah,
So I would like to present you some results of our research project FPV for Resilience. The project is basically about the hydrological and ecological effects of floating PV in Europe. First of all, I think we already saw the first graph, but I think the message is clear that floating PV on a global scale is getting momentum, and we saw a rapid increase in installed capacity, especially in the last few years. And what we are also talking a lot about is the lake coverage, and there's a study showing nice numbers for the global average of the lake coverage. So it's like 34%, considering over like 500 different projects. And you can also see that the standard deviation of 22 is quite large. So we have higher variability across all the projects. The key drivers for the lake coverage are mainly the lake size and also the morphology that are explaining most of the differences here. However, most of the lakes are mostly moderately used, so most of the systems cover less than 50% of the water surface. So let's take a look to Germany. In Germany, our first FPV system was installed in 2019, and all systems are installed on artificial lakes. And you can see, especially in southwestern Germany, we have a lot of installed FPV power plants and also planned ones, mainly on gravel pit lakes. However, since 2023, there's the Federal Water Act restricting the expansion, as you already heard, to artificial or heavily modified water bodies. We can only use 15% of the lake surface and have to keep a 40-meter shoreline distance. In our opinion, this political action is mainly based on a risk mitigation approach because there's very limited knowledge on the environmental impact of floating PV. And we also think that the main problem here is that this regulation applies to all the lakes the same kind, so regardless of their ecological quality. And this, of course, reduces the potential of FPV in Germany. So that's why we thought it could be worth to have a closer look on the environmental impacts in the FPV for Resilience project. And here you have an overview on our research topics in the project, so going from all the impact on the chemics of the lake to the biology, but also we had a look at the performance of the power plants, social acceptance and perception, climate change scenarios, and also finding like the optimal FPV coverage ratios. However, today we don't have so much time to have a look at all of these topics, but we will concentrate on the water quality and also on the macrophytes, so water plants, mussels, and look how hydrodynamic modeling can also help us here to have reliable forecasts, and then have a look on how this impacts the regulatory framework. So the main research questions are: which processes have the largest impact on water quality in preferential FPV lakes, and how should the current legal framework in Germany be assessed based on the results of this study? So let's have a look at the study sites. So we have three different ones. One is in Switzerland. It's a pilot power plant, so a bit smaller, covering 1% of the lake, but it's shaped on the special conditions in this alpine climate. So it's located at more than 1,800 meters above sea level and on a hydropower reservoir. The next one is in Germany on a gravel lake, and it's covering 8%, has this pure float system design, and has an installed capacity of 1.5 megawatts. And a third one here in the Netherlands, covering a larger proportion of the lake with 26%, and has a rafted float system design, east-west orientation, and 14.5 megawatt peak installed. And you can also see for the lake in Switzerland, we have a natural river inflow in the south, And also for the one in Germany, we have an artificial inflow generated by the gravel plant. So what we have done was we installed a monitoring setup at all the systems in a same kind to have a look at the physical impacts of the power plant, for example, on water temperature, but also on irradiance and wind flow across the system. We had a look at the chemical impact variables like dissolved oxygen, nutrient cycles, organics, and also turbidity. And last but not least, biotic variables like chlorophyll A as an indicator for primary production of phycocyanin as an indicator for toxic algae blooms. So another thing we did was we had a focus study based on the macrophytes, and therefore we first have to understand where macrophytes occur in a lake. So you can see in this visualization that most of the macrophytes are in the shore areas. So here we mostly have a dense vegetation cover, and then when depth increases and light gets lower, we have the so-called lower macrophyte limit. So this is the last point where macrophytes can grow, and after that it's not possible anymore for them to grow. So now considering floating PV, it can be a good idea to not directly place the system above the macrophytes. There are some studies indicating that we have not very good effects, especially in shallow lakes when we place the system directly over the macrophytes. So we have greenhouse gas emissions from the lake, but also decreased oxygen because of the decomposition of the macrophytes. So we are interested in to be 100% sure where should we place the system according to this shoreline distance, which can be important here. And therefore we have to figure out where this lower macrophyte limit is. So first of all, we have to look where is it even worth to take a closer look at macrophytes. So in Switzerland, we have the following situation. So in spring, all the water or most of the water is out of the reservoir and the system isn't floating anymore. And there's also not a possibility for macrophytes to grow. So this is probably not the best location to have a look on that. In the Netherlands, we had some macrophytes growing. However, if you're familiar with that, you will see that these are more of less ecological relevance here. So also maybe not the best option. So we took the one in Germany, which had a dense vegetation cover at the shores, also with quite high diversity of the macrophytes. Yeah, and we did underwater mapping via diving according to the EU Water Framework Directive to determine also the species composition, but also the lower macrophyte limit. And later, the VFD evaluation is based on habitat typical species and this lower macrophyte limit. I will tell you shortly what habitat typical species are. And last but not least, we also use the hydrodynamic modeling to simulate a restored natural state of the lake after completed gravel extraction. So here you get an impression on what habitat typical species are. So on the left side, this is something we want to have, especially in this gravel pit lakes. This is Caracea law, and these are often indicating very good water quality. And this is something we want to promote in these kind of lakes according to the Water Framework Directive. On the right-hand side, you see something we do not really want to have, which is a mass development of invasive species like waterweed. But first of all, before we go into the results of the macrophyte survey, we want to have a look at the water quality results. And you can see for the different locations some variables here. And you can see that, for example, for the water temperature in the Netherlands and in Germany, we have more or less no real impact because it's all within the measurement uncertainty. We had some impacts on dissolved oxygen. However, we are far away from critical thresholds indicated by the dashed lines. So this doesn't seem to be a problem here. We had a bit lower nitrate concentrations and also in Germany a bit lower turbidity. And this could indicate that we have an effect by mussels colonizing the floaters that are filtering the water, taking up some nutrients. And in general, this impact is low, and it's more like an indirect FPV effect. But now, when we look at the site in Switzerland, we will see, okay, this system is the smallest, but has some of the biggest impacts on water quality. And we don't think that this is a response from the system itself, so this is more caused by the surface inflow with high sediment load. You can see it especially in the turbidity values. So here we have no FPV effect, but the impact is quite large. And it's a good example how other factors can override the FPV effect itself. So now let's have a look at the macrophyte results. So what species did we found? We found 15 different species in the lake, and you can see in the plot indicated by the arrows, so red arrows are invasive species and green arrows are species with high ecological relevance and habitat-typical species that the invasive species dominate in the lake. And we only found one habitat-typical species. And by using the macrophytes as an indicator of ecological status of the lake, we can say, according to the VFD, that this lake is currently in a more insufficient ecological status. And now we want to figure out, is that caused by the floating PV power plant or by other things? And therefore, we have to look where were the macrophytes found. And you can see in the map that the macrophytes were found only in the shore areas and not below the floating PV. And you can also see indicated by the red line, which is the 40-meter distance, that the macrophytes often don't really reach this distance, so it could be even less. So to summarize, we have no direct FPV impact on the macrophytes here. However, the lake is still in an insufficient ecological status, and we want to know why. Therefore, we have to look again underwater. And you can see in the left pictures the two different depth zones. One is in the upper layer, and the other one is at this lower macrophyte limit. And for comparison, I made a picture from another lake, which is quite close to this one. And you can see that even in a higher depth, we have much more macrophytes and also this kind of Carasia lawn. So there has to be some impact on this lake. And we think that the main pressures here are the sediment-rich inflow from the gravel lake, which limits light availability for the macrophytes, and also herbivorous fish like cyprinids. So they are grazing all the macrophytes here. So this is also a very good example on how other factors can have a much more impact on the water quality or the ecological status than the floating power plant itself. But one last question remains. So what happens when the FPV system exceeds the duration of the gravel extraction? And there the hydrodynamic modeling comes into the game, and we can use this modeling to support the planning and also to simulate a natural status of the lake and support planning procedures and get a lake restoration in harmony with the FPV systems, and also to find the best suitable sites or positions for the system to be installed. To conclude it, which factors have the largest influence on water quality in preferential FPV lakes? So we found no severe effects of the systems on water quality here. Across all the systems we observed, and the influence of other pressures like inflows, outflows, or excavation can be often much higher than the FPV effect itself. And how should the current legal framework in Germany be assessed based on these results? So we think the legal regulation should be more differentiated because the other impacts are often much stronger. And also in the midterm, to have a modification on this, of these laws would be necessary to make this more site-specific and maybe also have kind of classification according to the lake type or the usage type. However, there's further research needed to better understand the environmental impact and also the long-term effects of floating PV on the water quality and the ecosystems. If you want to know more about that and if you are interested in more details, you can have a look at our newest publication, which was published this month, especially with regarding the effects of the mussels and macrophyte growth. That said, thank you very much for your attention, and also many thanks to the power plant operators who make this FP research possible and let us doing this study on their facilities. Thank you.
Okay, it's working. Thank you, Konstantin, for your presentation. I don't know if there are questions already.
Yeah, thanks for the great presentation. Very interesting, Jasper Lemmens, DNV. One of the critical things in Germany is this 40-meter distance from the shore, right? That you should stay away from, and that is impacting, of course, very much the smaller sizes of reservoirs. But from your presentation now, I see that for the bigger ones, for example, that you showed, and then again with the macrophytes are actually in that 40 meters and not a bit more to the shore maybe, but also not too much. The 40 meters is not double of that size of the macrophytes. What do you think of then those 40 meters in this case? Is it good, or should it be also case specific or so?
I think the shoreline distance isn't the right measure to restrict the installations regarding the shoreline. I think the depth is much more important. And for example, if you have quarry lakes, which have often a very steep slope, then this distance you have to keep gets very small. If you have very shallow lakes, this can be much higher. And I think therefore we have to look more on this bathymetry or morphology of the lake instead of setting fixed distances.
We have more.
Hooking on to the question about the 40 meters. I mean, from a, let's say, bureaucratic point of view, like a 40-meter distance rule is very simple to apply. Now, this one would be way more complex. Do you think there's something like a middle way for authorities to approve a certain project while not going into all the details? So let's say, as you mentioned, this depth aspect or a classification of different lakes, something which is not too complex for authorities to apply.
I think in general, can do something like this shoreline distance or depth threshold, but then you should consider like the lake type, for example. If you have these steep quarry lakes with steep slopes, then this distance or this depth can be less. And if you have different kind of lakes, it should be maybe more. Then you can set these kind of thresholds. But I think this kind of classification in the regulatory framework would be quite important to not have unnecessary restrictions on the installation.
Good afternoon. I have actually two questions related to international research. One of them is in the Netherlands, TNO has been doing quite some research, modeling, etc., about keeping vegetation under solar panels on land, how to maintain grass or certain things on this one. So also there, Shading was was a very big factor on this one, building height, etc., etc. Is this something where you cross-reference? The second part of my question is, if I look at Southeast Asia, where at this moment you see a very growing trend on combining floating PV with fish farms, shrimp farms, these kind of things, with very positive results. So they're already beyond the point of looking into the negative effects. They are exploiting at this moment the positive effects of floating PV. The different presentations so far, I'm missing this a little bit in that synergy that can be created as well. Is this something that you're also looking into, and do we have any results on that one?
Yeah. Regarding your first question, yeah, I think we can not directly cross-reference from land-based power plants to floating. However, the effects can be, yeah, in the water. Of course, we have different light availabilities compared to the land or the air. But also the water plants require some different conditions often. However,
yeah, I know, but just sorry to interrupt you for a second, but one of the key things on this one was, for example, row distance. So we have been looking now to specific plants, certain surfaces of the water surface that have been occupied. But one factor to play with, for example, is the row distance between the solar panels, for example. I know it has effect on wind and stability, etc., etc. That's a different element. But this is definitely something to look into, and I don't see row distance inside the floating PV system itself as becoming into as having a variable, which has a direct effect actually on how much light still penetrates the water. So it's more in that direction that I'm looking for. What kind of tangible elements do we have there?
Yeah, of course, you are right. You can adjust like the system design to reach the impacts in a positive way, for example, for the environment. I think this is a really important thing we have to consider. Row distance is, of course, important, maybe to let more light into the lake, maybe using glass modules or bifacial modules where also more light can get into the lake. This is, for example, something we have at the Switzerland side, even though there's not much ecology in the lake, but from a ecological perspective, this kind of system could make sense because the impact on irradiance and also on the wind flow is not that big compared to other systems that are more closed. However, you have, on an economic perspective, disadvantages maybe because less installed capacity. So you have to find this trade-off point. And I think we can also, or that's also something we consider in our research to find positive effects of floating PV. So we investigated, for example, evaporation, but also this impact on primary production, so algae growth in general. And I think this is, there are key factors there we can reach positive effects. And by adjusting the system design accordingly to the conditions we have, I think there's a good synergy between environment and economics possible at the end. So, yes.
So, Konstantin, thank you very, very much for your presentation and for your questions, for answers. Thank you. So, moving forward, we will have Sasha Risch that is going to do a presentation about the key challenges in assessing the environmental impacts of floating solar. She's advisor of freshwater ecology and water quality from Deltares. Thank you very much. The stage is yours.
Okay. Well, thank you for this opportunity to talk to you about the key challenges when you look at environmental impact of floating PV. And this presentation is all about finding the balance. And I didn't make this presentation on my own. I did make it with Emma van Veenendaal. She's here as well. And she's a PhD student in the project SURE. I will tell you a little bit more about that later. Why is the impact so important? Well, we've been talking about it quite a while this morning, and I've been here 3 years ago, and I think there was no question about biodiversity or water quality at all. So things are improving from my perspective. And why is it so important? Well, first of all, we have the regulations. With the waters in Europe, they have targets, and they are based on the Water Framework Directive. That's a directive which was in place in the year 2000, and that tells us what the quality should be of European waters for chemical and also ecological aspects. So what Constantine told you about the water vegetation. And the deadline is very close. The deadline of the water framework is 27. So that makes all the water managers quite nervous and cautious because they want to reach this deadline, of course. The other thing why we should be concerned about biodiversity and water quality is because we are in a biodiversity crisis, a decline. Last week it was Biodiversity Week. Maybe you read the papers about the problems we face, and our economy is still depending on biodiversity, so we have to be careful. Back to FPV. What does it do when you put it on water? There are 3 aspects we have to consider. First of all, it blocks the sunlight. And everything that lives underwater, or like plants and algae, they need sunlight. They make sunlight from carbon dioxide and sunlight. They make food and produce oxygen. And we all need oxygen. When you place FPV in the water, you form an artificial island. And animals can sit on it, or grow on it, or use it. So it's an artificial construction. And then the other thing is that you reduce the wind effects. And the wind effects are also for water quality very important. So we've made an infographic to make it more clear how it can affect everything in, on, and close to the water. And this shows you that it makes a shadow. You can see that very clearly. But it attracts birds. That's an observation you all made. If there are birds in the surrounding landscape, they will come to the floating panels, and they will sit on it. And they will leave their droppings, of course. But there are other birds, they are floating, there are swimming birds, and they might be repelled by it because they don't see so much anymore. But we don't have the observations of that, we lack the data. And fish, well, every fisherman knows that when you put something in the water, a floating object, fish will come. There will be, it's attractive for fish. It's a very old knowledge. So FPV also attracts fish. When you walk around, you see all these small fish, but we don't have the quantitative data yet. We don't know if the stocks will increase, but it will attract. And the other thing, which is a research question, is the electromagnetic effect of the cables. We don't know much about it. There's a lot of research on marine environments, so maybe we will learn a little bit about that in the future. I already talked to you about the reduction of light. I think that's the most important factor of floating PV. It might change the water temperature, it might change evaporation rates, and light availability is needed by everything or the green things that grow under the floating PV. That's algae and underwater vegetation. And then maybe when you think about algae, you think, oh, that's a good thing. We don't want these algae. But you have toxic algae, and of course you don't want them. You don't want to give them sunlight so they can grow. But you also have very healthy algae, which are a food source for the rest of the food web. So you do want to have them. Well, adding a new substrate in the water, an artificial island. Constantine showed you some pictures of mussels growing on anchor lines and anchors and the floaters, of course. That will happen as soon as you throw something in the water, things start growing on it. And that might be negative, can attract invasive species, but it's also a new food source could be a new food source for fish. And then changes in stratification. Stratification is an important phenomenon in deeper lakes, about 10 meters deep, which occurs in summer. You have a warmer layer above the water, and it's important for the biological processes. And it might change because of the temperature and wind effects changing. Well, what I want to show you now is two monitoring sites with long-term monitoring at FPV plants. And part of it is published in a book which is recently published by Marco Rosa Klot, and we wrote a chapter together with Fraunhofer, ISE, on the environmental impact. But the rest of the data, which I'm going to show you, will be analyzed by Emma within the project SURE. And so this is a preview of the data. A little bit more about SURE. SURE is a European Horizon research project, and it has several work packages on reliability and efficiency, and also a work package on sustainability. And there, in this work package, we work together also with Fraunhofer ISE on getting more knowledge on the ecosystem and the impact. And we will hope to end with an impact guideline for you. There's a lot of different organizations doing the research in this project. They're all here. The coordinator is the Institute for Energy Technology in Norway, and the project coordinator is here as well. It's Josephine is in the back, so if you have questions about the other work packages, you should go to her. Well, back to the data. We have two lakes, and they are Dutch lakes, and they have unpronounceable names, so I call them Lake A and B. And they're both in the Netherlands. They have, we installed sensors, which are quite expensive, so we could not do all the lakes in the Netherlands, but we would like to, but the sensors are quite expensive. We put a sensor in the open water and a sensor under the floating PV. And they are measuring, these sensors are measuring the water quality at 1 meter below the surface. So the orange dot, all the orange lines are covered with FPV, and the open water is the blue dot. At Lake A, we were lucky to install these sensors 3 years ago, so we have a very long-term record of hourly measurements. And at Lake B, we have monthly measurements of someone going there and doing the measurements. But from the start of this year, we also installed the sensors. But we don't have the data yet. It's still in progress. The coverage rates are both very high. They are 41% and 48%. So they are commercial plans. And that's what our wish was, to measure at real, not pilot sites, but at real large-scale sites. And the hydrology of these two lakes is different. That means that Lake A is isolated, it's fed by groundwater and rainwater and doesn't get an inflow. But Lake B, it is. It has 2 inlets and an outlet, so that the water is going through the lake. And they're both sandpit lakes. And Bijwaak GroenLeven, they were so nice to give us permission to do these measurements, and then we are cooperating with them. They are learning from our measurements as well, and we can have access in these parks. And Emma is doing some more field work this year to get more measurements in Lake A. This is the first graph I want to show you. It's against time. So the horizontal axis is time. So you start in June 22 and until June 25. and its temperature, the vertical x, and you see, so this is measured as water temperature, 1 meter below the water surface. It doesn't look like hourly data. Normally it looks like this, but it's smoothened. It's statistical to make it easier for you to read. And the orange line is under the FPV and the blue line is in the open water. And you see hardly any difference in water temperature, but there is a slight difference. Well, first of all, you see the seasons very clearly. You see the winter very low and high in the summer. And then there is a slight difference. Under the FPV is a little bit lower than in the open water. Same graph, 22 to 25 in the time, but now dissolved oxygen. And the oxygen is produced by these algae in the water. And now you see there's a difference in Lake A. The difference is that under the FPV it's always a little bit lower than in the open water. And we think that's because the algae get less light and they produce less oxygen. If that's bad, if it's good or not, we didn't analyze that, but this is the fact for Lake A. Then light, this is the obvious one. The blue one is again the open water, receives lots of light at 1 meter depth, and the orange dots are under the FPV, there's less light. So that's the obvious measurements. This is chlorophyll A, that's an indicator of photosynthesis, activity of the algae. And there you see that the story is not very clear, but you see there's a difference between blue and orange, and blue is higher in most of the summers because chlorophyll photosynthesis takes place in the summer, in the warmer times. So on the left you see again Lake A and then oxygen, because now I want to compare it with Lake B to see if we see the same trend, the lower oxygen, the lower photosynthesis activity. And then you see Lake B is a completely different story, it's a different story. You don't see this lower oxygen appearing. You see it's almost the same and sometimes even higher. It's a completely different trend. So we were somehow disappointed by this comparison. But then luckily we could explain it, because what I told you in the beginning, Lake B was completely different hydrologically speaking. So there was an inlet and an outlet. So the water is flowing through. And Lake A is an isolated lake, so fed by groundwater very slowly. And a little bit of rainwater. So now I would like to summarize lessons learned. And on purpose, I didn't call it conclusions, because I leave the conclusions to Emma, who is going to do the PhD on this data and is using the data as well for model validation. So we can validate the models. At Deltares, we work with 3D models. And because this is a new technique, we don't have ground truth, so to speak. So we need this monitoring data for validation. So it's based on ongoing research, and it's partly data and partly just observations. Well, the first observation agrees very much about what Konstantin said. Please avoid the shallow zone, because the shallow zones, the shorelines, are very important for biodiversity. There's a lot of insects growing there, there's water plants. It's a very vulnerable but important, valuable zone. And 40 meters might be sometimes 40 meters, but sometimes just 5 meters. It depends on the depth. So you have to protect the shallow zone because they needs light to grow, sunlight. Well, it's an attractive resting place. That's something you can say. Maybe for you it's not so positive, but it's for me it is, because it makes it very easy to observe the birds. Fish is attracted to the floating objects, but that's something we already knew. You see it at docks, you see it at all floating objects. We don't know if it increased stocks. We see growth on FPV systems, and we see also reduction of wind effects. And you see the waves on the water, and then in the lee side of the FPV, you see less waves. I didn't measure it, but you can see it. And for the Netherlands, this might be very important because we always have problems with protecting shorelines. We want to build bigger dikes, so we need higher and stronger dikes. But maybe if the FPV system reduces wave energy for the dikes, this might be a positive impact. Well, the data shows you very clearly the light is reduced, small temperature differences, and we're still measuring. So the sensors are still there at Lake A and B, so we will have a longer data set. The responses are different, the responses of these two lakes, and it depends on the lake characteristics. So I have to maybe disappoint you, there's going to be no number for all lakes. We have to, it will stay site-specific, the coverage rate and the distance from the shoreline. And I think we can say, well, if a lake is very isolated, the effects will be stronger. And I would like to end with some recommendations. And the first recommendation is for myself, and I didn't write it down. I didn't write it down on the slide, but I just thought about it an hour ago, is that we have to cooperate very closely with, well, we already cooperate with Fraunhofer, but there's a lot of research going on. And I think we should, well, put the data together and build a synthesis from all these different data, because the data is sparse, it's quite expensive to get the data, the long-term data as well. But what I did write down is, that's a recommendation for you, start monitoring. It was mentioned this morning, because then that's the only way to convince the government that what is happening, and maybe you can mitigate if it's going wrong. And then monitoring is not easy. And that's why we developed within SURE, we developed a monitoring protocol, and that will be published this summer. And the other recommendation is also for you that I think it's important when you start designing to involve an expert on hydrology or ecology and design together to look at the site, make a quick scan, what's important here, where's the vulnerable areas and how much coverage can be reached here. What's the balance between performance and protecting the environment? And the last one is, well, you can use water quality models. There are different, David used MyLake, and Konstantin used GLM. We use 3D. There are different models, but they can be all used for different scenarios to forecast the effects. And that was the last slide. I thank you for your attention.
Thank you, Sasha, for the presentation. I don't know if there are any questions from the audience. If there isn't, I will have one at least. Okay, so I'll move forward. An interesting question that I believe it's important to have is, from the experience that you have, and because you started to make measurements earlier in one lake and later on the other, what do you think it would be the minimum time that is required to do measurements, to take an assessment of what would be the conditions? That is the first part of the question. The second part is, when we are establishing an environmental impact, we have to have a base for comparison. And the base for comparison is, where is that base? Okay, so we are doing measurements in a system that was placed somewhere. What is the base for comparison?
Yeah.
20 years ago, 10 years ago, 5 years ago, or nothing ago?
Nothing ago. Well, the first part of your question is how long should you measure? Well, I think at least a year. But we see some difference we have now at Lake A 3 years of measurements, and we see already differences in summer 2 and 3. So maybe we should measure longer, but that will be part of our conclusions, I think. And for reference sites, well, the ideal situation is when you have 2 lakes next to each other, which are completely comparable, and one you put FPV and the other one is a reference. But that's a very difficult situation to find. Within SURE, we found one in Italy at the pilot site. We have 2 lakes, and one is the reference and one is the impacted site. So that's easy to compare. But that's very rare. So again, you have to look at the site and see, well, this is representative for open water, not impacted, and then the other point is under the floating PV.
Thank you very much, Sasha. No more questions. Thank you very much.
Oh, I...
There's one good.
I'm sorry.
No. For your Lake B with the inflow and the outflow, do you know the flush rate for the lake?
I know, but I wrote it down, but I cannot reproduce it. But I'll.
Do you think that's going to be? Do you think just the presence of an inflow and the outflow explains its comparably smaller change, or do you think the flush rate would be important for if, like, you had a very big lake with a very low flush rate?
I think the flush rate is very important for this lake, and it's significant. That's what. Yeah.
And we have another one over there.
Thank you. Just one more question regarding the birds issue. Of course, as a developer, it's not so fun to have birds sitting on the solar panels, especially the droppings. On the other hand, from permitting issues, we sometimes get the question to construct also, when we develop a floating PV, to construct also a bird nesting island, an artificial island. Do you have any experience with that? And is that in one way or another really effective? Or?
Well, I know that in the Netherlands you have a lot of artificial islands for birds, so not close to FPV, but everything you have in the water will attract birds. So if you have like a compensation next to your FPV island for birds, then you will attract more birds. And in the first place, they were not nesting there. They are nesting on the shorelines. So as long as you have not disrupted the shorelines, they can still build their nest. But they will sit on the FPV because they like to sit there. And they have a nice view, they have warm feet. So in fact, I think it's something you have to live with. Because you don't want to chase them away, you're not an airport. And I think cleaning in spring is the best thing you can do, but building an island, an artificial island extra for the birds will attract only more birds and more droppings.
Okay, Sasha, thank you very, very much. So, and now we'll continue with Pablo Briggs, that he's going to present something about socioeconomic and environmental considerations of offshore solar through the lifetime. Pablo is energy solutions analyst from DMEC. Okay, Pablo, the floor is yours. Thank you.
Hi, and thanks everyone. I won't keep you from your lunch, so I will try to get through this as quickly as possible. So what I want to talk about today is specifically the considerations, so environmental and socioeconomic considerations for offshore solar, so taking this out at sea. And for those who aren't familiar with the Dutch Marine Energy Centre, we're an accelerator and knowledge centre for offshore renewable energy and sustainability innovations. How do we do this and why do we call ourselves this? So working directly with developers, so advancing their technologies and business cases. We help them develop in the market, so supporting the use cases across their value chain, either by developing projects or helping them find investments. We do our own research, so advancing the scientific knowledge base, and by developing our own tools, which I will dive into a little bit. And then we also help advise policymakers on best practices in the industry. And we do this with over 145 innovative technology companies. We have raised over 167 million in public and private investments, and our ever-growing network of collaboration partners. And just quickly reminding you of what I'll be talking about today. So starting with LCA, so life cycle analysis specific to offshore solar systems. So how we can decarbonize the systems, their impact on marine ecosystems, the economic viability, so comparing that with other technologies, and opportunities for scaling up the technologies with other systems like wind farms or, for example, hydrogen production. So going quickly, and forgive me for the text, I promise it goes away quickly, but introducing offshore solar has very unique socioeconomic and environmental stakes. Namely, you are creating new coastal economies. So offshore solar creates new value chains in areas. So for example, in countries with limited land use or limited land space, like the Netherlands and Singapore, this has a lot of potential. Multi-use potential, so integrating offshore solar with another technology like offshore wind enables for synergies, also with aquaculture, offshore wind, hydrogen, which unlocks new business models and makes for more effective use of marine space. And on the right, the graph, what I really want to highlight there is the complementarity of production profiles between offshore wind and solar. So you can see that throughout the year you have varying production profiles. So in the summer months we have a little bit less wind, and that's when the sun shines even more. So an effective use and a mix of those two technologies creates a more steady production profile throughout the year. And finally, this everlasting balance between climate mitigation and marine biodiversity. So obviously we want to try and decarbonize our energy, but how do we do this without having too great of an impact on the marine ecosystem? And one way which we can track our emissions is through life cycle analysis. So for those not familiar, life cycle analysis is just tracking a factor like your greenhouse gas emissions for a project or a process or a structure like the ones we have here. And one of the many exercises that we've done at DMEC is trying to model the emissions that an offshore solar project would have. And we did this by creating two kind of concept structures. So we have the high above sea and the just above sea. And these are based on trends that we see in industry. So looking at how developers are advancing their technologies, and these are systems made for the future. So these are optimized. So we want these to be technology agnostic. We're not trying to directly compare this to technologies that exist now. We are mostly doing this for demonstration purposes. But aside from just creating your concept structures, there are a lot of considerations, namely how you are getting these structures out into the ocean. So what kind of vessels are used, what kind of anchoring and mooring you need. On the right, you have some maintenancing. So how are you cleaning your panels? How are you servicing the electrical equipment? And then also, obviously, the balance of plant. So all of your central inverters, your mooring lines, your underwater cables, your dynamic cabling, there's a whole load of systems. And then life cycle analysis, you need to kind of create a box around what you want to analyze. And in our specific case, we wanted to see what it would look like to bring a 15 megawatt system. So not that big for onshore, but for offshore, that's never been done before. and we wanted to see what that would look like. And some quick results. I don't want to highlight any differences between the developers or the structures. What I really want to show here is the impact that each of these considerations has on your total emissions. So this shows for all the different structures, and we have variations between aluminium and steel constructions. And we can see that fuel consumption at the top has a huge impact. So how often you are going to and from your structures offshore will obviously add up over the years. So that's one way to reduce the emissions. The actual solar panels and balance of system plays another big part, but those are mostly overshadowed by the materials and structures that are used to hold up the panels. So that's your steel or metal or aluminium, and then your HDPE for the floaters. And that brings us on to the marine ecosystem itself. So how will offshore solar systems impact local ecosystems? So just to name a few, there is obviously shading, which has been spoken a few times today, changes in water dynamics, obviously, biofouling, so monitoring what kind of species are active or are stationary on the platforms. You create also an artificial reef effect underneath. You are cooling the water column, and then obviously providing a resting platform for birds and mammals. So how do we mitigate all of this? So in, for example, the design phase, you want to have modular systems that can have adapted light gaps. Your material choice is very important at that stage. So you want materials that have a low leachability, so that aren't going to harm the environment that they're in for their life cycle. In the installation phase, it's important to select your site carefully, so to not impact any sensitive habitats like reefs. And you want to use low impact mooring as well wherever possible. In the operation phase, it's important to monitor the species that are present on your structure, and if possible, create nature-inclusive design, so habitats for these native species that you want to encourage, that you want to have there. Like, for example, in the North Sea, we have guillemots, which are a species of bird that are endangered, and there are ways that we can help them find more suitable resting areas. And finally, in decommissioning, and this is something that is very difficult to plan for, but material recovery at the end, that's really important. So making sure that we remove all the anchors and cables that are used throughout, and then also we think it's important to monitor the space that we've been using for the past 20, 30 years, and making sure that the impact that these, for example, a solar plant has is not immediately deteriorating. And by minimizing risks like biofouling, material degradation, as early as possible in the design phase, we can reduce maintenance costs, and that can also help with insurance premiums. And all of this will directly influence the LCOE. So this is a pretty stark jump from environmental considerations to the LCOE. But at DMEC, we also model what we think capacities will look like and what LCOEs will look like based on two of our models, so a growth curve model and a doubling time method. And these both use a learning rate of 17%. And this is to see how we can make the technology cost effective and when we expect to see larger rollouts of the technology. So as of 2024, we found that there were 2.4 megawatts of installed global offshore solar capacity, giving us an approximate LCOE of about 202 euros per megawatt hour. And our forecast is that in 2025, this will increase to about 3 megawatts, reducing the LCOE further, and that by 2030, we hope to see 40 megawatts of installed capacity, and this will give us an approximate LCOE of 100 to 120 megawatt hours. Comparing this to other existing technologies, for offshore wind, the range of LCOEs is about 60 to 100 euros per megawatt hour, And onshore PV, which is a lot more cost effective, is about 30 to 60. But really we're aiming to get it within range of offshore wind. And some ways that we can reduce the costs of CapEx and OpEx throughout, obviously choosing the right materials early on, so make sure that they are durable and cost effective. The mooring and anchoring, obviously it varies a lot depending on where you are installing your plants and has an impact on environmental constraints, so planning this as early as possible. Your electrical infrastructure, so offshore substations, dynamic cabling, all of these are very expensive, but if you are able to co-locate with, for example, offshore wind, you can share some of those costs. In installation and logistics, so how are you getting your structures out at sea? You need vessels. These are in high demand, and obviously you also need favorable weather windows. So a careful balance of that. Operation and maintenance costs are another big one throughout its life cycle. You want to reduce the amount of times that you need to service your structure, so you want to make it as sturdy as possible. And finally, financing and insurance. This is a big issue for offshore projects. So these are very novel systems, so this leads to very high risk premiums and insurance premiums. But we hope that by standardizing these technologies, we can have an impact on that. And one thing I've briefly touched upon throughout this presentation is multi-use. And we really think that this is a great opportunity for upscaling and getting to economies of scale within offshore solar. So in this example, I want to talk about co-location with wind and why the benefits, what are the benefits that it has. Obviously, if you have an existing wind farm, there's an opportunity to retrofit your offshore solar, and this helps early demonstrators de-risk their project, making it a lot more bankable, as they don't need to rely as much on shelling out for cabling or for vessels that are already used on site. And these sites are already industrialized, so there's experience, there's a local workforce, and there's likely to be less public opposition as well. We want to see intersector collaboration. There's experience there, and we hope to bridge that across existing offshore wind and the growing offshore solar as well. So boosting local supply chains, and obviously this is all in alignment with broader EU strategies. And what are some of the direct socio-economic benefits that we see with offshore solar? So obviously we have shared infrastructure potential. So being able to share the grid connections, like I mentioned, the anchoring systems, vessels, and this directly reduces CapEx and OpEx. We want to see an efficient use of maritime space. So if there's an existing wind farm, then we want to maximize the output per square kilometer. So these areas are already dedicated to energy production, so why not make them more energy efficient? And also, this is very critical in dense exclusive economic zones like the North Sea and the South China Sea. So these are definitely things that need to be looked at. Although I mentioned job creation quickly, so we want to have the diverse workforce. And finally, this is a big topic at the moment, is energy security. So if we're able to balance the production throughout the year, we can have a more secure power supply, and mixing that with other technologies, including hydrogen, storage, or ammonia, unleashes even more potential. And finally, what is kind of our vision for this sustainable expansion of offshore solar? So we really believe that establishing international standards is one of the biggest hurdles, and we are directly involved in the development of IEC 62548-3. It has a very catchy name, but it's one of the IEC commissions working on regulating floating solar standards. And we think that that will have a direct impact on insurance premiums and investor confidence, which also needs to be done by the developers themselves. So getting those small pilot projects out proving the survivability and the reliability of these technologies is crucial as well, especially in difficult marine conditions. Obviously, driving costs down through scale. So we want to get these projects as big as possible, as early as possible, to bring that LCOE down and make it cost competitive with other existing technologies. And one easy way to do that is obviously to align with offshore wind infrastructure. So leveraging existing assets and using those. And our role in all of this is really to support industry alignment through our standardization efforts and facilitating collaboration across Europe through our network and projects. And if you have any more questions about DMEC or offshore solar in general, I'd be happy to reach out. Thank you.
Thank you, Pablo, for your excellent presentation. I don't know if there are any questions from the audience. No? Okay, I believe it's almost lunchtime and that's the problem. Okay, so Pablo, thank you very, very much. So, thank you very much everybody for this morning, and we have now our lunch break. We are going to be here again on 2:20, please. Don't be late because we have other presentations and we are going to have a big afternoon anyway. So have a good lunchtime and we'll be back here to this room at 2:20, okay? Thank you very much.
Det var inte den.
As you want, whenever you want. Speak with Malaysia, and then after the beginning of the afternoon, we talk a little bit, or even there's a coffee right there. Yeah, there is the one at 4 o'clock. At 4 o'clock, we can try to announce what is going to be next. No problem at all. Really.
All right, let's
Yeah.
Tady to proti světlo tě nesere?
Hello, everybody. Shall we start? To be on time. Okay, so hope you enjoyed your lunch and you had a good time to networking also. It's also important. So I'm going to invite now Wilma Ehrenstein to come to the stage to take the floor. She's expert on renewable energy from Reenergize Consultancy, and she's going to present model to assess impact of floating solar based on data collected at the third floating pilot constructions. Wilma, the floor is yours. Thank you very much.
Well, good afternoon, everyone. Glad to see you made it back after lunch, and I hope you're not suffering from after lunch dip, so I'll try to make sure you stay engaged. It's really my pleasure to talk to you about a model that we have developed to predict the impact of floating solar on water quality, where the model is based on the data that we have collected at our pilot systems. Yeah, we've already discussed it a bit this morning, like Max gave a good presentation, Kim, sorry, on the regulations. I've shown you examples here of 3 European countries where there are actually regulations on which coverage and shore distances are required. So in Italy, you can place 50 to 70% lake coverage, and you need to stay 10 meters from the shoreline. But in Germany, it's only 15% coverage with 40 meters from the shore. So this is already restricting projects on smaller lake locations. And in Spain, it can even be more strict if it's like a 5% coverage on non-eutrophic sites and 15% coverage for eutrophic state, where eutrophic means with, it's high in nutrient levels. Of course, even if there are no regulations, you still need to obtain a permit. And in the Netherlands, for instance, some of the water authorities can grant a so-called conditional permit. So you obtain a permit, but you're also required to monitor certain parameters on the water quality. And if there is a deterioration of some of these parameters, you are obliged to take measures. And of course, as a project developer, if you have to adapt your system a few years after you have installed it, that is not going to help your business case at all. Thirdly, I think also as a green energy sector, we also have a responsibility that the systems that we install do not cause ecological damage. Yeah, it's already been discussed a bit this morning, but it's important to know what floating solar does, how it impacts the water quality. And it's very important to realize that a water body is an ecosystem. And an ecosystem is always a balance of many parameters and processes. And when we place floating solar panels on the water, we can change some of these processes and change the balance. And I think one of the most important changes is, of course, the light availability, because light is needed for photosynthesis, and that in turn also changes oxygen and CO2 concentrations in the water. There can also be an impact on nutrient levels, especially nitrogen and phosphor. And also plant growth and decay can be influenced by the presence of solar panels, and this in turn has an influence on CH4 concentration in the water. Fish behavior can be different. If the oxygen levels are too low, fish will move away from solar panels, but they can also use it as a place for shelter. So these are also two different processes you have to take into account. And the water temperature can also be affected. And then the question is, of course, how exactly are these processes going to be changed when we place floating solar on the water? And we wanted to set up like a pragmatic model that can be used as a so-called quick scan by water authorities or by project developers, so that you can assess what is possible at a certain location, because then you can also assess the financial feasibility and whether you want to proceed with your project or not. So you can use it before you start putting a lot of effort into detailed system design, because that's something you still need to do, of course. Our model doesn't do that, but at least you will know whether it's worthwhile or not to do so. And we decided to use the program PC Lake Plus, which is like a box model, which is already used by many water managers, at least in the Netherlands. It's a model that uses a set of equations to model the processes which are occurring in the lake. So some of the processes I just mentioned in the previous slide, such as nutrient cycling, phytoplankton growth, or grazing, etc. And it considers factors like nutrient concentration, like phosphorus and nitrogen, light penetration, but also water cycling time. And we'll see that that is also important. And it also takes into account stratification. So that means if you have a deeper, colder layer which does not thermally mix with the surface layer. So then this model PC Lake Plus can model when a lake switches from a clear to a turbid state. And let's say in the normal model, when no solar panels are present, this is largely driven by the input of nutrients to the ecosystem. But if you place solar panels, it can then also compute the effect of the light reduction and the mixing of all components. So then it's possible to assess if floating solar is possible at a certain location, and if so, at which coverage. So just a short visualization of the PC Lake model. So this is just PC Lake without PV. So it's a two-layer. So we have the deeper layer, which does not thermally mix with the surface layer. All the green boxes are processes caused by organisms. The brownish colors is all organic and non-organic matter. And the orange box is nutrients. And then, of course, we also have oxygen levels and the interaction with air. And the model then computes how these processes interact with each other. So what we've done is adapted this model for the presence of floating solar. And we did this by adding 2 additional boxes. So basically, we've assumed that the lake has a shallow region around the shore. So in the shallow region, there's also plants growing. Then there is a deep part without PV and a deep part with PV systems on top of it. And then we are able to increase the PV part as a percentage of coverage, and basically the deep part is then reduced. The shallow part remains the same. And the model then computes how the reduced light affects the processes in the deep part with PV, and how these layers are mixing with the deep part without PV and with the surface layer. But then, of course, we need to know how can we calculate how the processes are changing. And in order to do that, we've also taken a lot of measurements for 3 years at our pilot setups. So I'll give you a very short introduction of the project that we had in order to conduct all these measurements, which setups were used, which measurements were performed. Some of the measurements result, because of time I cannot show all the details, but both Sven, who conducted a lot of the measurements, and myself will be here for the remainder of today and tomorrow. So if you have questions, please feel free to come to us and talk about it. And then, of course, show the model results, how we can apply the model, and some conclusions. So the project is called DRIVER. It was a Dutch research project, which was funded by the Dutch Ministry of Economic Affairs. And the main aim was to measure the impact on water quality for 3 different setups for a period of 3 years, and then also to set up a model to predict the impact for large-scale floating systems. And the project ran from April 2020 till the end of last year, so it's recently finished. And it was executed by the project partners EasyFix Solar, which is a Dutch company supplying the constructions, NEO, which is the Dutch Research Institute for Ecology. I participated through my company, Renergize Consultancy, with project management and data analysis. ROM3D is a landscape architectural office who conducted visualizations. And the University of Wageningen has a research farm called De Marke, and they provided the test location. So for the system setup, we used a system consisting of floaters plus metal structure. And EasyFix Solar is a company which is specialized in tailor-made constructions. So they have the ability to adjust distance between the panels, height of panels, and inclination angle. So this way we were able to build 3 different setups with 3 different levels of openness to the water. So we could study also the effect of light penetration to the water. So the first system we built was what we call an east-west system, which was open. So the distance between the panels was 0.5 meter. The second one was an east-west system, where the panels were placed as closely as possible with only a few centimeters gap between the panels. And the third system was a south-facing system, also open, with 0.5 meter distance between the panels. And they were installed at a former sand mining location called the Markerplas, which is in the east of the Netherlands. Then for a period of 3 years, NEO conducted measurements on the concentration of oxygen level, CO2, CH4, water temperature, light availability below the panels, nutrient levels, and carbon balance. So that's like plant growth and decay. And for 1 year, we also measured the panel temperature and the air temperature below the panels. I'll just quickly start with the last ones and then continue with all the ecological aspects. So if we look at the panel temperatures, we found that the average panel temperature of the closed field was about 1 degree higher than for an open system, which has to do, of course, with wind effects. But this is averaged over an entire year. And if we look at a sunny day, then the panel temperature of the closed system is about 2.3 degrees higher. So if you have a difference between 1 and 2.3 degrees in panel temperature, that means that on an annual yield effect is between 0.3 and 0.8% in favor of the more open systems. Then we also found interesting effects on the air temperature, because this remains higher at night than the panel temperatures. So what you see in the lines is the closed lines are the panel temperatures, and the dotted line is the air temperature below the panels. Of course, during the day, the panel temperature is higher, but during the night, the air temperature remains higher than the panel temperature by about 2 degrees. And we think that this also helps to explain that there is not a very strong effect on water temperature, what Sasha also showed before lunch. We did not measure a difference in water temperature, but of course our systems were relatively small compared to the area of the water body. But also for larger scale systems, there's not a huge difference measured in water temperature. For instance, at NPU Singapore, they also found that the water temperature was only a very small difference compared to the reference. And they also explained this by a balance of, let's say, there is less direct light coming in the water, which reduces the water temperature, but the panels also radiate heat towards the water, and these two processes balance each other. And then we've measured the light reduction below the panels, and we really see a very strong reduction at the closed system of around 80%. In other words, only 20% of the incoming light is reaching the water. And for the two open systems, the effects were more or less similar, with a reduction around 45%. And then we looked at the oxygen saturation levels in the water. And we found that below the solar panels, the oxygen saturation is always lower than for the control. But interestingly enough, we also found that the east-west open system had the lowest oxygen saturation, and this was not expected. But so we did some more research, and we believe that the reason is because this one was located in the curve of the lake. So there was a lot of accumulation of leaves at that point. And when leaves are rotting, they also consume oxygen. So if you have larger systems, we think it's always important to measure at multiple locations and not just at one point. And also to understand the processes which are going on in the lake, we also looked at the processes which produce oxygen, such as photosynthesis, and there are processes which consume oxygen, like grazing fish or rotting of organic material. And we see that at the control, the production of oxygen is always higher than below the solar panels, which makes sense because you have more light availability and hence more photosynthesis. But the oxygen, it's called respiration, the consumption of oxygen is also higher at that location. So these parameters we used as input for our model. And before you can run the model properly, you also need to know about your water flow and nutrient levels. So we did a detailed water flow analysis. And I think it's also very important to realize that the location where we had our pilot systems is also not connected to other waterways, a bit similar to Sasha's case A that she presented this morning. And there's also a strong influence from the local drinking water company, because they extract groundwater for drinking water. So we have quite high fluctuations in the groundwater level. And also because the system is not connected to other waterways, the nutrient concentration was already high, particularly nitrogen. And that's because in the Netherlands we have relatively high levels of nitrogen in the groundwater from agriculture. And because the system was already high in nutrients, it was already a bit close to a turbid state. So what you see where it is at the start, that's the relative nutrient level of 1. But if you only increase the nutrient levels a little bit, you can already move the system to so-called a turbid state. So this is actually, I would call it a fragile ecosystem. So we've used this input parameters plus the changes in oxygen process parameter that I previously showed you. And then we put this in our model, and then we slowly increase the PV coverage from 0 to 60%. So what we see, for instance, if you look at the chlorophyll A levels in the shallow part, we see that there is a strong spike if you go to higher PV coverages, and this spike occurs at higher coverage percentage for the more open systems. And this also makes sense because the closed systems reduce the light more, and so it has a stronger influence on photosynthesis and hence also on nutrient levels, because photosynthesis is also driven by nutrients. Connected to the fact that there is more chlorophyll A in the shallow part, we also see that the plant growth is then reducing in the shallow part. And again, the reduction happens at a lower PV coverage for the closed system, but this is also related to what happens to the chlorophyll concentration. And we also calculated the oxygen levels in the deeper parts of the lake, both the deep part with and without PV. And also here we see that the oxygen levels decrease if you increase the PV coverage of the lake, and the drop happens earlier for the closed system than for the more open system, which makes sense because there is less light. From the water directive, the oxygen level has to be at least 6 micrograms per liter. So you can see if you want to stay above that, then your PV coverage should not exceed 20%. But that is for this specific lake, where there is no refreshment of water from other waterways, and this lake was already in a fragile state with relatively high nutrient levels. So if you go to another location, which is located to connected to other waterways and has lower nutrient levels, you can of course go to very different PV coverage ratios, but with this model we can relatively quickly assess it. So that brings me to the applicability and conclusions. We have a PEC Lake Plus model available, which is suitable for a quick scan, and we see that even small PV systems already impact ecosystem processes. But the good news is that floating solar is safely possible, but the exact coverage is location dependent, and we saw it's also dependent on the design and openness of your system. And it's strongly dependent on the water flows and nutrient levels at the start. And it's my personal opinion that instead of a fixed percentage in legislation, we should go to a quick scan per location and create the flexibility that each location deserves. And measurements are very important. We've already seen a few ones this morning. The quick chat with David already also. So I think it's really good if we create also an ecosystem of data and impact on water quality. So if you have data, please contact us so we can see what we can do together. Thank you very much for your attention.
Thank you, Vilma, for your presentation. I don't know if there are any questions from the audience. If not, I will have one anyway. And my question would be, Vilma, how do you think it would be difficult or not to assess different ecosystems? What do I mean by that? What the reality of any ecosystem in the Netherlands is different, for example, than south of Portugal or south of Spain. So the idea is, do you feel that it is possible to change the parameterization of Lake Plus to adjust to different kind of ecosystems? Difficult, not so difficult? What is your feeling?
Yeah, that's a very good question. Because we have assessed how the processes change when you change the light availability. And what you need to do for each location is to do an analysis of your water flows, so you know your water balance. the nutrient levels, and then we can relatively easily use that as input for the model.
Okay, it was my question. If there is no other question from the audience, Vilma, thank you very, very much. So, and we will continue now with Theophile Bresson, Technical Director of Heliorec, and that is going to reduce risks, eliminating unknowns. How will digital twins support for new area of floating PV modeling? The floor is yours. Thank you very much.
Okay, good morning, good afternoon to all the person I didn't met yet. So today I want to talk about a critical evolution in how we approach floating PV. The integration of digital twin technology to de-risk projects and unlock the full potential of this rapidly growing sector. Heliorec is a French company specialized in floating solar technology, developed in nearshore and inshore application, but more focusing in nearshore. We're a B Corp company with the AIP level 1, and we're ongoing to get AIP level 2 for our product. Okay, so this is a quite heavy agenda, I guess, but it's going to be quicker. But okay, so we're gonna go into the FPV that faces unique challenges, focusing also on marine applications, and those are to be related to environmental stressors. And not only stressors can act at once, but then can combine together. So the current risk assessments with our methodology is not sufficient yet to understand fully what's ongoing. And that's where digital twins can really help us with this. So what are the benefits on design? So on different steps, design, operation and maintenance, and also environmental stewardship, as we've seen it's a scope right now. And we're gonna see also that there are things to be learned from similar applications. And also how Heliorec is, what's the vision of Heliorec into that. So floating FPV, as we've seen, is no longer a niche. I guess it's more like a revolution, and we're here to see that, to prove that. We're seeing explosive growth and ambitious projections. This expansion brings immense promise, especially in land-scarce regions. However, as we push the boundaries into a new area, larger, more complex, and longer-lasting projects, we face significant challenges. Higher initial cost, intricate engineering for dynamic conditions, and unique operational hurdles. A key issue in the relative scarcity of long-term data, which introduce uncertainty. And this is where advanced modeling comes into account. I don't know how to get down the notes. Sorry about that one. Okay. Anyway, so I think it was the end of it. Oh, thank you very much. Yes, so a key issue is the relative scarcity of long-term data. We don't really have enough data, as you said just before, so it'll be very important to get that, like a database onto that. And also, I guess that those data doesn't come from anywhere. So there's to be a really big research and development on measurements tools, things that we can install quite as a standard to measure daylights, turbidity, like main parameters that can not grieve like CapEx as much as today. So what are the environmental stressors? FPV plants exist in a uniquely demanded environment, facing a gauntlet of stressors. Mechanically, they battle constant waves for marine applications, current forces, wind, and changing water levels. So here you can see our breast plant enduring one of the storm that hit it in November 2024. But not only mechanically, thermally also, there's a delicate balance between solar heating and the potential cooling effect of the water. So we've seen that also, what's the good height between floating solar and the sea level. And also, let's not forget about chemicals and biology. So biofouling, saltwater corrosion and biofouling are major enemies. Let's not take about enemies, but let's say regarding the survivability of the structure, especially as we move to more diverse water bodies. So these stressors don't act in isolation, as I've said before. They're combined, and let's see now, how can they combine? The stressor don't just cause isolated problems. They create a cascade of interconnected risks. So this is an example of case scenario that can happen and that has to be taken into account while designing. So I think it's explained enough. So a failure in the mooring line system, our lifeline, can be catastrophic. Float degradation and panel damage are also significant concerns. Performance can be steadily eroded by soiling, salt, and accelerated panel degradations. Electrical losses and safety hazard are amplified by the wet environment, as you know, and all this translated to increased O&M burdens. Difficult access, so the footpath needs to be well designed also for more frequent interventions and especially costly procedures. So all this again related to digital twin that has to be a part of the design. It's not about just a big failure, on one case, like the weakest point. It's also, as it can be said, the death by 1,000 cuts. So slower degradation from one part and slower degradation on another side, and chemicals and wind acting together as resulting into the failure. And this is very hard to design because, in fact, we always consider one critical, like wind, let's study wind, wave, let's study wave. But when it comes to bring that together, then there have to be like something to help us more than formulas. Datas are critical. So, all this translated to increased O&M burdens, difficult access, more frequent interventions, and especially costly procedure. It's not just about, So the industry has, of course, developed robust methodology for risk assessments, site studies, material testing, thanks to DNV, thanks to BV, thanks to all the oil and gas and the wind industry. We came up with really good work and valuable material. These are essentials, providing a baseline for safety and reliability. However, these traditional approaches have limitations. They are often reactive based on past data, which doesn't fully help when pioneering new. Harsher environment or facial combined extreme events. There are still data gaps for truly long development. So digital twin is not just, so to overcome these limitations, we need a paradigm shift to enter the digital twin. So a digital twin is just not a 3D model as you see there. It's a living, dynamic, virtual counterpart of the physical FPV plant. So it's continuously updated with real-time data and powered by advanced simulation and AI, because today we don't have formulas to reflect the reality. So AI is really helping us on that. And its core capabilities, real-time data integration, sophisticated multi-physics modeling, and predictive analytics span the entire project life cycle. So here you can see how the behavior of the plants into the wave tank and the simulations. Thanks to that, we could correlate the plants versus the modeling, and that's only for waves, so for different types of waves, and that helps only building one block of the digital twin. Okay, so we need to do that for wind, we need to do that for buoyancy, for snow loads, for biofilling, and all the rest. For FPV, this means we can finally start to manage and reduce the unknown unknowns, in fact, moving from reactive fixes to proactive optimization and risk mitigations. The biggest impact of digital twins starts right at the design phase, as already said. We can perform incredibly detailed simulation of environmental loads, how specific waves, currents, and winds will affect our specific plant and at its specific locations. This allows us to virtually prototype and test countless mooring and structural designs, as you can see in the middle in black. So sorry, it's maybe a little too small, but you can see how the fact that the plant is like a tissue shape has an effect on the behavior of each of the mooring lines. And this, as a unique body, you don't have its behavior, and we struggled how this adapted plants could fit with the actual technology for mooring lines. So this allows us to virtually prototype all those conditions, and the result is optimized designs that aren't overly conservative, reducing material use and capex without compromising safety. We can also simulate material degradation. We have a cooperation with BAS ongoing for additives, and so that's the material needs also to be put into the digital twin, because it's a part, also the way it's gonna wear is a part of the resilience of the system. I couldn't keep myself, focusing too much on the digital twin without saying that we perform quite huge simulation with OrcaFlex. And also building the model and the response. So sorry, I'm going into physics more, but we needed to describe each of the components as its behavior. So we packed with Deep Math in Paris, so mathematicians and physicians to model one of them, and then to bring that to a full scale of 2,000 bodies. So that's a 1 megawatts in a 10% steepness wave, and so it was 3 meters there. And we performed that at each 30-degree direction with the scale plants. And we've seen that, what is the question is that what will be the traction force in the mooring lines in all the system, depending on the size of the plants. So that was a big question on our side, because how could we scale up without something to model what's gonna happen? And so we figured out how to do that. And I also wanted to show you the fact that, okay, this seems to be dynamic, but it's more or less, you get a stable wave. And here is just a 0.5 meter wave with also a steepness of 10%. But you'll see that the behavior of the floater is quite odd, and that you cannot even see the wave passing through. So Yeah, so that's a resonating behavior, and you should be very aware of that when designing. So that's why we need, so that's why processing the design, and that helps us improving afterwards to get more convenient behavior. So to add damping, so that's the purpose of our HydroLock system. So once operational, the digital twin becomes an intelligent co-pilot for OEM also. So out of design, now get into operational and maintenance. And through a network of sensors, we get unprecedented real-time visibility into the health of every critical components, from mooring lines to individual panels and inverters. This data feeds AI algorithm that enable predictive maintenance. We can forecast failure before they happen, shifting from costly reactive repairs to proactive scheduled intervention. And this drastically cuts down time and OPEX. We can also predict degradation rate for soiling and biofoiling, optimizing cleaning schedules to balance cost and yield, and make smarter decisions about long-term component replacements. Okay, so digital twin also play a vital role in environment stewardship, as we've seen. So we tried to simulate how our FPV plants might interact with the local aquatics ecosystem effects on the water quality, shading impacts, as has been said, on vegetation or change to the water flow. So this again relies to the fact that each of the plants today, like we would like to have it with measurements, but they're not so affordable. But this lack of measurements leads us to a status where we don't have enough data to show that and to integrate it. So we implemented some of the measurements into our plants, and these insights allows us to optimize the plant design and operation to minimize our ecological footprint from day one. Crucially, by integrating real-time environment sensor data, then the digital twin supports adaptive management. If actual impacts differ from predictions, we can model and evaluate corrective actions quickly. So now, what's the thing is, digital twin is also into improving LCO. Ultimately, digital twin offer a compelling economic case. We believe in that they reduce capex through optimized design and smoother commissioning. They significantly lower OPEX, primarily through predictive maintenance, but also by optimizing routine tasks and extending asset life. That leads to enhanced revenue through better yield and higher availability. And critically, the transparency and demonstrable risk mitigation provided by digital twins improve project bankability, making FPV investment more attractive and potentially lowering financial costs. So while full-scale operational DTs for FPV are emerging, we're already seeing compelling insights. The floating offshore wind sector, a closed cruising use DTs for structural health and fatigue predictions, lesson directly applicable to us, trying to applicate them. Pioneering FPV research like Heliorec have actively developing and using a DT concept for design and performance assessment. Broader application in renewable and industry confirmed the power of the digital twins to fuse physics-based model with real-world data. Yeah. So at Heliorec, we're convinced that digital twin are foundational to the future of FPV. Our vision is to develop a comprehensive FPV digital twin platform with specific modules targeting the core challenges: structural integrity, panel performance, OEM optimization, and environmental stewardship. We are baking this with significant R&D strategic partnerships, and by applying this technology in our own projects, learning by doing. Our goal is to deliver FPV projects that set new benchmark for performance, reliability, and cost effectiveness. So in conclusion, the FPV industry is on, I guess, an exciting trajectory, but one that requires us to embrace innovation and to overcome its unique challenges. Digital twins offer a transformative path forward, moving us from reactive problem solving to proactive predicting management across the entire project life cycle. By reducing risks and eliminating unknowns, DTs are instrumental in making FPV more reliable. This technology is key to unlocking the full global potential of floater solar and accelerating our journey toward a cleaner energy future. Okay, so at Heliorec, we built floating solar power plants for the sea and help industry company near the shoreline reduce the CO2 emissions. Without taking any valuable land, we developed certified and patented novel diamond-shaped floating system featuring unique hydrolock, shock absorption, and traction resistance mechanism that's significantly reduce structural loads on floaters. So this new products will be out at the end of the year, like September, and patent is ongoing. It is engineered to withstand wave up to 4 meters with a steepness up to 10%, making it suitable for normally approximately 70% of global coastlines. We're a revenue-generating company with an installed power of 300 kilowatts peak, and a 700 kilowatts plant is under construction right now. We make nearshore floating solar finally as affordable as rooftop solar, which was one of the goals of this year. At Heliorec, we believe collaboration is essential. So we invite industry partners, technology providers, and research institutions to join us in creating the future of digital twin-enabled FPV. Together, we believe that we can build a smarter, more resilient, and more sustainable FPV industry. And thank you very much for your attention. I'd be happy to answer.
Thank you, Geoffrey. I don't know if there are any questions from. Oh, there are several questions from the audience. Okay.
Very interesting presentation. Thank you. I was just wondering. This might be a stupid question, but with the digital twin, how do you know that it calculates the forces and the moments correctly? Do you have measurement sensors also on the installed, on the actual FPV installation, so that you can measure kind of all the Morgenheim forces, all the individual floater motions, or kind of how do you control that the digital twin is correct?
Yeah, I think you get the point. So the first, I think there are two main parts in your question. The first is we need to identify what is the measurable characteristics. So if it's the load, then let's go for load cells. If it's environmental, then let's go for turbidity or pH. So then it comes to the sensor. So there's no models without measurements. There's no AI without data. So yeah, I think the first is to identify on each of the plants of the location, which are, and it's not simple, in fact. I'm just presenting that as simple as it can be, as I could. But for each project, like there are some equilibrium to respect and then to measure. The thing is, as much as we will have tools to measure with the lower cost, so that brings us to the fact that we really need an industry on those kinds of sensors, in fact. And so with those sensors, we can have measurements and then comply that, although with formulas, as researchers are looking for, or with an AI to try to match that. But for sure, there's no model without measurements.
Yeah, thank you for your presentation. It's very interesting to see what's possible with the twins. Is it also possible to calculate whether fatigue effects will occur either on the floaters or the metal or on connectors?
Yes, so that is that is very interesting when going into plastics, because in fact metals has been into the industry and is quite good knowledge on that, and going into plastics with humidity, salinity, with temperature variations is quite hard to get some good knowledge onto that. And then getting into additives is another subject. So this is ongoing. I mean, we figured out that the formulation of the materials is one parameter. The concentration of additive is related to pigments also. I mean, the viability. So it's very hard to accurately understand how things are going to behave. Still, we can have how do you say, limits, borders. So we're trying to reduce that borders, okay, while having more data for the fatigue, for each of them, but for the fatigue, that's it. Then we go into laboratories. So when we have figured out what are the good concentration, good material, good concentration, all the rest of it. So a good formulation. Then we go to laboratories, and then we do. There were a slide with this cycle effect and showing how the wearing affects the mechanical stress. Yeah. Oh, okay.
I had a very similar question, but a little bit different actually. My query is that when you develop the 3D modeling, are you able to identify the stress that is coming on all the connecting points for the floaters? Are you able to identify and correlate further? Is it possible?
That was part of my job, yeah. So with the team, in fact, it's a very hard question to answer because for a typical study, you need to really have a good boundaries. And those boundaries in the floating PV on near shore are not so easy to get because this relies on the state of the sea. But the state of the sea, you have an impact on the way the wind will go across the waves, you know, and then it's hard to find models that can with a computer effort, you know, minimal computer effort, can bring in time, you know, a short time, can bring those results, like on the full 2000s floater scale. So that has been a really hard job, and we succeeded into that.
That's great. That's really great. Thank you.
Hi. Thank you for the presentation. A really complex and challenging matter you presented, and really nice to learn about this. I was wondering, maybe not on the mechanical part, but you mentioned fouling simulation, and I was wondering, my question evolved a little bit. You already answered in the first question, you need to measure and then implement that in your prediction system or whatever. And you mentioned we need like an industry on new sensors or developing this industry. Is there any guideline, or you are working on any kind of description just to move forward on this? Because I try to extrapolate the technical campaign to near-shore environments, let's say, from onshore PV to floating. But is there any movement or any work on this?
I think we are all, I mean, for the person who are developing, we have a whole a platform, you know, some of sensors. So we have struggled with a company in Grenoble, in France, to apply some sensors on the plants in Brest. And that was really good, you know, work together to understand which sensor would be the good one, and then we go into the fact that they're very energy consuming. What are you using? Do you need a battery on the plants? And all this, at the end, we came up with like things apart, you know. So then we would like to get, you know, one centralized thing, like looking more professional. So it's like we're more like in a garage state, you know, to try to fit the sensors with the others. And I think there is really something to do with the sensors being really compliant to the FPV. Like, okay, you get a manufacturer of that, and then you can buy it because I want to characterize sun, to characterize boy fooling, and then you just plug that in, you know, modular. So that we were looking for that.
So, Teofilo, thank you very, very much for your presentation and for the answer to the question. Thank you. So, moving forward, we are going to have Jocelyn Ellen Hessel, that is the head of Floating PV Research Group of IFE, and she's going to talk to us about highlights from the new IEA PVPS report on floating PV. The floor is yours. Thank you.
Good afternoon. I will present some highlights from this new report from IEA PVPS, and I'll get back to the abbreviation. Does it say anything to anyone? IEA PVPS? A couple, okay. But just first, a couple of words about my home institute. I'm from IFE in Norway. That's an independent research foundation working within the energy sector quite broadly, and working with PV since the late 1990s. I'm also heading the Floating PV Research Group, so this is my regular gang of people, and we work quite closely together with industries. I've also included some recent projects and industry partners. But today I will talk about a report that is not only written by me and my colleagues at IFE. It's a collaborative effort between 30 contributors from 12 different countries. And the title of that is Floating Photovoltaic Power Plants, a Review of Energy Yield, Reliability and Maintenance. It was just published now in April. And this is done through the International Energy Agency. They have a work program called the Photovoltaic Power Systems Program, and that's where the IEA PVPS come in. And this is what is called Task 13 in this program. It's about performance and reliability of floating PV, of PV in general, and for this particular report on floating PV. So the whole idea here is to gather experts from different institutes and try to present a consensus, try to present things that most people agree on. And all of these reports are freely available from the home site webpage of IEA PVPS. And I would think that some of you are familiar with some of these reports, like Trend in Photovoltaics Applications or Snapshots. They're quite widely used for numbers and freely available at the homepage. But for this report, it's all about floating PV. It's been said quite a bit on market today. This is not primarily a market report. There is some market updates in the introduction, but I will not say so much about it since it has been covered previously today. And the target audience is you, FPV industry, basically, but also policymakers, standardization authorities, and research institutions to pinpoint what gaps we have. You have seen this before. I will talk a little bit about terminology and categorization. It was mentioned in the panel debate. That is always nice to know what we're talking about. And generally, it's a good thing to agree on terminology, which is not really the case within floating PV today. Of course, this is perhaps the less interesting way of categorizing floating PV based on the mounting structure. This has been around for some years, so I guess that you have seen it. Solar Power Europe has suggested the inland versus marine categorization, where inland, again, is divided into static freshwater bodies, inner waters, and larger inner waters, while marine FPV is divided into nearshore FPV and offshore FPV. That would help a little bit. Not perfect, because as was also mentioned in the panel debate previously, we may even have to go down to the sea state codes. We may need to be very specific with respect to what waters we are deploying on to make sure that we understand each other in all contexts, and also that people outside of the community understand what we're talking about. At least in Norway, the politicians in Norway often seem to think about offshore FPV when we talk about just FPV, because in Norway, I guess we tend to think that everything is offshore. But of course, for FPV, everything is not offshore. Most of it is definitely inland. Most of it is inland in Asia yet. Hopefully that will change. But again, I won't go much into this. I don't think this has been mentioned. And this, just to have said that, this is numbers that has been collected by the end of 2022, so there may be changes here, but this is the most recent update I'm aware of. It was published this year. But if anyone has newer numbers, please let me know. But this is taken from Ceres database on floating PV. And I don't think there are big surprises here. This is a pie chart of float suppliers for floating PV. And in addition to many familiar names, you see, is there a pointer here too, perhaps? Yeah, oop. Here, a lot of, well, fairly big, you would perhaps say, but small companies with 1 to 4% market share, and also a big chunk of others, and a big chunk of unknowns, which adds up to more than 80 float suppliers in Ceres database. That's a lot of suppliers for a fairly small market. So I think it's still an early stage, and it's natural that there will be consolidations within the float suppliers. And another thing that I would like to mention with respect to this is that it tends to be a benefit to produce locally, since it's not so cost efficient to transport a whole lot of air, which could be good for the European market and the producers, well, most of the people here today probably. But so far, the majority of these also are Asian or Chinese, with the exception of Cielotard and Zimmermann, which makes it into the pie chart. Of course, there are many more, but this is just the biggest producers. I'd also like to highlight that the power density has increased from 82 watts per square meter back in 2013 to 123 watts per square meters in 22. That's the median. Of course, some of that is due to just more efficient modules, but it's also likely that some of it is due to more efficient FPV systems, and that there may be more to collect here, at least for some. A bit about energy yield, and for the next two topics, which is energy yield and reliability, I think I very much agree with the former speaker that we need more sensors and measurements, and perhaps a bit more old-fashioned when it comes to the analysis. So I think that it's also big need for us to understand the analysis. And currently, where we're at, it's very much a lack of data and very much a lack of knowledge on what stressors even are there for floating PV. So I would argue that we should start there and gain more understanding before we just feed it into AI. So from the report, the goal of this chapter in the report is to provide guidelines and quantitative recommendations to calculate accurate energy yield assessments. And this is because, of course, it's a key factor to determine project profitability. And there is a clear lack of these numbers that is needed into floating PV. But there are some literature, and that's what we've been trying to gather in the report, summarizing what is currently known and also be open about what is not known, and hope that other research institutes will follow up on that. Yeah. And there is also, we also discuss the modeling tools. We stick to PVSYST and PVLib in the report. But it's, as I will come back to, there will also be a new report in the new work program of the task. And if you have other tools that you think is more relevant and is more used than PVSYST and PVLib, let me know, and we might be able to include it. So we aim to, as I more or less said, identify and quantify essential parameters that is different for floating PV compared to ground-based PV. And also highlight several areas where there is currently just too little information. And what we want to achieve by this, it's impossible, of course, to do this for all technologies. There's, as I said, 80 float suppliers. It won't happen for all technologies. But it's possible to do it for the most used technologies and, over time, improve engineering judgment in general. So today I will talk a bit about temperature, wave-induced losses, and slightly touch on soiling losses. And I should also mention that this is mainly for inland, to some extent nearshore, but it's not for offshore floating PV. That's simply not mature enough to gather a significant amount of experimental data. How many are familiar with, how many of you think yourself that you are familiar with U values and know what U value you should put into an energy yield assessment? Is this familiar to you? No? A little bit? Well, I guess it's familiar to most people that the reason for the cooling fuss for FPV, because there has been a cooling fuss for FPV, we've been talking about cooling for FPV for many years, and it's of course because we are improving efficiency and we are potentially also reducing degradation. And then the next question, is FPV cooler than GPV? Nodding? Yeah. That tends to be what we hear about, and particularly many of the early studies were very clear on this and gave large cooling effects. Some of the more recent studies are more moderate, still perhaps a few percent, 2 to 4% gain, but definitely more moderate than they used to be. But I think it's pretty clear that improved thermal performance is at least not an inherent advantage of all FPV installation. It depends critically on the design and on local climate conditions, which is many.
So it's irradiance, ambient and sky temperature, circulation, which is both wind, wind speed, turbulence, humidity, mounting structure, and module materials. And for FPV systems where the module has water as their ambient, you also have to include water current and water temperature. But that is not for the typical FPV systems that are, after all, in the air. So why we have module temperature? Why then talk about U values when it's easier to understand the module temperature? Well, we're trying to differentiate between the impact of local climate conditions on one side and the impact of the technical installation itself on the other side. And that's why we keep talking about these U values. And of course, it's like with Windows, a high U value gives it says that it's a better heat exchange, and a low U value is a poorer heat exchange. But it turns out that it's difficult to really separate this technical installation with using just this one U value, because in this equation that you see to the left here, really there is more. This is where we try to separate the ambient temperature. We take the irradiance into account, everything just to try to separate this heat exchange ability of the technical installation. But it's not sufficient because wind and turbulence also greatly impact the heat transfer. And this is why, if you want to be more accurate, it's also wise to include a wind-specific term in the U value. And this is often not done for PV, also often not done for ground-based PV. But since we are seeing slightly improved cooling for floating PV, we're curious what that is, and including the wind term is kind of a first step to understanding why we see a slightly improved cooling. And here are some values found in literature for U values. So you see, that's for ground-based systems, it's around 29. That's the default single U value in PV-Syst. In red up there, and you also see corresponding U values if you include this wind term. And if you follow the list down, you see that generally they're slightly higher for floating PV. And this is what is there in the literature today. So this is where I would go if you are wondering what to put into PV-Syst, for instance. And it also is an explanation of what type of technology it is. Wind direction is because we included the wind speed. It turns out the wind direction is also important. Here is an illustration of the difference in U value based on just wind direction, whether it's coming from behind or from the front. And of course, then we have not taken humidity into account, and that's still an unknown. We don't know for sure how much effect humidity have on cooling of the floating PV panels. And there is also some module materials that we haven't, that's not in the equation, so to speak. And this is why it's still not uniquely defined for each technology what exactly the U value will be. But we have a pretty good idea for the main technologies, which will give better energy yield assessment, just to remind you why we're messing about this. And it's perhaps unfair to say, but even so, over the PV system, it will be huge variations in it's not homogeneous, so it will be big variations in temperature, which means that even if you have measured the temperature somewhere behind that module, it's not guaranteed that it's representative. So it is a bit of a difficult business to pinpoint exactly what the operating temperature of the system will be. Another thing that we, oops, sorry, can I go back? Another thing that's we have been talking quite a bit about in recent years is wave-induced losses, and what is expected for wave-induced losses for floating PV. This is quite complex, and that's also why it has been difficult to give one single answer. And of course, one single answer is not what you want either. You want it for different sea states. I have a figure, yeah. So this is the modeling of wave-induced losses. So this is why it's taken some time to come up with good numbers for wave-induced losses. Just as a starting point, you need a good hydrodynamic model. And that's just where you start. And then you also need a irradiance model, and you need a good electrical model, which is actually not entirely straightforward to know how the inverters react to the different positions of each single panel. Yeah, in DNV's recommended practice, the current recommendations is to use 1 out of 3 methods: wave tank measurements, numerical analysis, or engineering judgments. And I hear that it's very varying what the different simulation tools has as a default for wave-induced losses. But to facilitate this engineering judgment, what is important when you're going to assess what the wave-induced loss will be? The number of modules per float is obviously important. There won't be any mismatch if they're all aligned when they're connected to the same MPPT. And the extent to which the floats follow the wave movement will be important. If they're kind of a big structure and don't follow the waves, then little mismatch. The sea state, obviously important, and it's not just for specific wave heights, it's really how steep the wave is, and latitude and season, and also the electrical configuration, so the length of the string. How many modules do you have in a string? All of these parameters are important when you are going to judge the mismatch that is expected. So we calculated this for one nearshore location in Norway. This is not included in the report because it came too late for the report. But basically, so to your left are counts, and to your right is the mismatch. So the count says something about how often you experience this sea state, and to the right you see what wave loss you can expect for that sea state. This is pretty low, and this is for a nearshore location. And you see that it's not, I mean, you can't say one specific number, but it's somewhere between 0 point a little bit and 2 for the sea states that are most frequent. And this basically shows the same. It also varies with clear sky, and to the right you see how it varies over the year. And I've separated into irradiance losses and actual mismatch losses. But for all practical purposes, we can talk about wave-induced losses as one. So it's 1% for a nearshore position or location, which is far less than some of the PV modeling tools suggest as default. And I think that's partly the researchers' fault, because also when I show you all the sensitivity analysis, we tend to show the sensitivity analysis on cases where it actually makes a difference. So when we want to highlight that it changed with different properties, we do this at pretty high or steep waves, because that's when you see that it makes a difference. But then it's also, as you can see here, you also get the impression that there is high mismatch losses on these graphs. I think I will stop there because time is running out. And really this was some highlights from the report, but the rest is in the report, so you're welcome to look it up there, and of course to ask any questions if you have.
Thank you, Jocelyn.
Are there any questions?
Hi. One question regarding uncertainties. So for irradiation figures, we have a very good understanding of the uncertainties, and they are pretty low. Now for wind impact or even the wave impact, how would you look at the uncertainties for this, for their impact on the losses and the overall energy yield?
Yeah, good question. I think that so far, we've been pretty busy just trying to find an approximate number. And really, the uncertainty analysis hasn't been given much attention. There is one subchapter in the report on it, but basically what it says is that there are very few examples of full uncertainty analysis for the different parameters for floating PV, and that we need to start. Of course, we have something to build on from ground-based PV, and we need to do the job for floating PV.
More questions? There's another question over there. Please.
Sorry, thank you. But just losses, I don't really understand. What you were talking about losses, are you talking about the losses for the whole system, or are you just talking about the losses using the PVSys to determine only the DC losses?
This is, I can spend 1 hour talking about just one loss.
No,
So
I have been working with this for 23 years, so I understand exactly, but that's why I want to understand.
It's just one loss. So this is just the mismatch loss. So the one box in PVSys, for instance, where it's asked for mismatch, this is the additional loss because it's floating. So you would have the normal default 1 to 2% because of differences in the panel rating, and then this 1% would come in addition.
Okay.
Maybe
we need to talk later on. Yeah, thank you.
So if there is no more questions, I would like to ask one, Jocelyn, if it is possible. Something that is not clear, I would say, for me in all of the, let's say, simulations that is done, is that normally we have more wind, especially if we are speaking about inner waters. You have more windy when there are more clouds and normally in winter. So when the production is lower. So we are speaking about mismatch losses many times caused by waves that are produced in lakes, in inner lakes, let's say that way, where there is only waves when there is wind. Exactly. So the problem is many times is to understand if that mismatch losses are made in winter or if they are made in summer, because the difference is huge.
Excellent question. And here it's calculated with correlated irradiance and sea states, and wind. So this is an average mismatch based on actual data from one site, both irradiance and sea state data from the same time period.
Thank you very much. If there are no more questions, Jocelyn, thank you very much. So, and now we'll continue with Mark Montgomery, that is CEO of Sunsurf Solar AB. Sunsurf Solar, the innovation in floating and semi-floating systems for Nordic conditions. Mark, the floor is yours. Thank you.
Perfect. Yeah, thank you, Antonio, and the Lead Vent Group for having me. Like you said, I'm Mark Montgomery. I'm the CEO of Sunsurf. And Sunsurf is a Swedish company specialized on floating and semi-floating solar solutions. And like many of the other companies in this room, We are focused on providing solar in areas where traditional technology isn't applicable. Just to not go into deeply, but I'll tell you what semi-floating solar is in just a minute. First, let me give you a quick overview of our technology and what sets Sunsurf apart. We have developed our own floating and semi-floating solar systems. Our pontoons are specially engineered to handle both snow and ice loads in compliance with Nordic climate and standards. Our systems are capable of handling 2.5 kilonewtons per square meters, and our patented mooring system can handle continuous winds up to 26 meters per second, meeting national standards across Sweden. The system ensures long-term stability even in storm-prone environments. And some of our systems has actually survived freezing bottom up and has operated reliably at minus 18 degrees Celsius. So that's quite impressive. And regarding mooring systems, if we, or that's our tactic at least, if we encounter bigger projects with more complex mooring structure, we do as some of the companies in here as well, we actually give Lars and Seaflex a call and he'll sort out the rest. Let's talk about one of the biggest design challenges that we have, and also one of our greatest strengths. And this is ice and snow. Like I said before, our pontoons are designed in a special and reinforced V-shape. This helps to absorb and redirect pressure from the expanding ice, allowing the system to move safely when the water freezes. And for extra durability, we can actually fill our pontoons with steam-expanded EPS, a lightweight but strong core that keeps everything afloat, even under harsh conditions. Each Sunsurf power module, as we call them, is constructed with 3 sealed pontoons, 3 in each corner, following the principle of watertight compartments for maximum buoyancy and redundancy. On top, we mount a robust aluminum frame which supports a walkway. This makes it safe and easy to service every part of the installation, even in icy conditions. Each module holds 3 solar panels firmly secured and attached to the aluminum frame for optimized performance. And maybe the most important thing about our module, all components are made in the Nordic region, mainly from recycled materials. At Sunsurf, we try to combine sustainability with the performance. For those who doesn't know, Sweden enforces one of the most demanding environmental regulations for water installations in the EU. And our system is designed with this in mind. We use an open system that enhances solar performance by maximizing light reflection. This is achieved through an open and hollow structure with highly reflective aluminum frame. Our module allows the bifacial panels to capture much of the reflected light from the surrounding surfaces, especially from the aluminum, the water, snow, and ice. We also let the sunlight pass through the module, keeping the photosynthesis going in the water. The height of the module, 110 centimeters above the water level, lets wind through the system, keeping oxygen levels high and cooling the panels even more. And what has been the result of our design? Firstly, we have actually seen higher energy output than expected nominal values. Secondly, we have achieved a minimal ecological disturbance from our module structure. We have also proven track records from obtaining permits in Sweden, very harsh, like I said before. And this is for different types of locations, irrigation ponds, quarries, etc. And this demonstrates the system's strong environmental compatibility and regulatory compliance. And let's move on from water to land, actually, at least partially. In Sweden, at least, the solar market is shifting away from farmland towards low-impact alternatives, such as peatlands, wetlands, and other marginal lands with low natural values. Therefore, we at Sunsurf developed a solution, and we call it the peat module. And this enables more large-scale solar, but with lower impact. It offers a stable, piling-free solution with floating properties. It comes with buoyancy, with surface anchoring to ensure structural integrity on soft and saturated ground. And it's designed to handle extreme weather events with a 1% annual exceedance probability, handling storms, flooding, and snow loads expected only once per 100 years. So, what makes the peat module so effective? First, it's lightweight, so there's no need for ground compactation or heavy machinery. That means faster installations and minimal site disturbance. The structure has floating properties, like I just said, and it adapts naturally to seasonal various changes in the water levels. The module is built to resist corrosion in extreme environments, even where the pH is actually lower than 1. The modular units can be winched into place. You can actually use the water surface when it's more wet as an advantage as well, even in remote or hard-to-reach areas. It's practical, it's gentle on nature, and it's fast in deployment. And the electrical infrastructure is always routed above ground via the modules. This protects them and makes maintenance easier. Our mooring system is non-invasive and carefully planned to handle sensitive areas, helping to preserve biodiversity and also protect the water flows, a vital part of this installation. But the most important point I want to make is that we don't use forest or farmland. We target the marginal lands, places that otherwise would go unused. Oh, sorry. Back to our floating modules. Our systems are optimized for rapid deployment in areas with limited infrastructure. Our design ensures reliable winter access for operation and maintenance, even under challenging Nordic conditions. With a modular and scalable approach, installations can range from a compact 100 kVp to multi-megawatt solar farms. We also get a very low O&M, and this is due to the modular maintenance access on every platform. And just to mention, like we did not do last year, we have actually delivered turnkey small scale projects for just 700 euros per kilowatt. Per kilowatt, not watt, just to not confuse that. And let me share a very quick case study. In Western Sweden, we installed a 122 kilowatt floating solar plant, and the results were actually better than expected. The energy production was between 7 and 11% higher than projected nominal values. And the ice and snow resilience was fully confirmed with a lot of ice in the last winter. This proves that when designed right, floating solar can deliver high performance without harming local ecosystems. it's a great example of balancing the thing we're targeting, solar energy with minimal impact. And also a short case study of the peat module and how it performs in practice. Our first field test took place in a challenging peatland site with uneven terrain, very low pH, and limited accessibility. Our aim was to evaluate both installation logistics and systems performance in this very demanding environment. And the outcome was highly positive. Our system proved stable, effective, and easy to install without piling. A key advantage was the ability to deploy the modules on a sensitive area like peatland with minimal environmental disturbance. And the exciting thing is that we're now able to produce solar energy on land that would otherwise be left unused. Former extraction areas, degraded wetlands, and low-value terrain. And we're doing it while keeping peatlands functioning as a critical carbon sink. So, where are we going from here? We are actually entering a new phase of growth. We have multiple large-scale floating solar projects in pipeline across Sweden. And our goal is clear. We want to reach between 100 and 200 megawatts installed capacity within the next 5 years. And to achieve this, the real game changer for us is the peat module. And to put like the potential in perspective, 15% of Sweden's or 6.4 million hectares is actually peatland in Sweden. So it's a lot of area compared to artificial water bodies, for example. We have so far offered our peat module system on a large number of projects in the Nordic countries. It's scalable, it's sustainable, and it's ready for deployment. And to make this vision a reality, we know we can't do it alone. Sunsurf is looking to open up a new market in Europe, and one that focuses on land where piling just isn't a good option, and where we have floating properties as well. So we say it. We actively seek partners, both developers, EPCs, researchers, perfect place to come as well, and other floating solar companies that want to cooperate. This was everything for me today. So 8 minutes left, I think, Antonio.
He's my friend, okay? He's taking care of me because he don't want me to be late, so nobody is going to be angry with me, okay? So thank you, Mark. Thank you very much. I don't know if there is any question from the audience. Yeah, there are questions from the audience.
Hi, okay, it's quite interesting looking at the semi-floating solar in the peatland. Would like to know the price or the cost compared to the ground-mounted and floating solar and the semi-floater, which is on the pit. So what is the price range? Is it huge difference or?
Yeah, it's around the same, maybe 10% more.
To floating.
Yeah, no, compared to traditional ground-mounted PV.
So only 10% more than the ground.
Yeah.
Right. Good to hear that.
Yeah.
Yeah, and on my side, I have a question regarding, you mentioned uneven terrain for the semi-floating also. I would like to know if you have any restriction or any requirements regarding the flatness, the slope, the type of topography or bathymetry you could cope with your system.
Yeah, because we have the modular structure as well. It's 4 panels on each, so we can actually work with the terrain and do, make the rows between the panels bigger. And yeah, it depends on the site really, but we can work because it's a modular approach there as well.
Okay.
Yeah, I had a question about the ice.
Yeah, sorry.
You mentioned that this construction is withstanding ice.
Yep.
In the Netherlands, we don't have every winter ice, unfortunately. But the problem when we have ice is, especially on larger lakes, is the breaking up the ice. I don't know the English word for it, but then the ice moves. So
Yeah.
it breaks in flows, and that has a huge power.
Yeah.
And we on larger lakes, when we want to scale up FPV, we need protection of this moving ice. And
Yeah.
what's your experience about that?
In Sweden, we have actively excluded natural lakes just because of this, actually, and also the bigger hydroelectric plants, for example. The ice breaking loose and comes down, it actually makes it, the O&M would probably be higher than the capex. So, so we have actively not chosen those areas to begin with, at least. But yeah, so that's my short answer.
I don't know if there is any other. I don't know if there is any other question from the audience. If not, I will have one, Mark, if you don't mind. One of the questions, it was already, I asked already, taking that in consideration, that normally you have lots of waves that are induced by the wind, okay? And with the wind speeds that you mentioned, I would say that if there is a fetch that is important, you are going to have waves about 1.2, 1.5 meters high, I would say. What is the resistance of your system to that kind of waves? So it moves with the waves slowly. Do you have a special mooring system for that? How does it work?
Yeah, our mooring system is adapted to like small scale ponds, and like I said, if we encounter bigger systems, we actually have a cooperation with Seaflex. So in the ponds and irrigation ponds or the quarries that we have projects in, there won't be any waves to talk about, really. So that's why we have developed our own and patented our own system for that specific environment.
Okay, thank you very much. If there are no more questions, thank you very much. So, even being a little bit earlier, which is very good, let's say that way, what I would propose is this. We have a coffee break now that is going to start within 5 minutes. I propose to start a little bit earlier and then to maybe come a little bit earlier also too, because we could finish some minutes earlier, I don't know. That would be good. Thank you very much. Okay, so my proposal is that we go to our break. We can do our networking outside, and we'll be back 4:20, if that's okay with you. That will be 10 minutes earlier than scheduled. Okay. Thank you very much. It was a nice try from my side, okay? I'll do my best. I've done my best. We sleep in the hotel. So here we are again. Now we are going to continue with Nikolai Anderson, that he's the Vice President Commercial for Fred Olsen, and he's showing us a case study of floating solar in dynamic environments. The floor is yours. Thank you very much.
Good. Well, thank you very much for letting me open the last session of today. I think everyone's happy with that. Just gonna go with the pointer. So for today, I just want to open up with some thoughts we have around floating solar, of course, with a focus also on Europe. And then we will dive into our technology, BRIZO, and more importantly, some of our latest developments and activities we have at our test site in Norway. But before doing that, I just want to quickly introduce who we are at Fred Olsen 1848. So we are part of a large group of companies that is family owned, and we are basically born into the maritime environment. We were established now more than 175 years ago, and we basically have been starting our business in shipping. So we were building vessels, and from that we went into oil and gas. But for the last 30 years, we have pretty much been focused on converting ourselves into a fully renewable player. So that means within renewables today, we are very active, especially in wind, both as developer. We are having companies that are leading suppliers, especially in the offshore and onshore wind sector, and also a lot of consultancies. And how we fit into the group is that we take care of all technology and innovation. And that means that we are looking at some of the future trends within renewables, and also based on our maritime heritage, how can we then solve these challenges? And that means today we are in two fields, one being floating wind, and then the other, which is the topic of today, which is floating solar. So going a little bit into floating solar, and something which, at least to me, is often quite a big surprise, is why does Europe continue to want to take this big jump, going from you have your calm inland waterways out to the harsh offshore? Because it's two completely different worlds. As we see it, at least, there is kind of a middle step in this FPV journey that's missing. Because you have your inland water bodies, which is mature. I know it's still a new industry, but it is really mature. You see, I think it was 80 technologies previously. That means it's being a commodity. It also comes with very low risk and also very low complexity. But the problem you have with inland floating solar is that you can't build at scale. And I think a general rule of thumb for solar is that you need to build scale. And then we can, of course, try to go out to harsh offshore, where we have endless opportunities of scale. But to be quite frank, it comes at an extremely high cost. It comes with very high complexity and high risk. And I don't think there's anyone that today can say that floating offshore has a viable business case. It might come sometime in the future. 5-7 years down the line, it's not going to happen. So basically, actually one thing which, at least for us, is also important to state is that if you have a solar panel and you put it on a pond, or you put it at harsh offshore, it still produces the same amount of energy. So we question a lot, why do you want to spend all the additional risks and costs to put it offshore? So that's why we see there is actually a missed opportunity, or maybe a key opportunity for the industry to take. And this is basically to start considering deploying floating solar in more nearshore areas, or it can also be larger lakes. Because there you have your moderate waves. They are still high, and we shouldn't neglect wave. I think that's also important. But it will give you the areas that can give you scale, and then hopefully also drive down the cost of energy. And I think what you will also see with our technology is that that's something we keep quite a big an eye out, is we need to keep the business case first in everything we do. So all the products and material you're using, it needs to be affordable. So basically, the way we see it is, as we need to learn how to walk before we try how to run. So just showing some examples to some of the potential that we can potentially grasp. And we looked at some wave data from the coastlines down with Italy and Greece. And I think visually it's quite evident the additional potential you're actually gaining by going from 1 to a 2 meter HS configuration. And then just to comment again to the 2 meter HS, we shouldn't neglect the fact that 2 meter HS, it's almost 4 meter in peak wave. That's quite large. So we need to make sure we have the right technologies and the right competencies to deploy solar in these areas. And one thing which is also, when we start looking at inland markets where you have very large lakes, you will also be exposed to large waves in these areas, because there is a clear correlation between once you have a fetch and then the wind speed. So just because it's inland, it doesn't mean you can always deploy inland technologies. So that's why with our technology BRIZO, we are trying to target the market from around these 1 meter HS up to 3.5, 4 meter significant wave heights. And that's pretty much putting ourselves on the upper limit of what the conventional systems can do today. Good. So basically what this unlocks for us at least, and how we see it, and I will introduce BRIZO, is that you get the scale, but you still can build affordably. So just quickly on our technology before we move into our developments. Maybe I should use that screen. So BRIZO, our system, it has a lot of similarities to the inland components, or at least the components we use have a lot of similarities to what you know from your inland floating PV modules. But what differentiates us quite a lot from the rest is that we have basically designed our system as one large anchor mooring system. So what you see is that we have our panels in a rope mesh, and they are all individually anchored. And as you can maybe see on the side layout to the right, we have an outer perimeter of plastic PE pipes, which sort of acts as an integrated wave breaker. So all the components that we are using in our system is very cost-effectively and also affordable components. So our floats, it's blow molded, it's made out of plastic. The locks we have to hold the ropes is injection molded, it's plastic again. The PE pipes is plastic. Our floating walkway in the center is also made of blow molded parts. And then we're using something called a danline ropes for all our rope mesh, which is also something that's typically used within the aquaculture industry. And one of the key features is, as you can see on the picture, is that each of the floaters are individually anchored into the rope mesh. So this actually means that once you start to receive your large waves, all the forces from the waves are transferred through the ropes and nothing goes into the panel itself. And another thing which is also important with this is that you're not having any forces transferred from one panel to another. So we are not experiencing that, for example, if you have one string going out, it's not affecting the panel next to it. And then also, of course, when you're building a PV system, you need to make sure you have a solid strategy for O&M. So what we have done basically with our system, we have removed any, you can call them O&M walkways, or at least walkways for people to walk on the system to do the cleaning, to do repairs, or do component exchange. We have basically allowed for access through the sea in the entire system. And then our system comes with this catamaran, as it's illustrated, and I will also show you a video how it's working today of our prototype in Norway. And it basically comes with two functionalities. The one being, as you see on the front, it has some brushes that acts kind of like a car washer. And then on the back, you have this large working platform that when you have to replace a panel, you have to replace some cables or anything, you can position people on the catamaran and they can actually go out to the site and do the necessary replacements. So moving a little bit to some updates for our test site, which we have in Norway. So first of all, our test site, it's fairly small. It's only 124 kV. We installed it almost 2 years ago now. It's positioned in a seawater site in Risør, which is just south of Oslo. And one of the major things we did over the past 6-8 months has been to actually replace all our floater modules in the system. Because basically what we are using our floating laboratory to is to, every time we come with an optimized product or we come with a new, let's say, a new feature or whatever, we always make sure we test it in Norway first. So everything we do, we build it and then we test it in Norway, although at a smaller scale. And I think this is also quite a good illustration for in terms of space. Of course, we would like to have a lot of space available for assembly because that makes it more efficient and also more cost effective. But in this case, we don't have any land available basically to build our solar project. So instead, we've just made up our own little working platform and we can actually work at very narrow spaces. And the installation itself was done using around about a 50 by 50 meter parking lot. Then the other thing which has been quite important for us, and I want to show a video in a second, that's around the O&M catamaran. So as said before, we want to use the catamaran for all our operations and maintenance. So of course we have had to build a prototype which is also now in operation. And when we did the floater replacements, we actually used our catamaran for all the installation works because we wanted to make sure it has all the capabilities to maneuver within the system as it's required doing a component replacement campaign, but also, of course, testing the cleaning capabilities of the catamaran. And what you will see in the video, they are manually steered, but we are working quite a lot these days to make it autonomous. And we are fully confident that for the next commercial project, we will be able to supply an autonomous catamaran. So I just want to play the video and hopefully all works. Perfect. Then we're moving on to some more technical developments which has been taking place at Fred Olsen. So one comment which we have also received since we launched the system has been that our energy density is of course low compared to our Celetaire or traditional inland systems. But I think it's also important for us to emphasize we are not to compete with the Celetaire. We are targeting waves that are a little bit higher. Again, it's not offshore. We can't go offshore, but it's still a little bit higher. And we need a little bit of space both for the catamaran, of course, to move within the system, but it also comes with the benefit that you have this penetrating sunlight. I think there's been a lot of presentations that blocking off sunlight entirely is a challenge for FPV. So that's somehow overcome to some degree, at least with our system. And we also need a little bit of space because we have all the floaters individually anchored in order to withstand large waves and large wind forces, especially when we are deployed in typhoon or hurricane environments. But of course, we have taken up the challenge. So we have optimized our site layouts quite a lot in order to improve the density and also to make cost outs on the system. So for example, on these floating walkways where we have the string inverters, we are reducing these in our building blocks. So we have these building blocks of around 3 megawatt each, and we pretty much has minimum halved the need for walkways. And then the other part is that we have been for quite some time been looking at trying to get out in 3 meter HS, so nearly 6 meter peak waves. We also have to say the market doesn't seem to be fully ready for that for the moment. We believe it comes, and that's of course why we work on this. But this has made us to do take in kind of a floater portfolio where we now have a second version, which is for more benign areas, but it's still above the 1 meter H mark. So that's of course a bit more cost effective. And then we also did some optimizations, both on the layout for the walkway, but we also did a new improved design, and it was upgraded for manufacturability. And then, as said, let me just play the video. We are coming from the maritime environment, and at least how you do, I know this is not oil and gas, it's not offshore wind, but how you do things when you're building a vessel, or if you're building an oil and gas rig, or if you are trying to design a floating foundation for wind, you will always need to test it at a tank test. So this is now our second tank test, where in February we did a 1 to 10 scale of BRIZO, so it was a 25-meter long module, where we actually tested wave height from 1 to 3.5, so that's again up to around 7 meters of peak. What the video is shown on the screen is 2 meter HS, but it is really important to test your system, like basically test the extremes of the system in a controlled environment. Because we of course need to understand what is the max capabilities. And also a second part, which is very important also, which is a big cost driver, that's the anchoring and mooring. So this allows us basically to have so much data now that we can make sure when we design anchoring and mooring, it is within all the safety margins that is required. And secondly also, it allows us to then see how can we then optimize, which will always be project specific or based on a specific site layout. So what that gave us basically is actually a lot of positive answers, and of course we should say that, but it gives us the comfortability now that we have no concerns around our system integrity. That's 100%. One concern we did have is that what will happen to our system when we have breaking waves within the system. And basically also there the system proved well. And then of course we have this pre-tensioned rope mesh, so it's important for us of course that our ropes are not breaking, and again it seemed it came out positive. So all in all we were really pleased, and right now all of this data is in with DNV, and then as part of our final validation together with them. So I think that would be my presentation for today.
Thank you very much, Nikolai. I don't know if there are questions from lots of. Okay, you cannot leave, Nikolai. You have to stay. Sorry.
Thank you.
Yeah, thanks for the great presentation. Could you elaborate a bit more on the cable management of the electrical cables, for example, between the modules and so on?
Yeah. So now we didn't have a picture, but we are at our site. We are testing. We are testing three solutions at our site, and two seems to be proving. So one of them is like a, which is probably not going to be, but like a spiral cable, like your old telephone wire, which extends. And then the other is where we have basically a protected tube, I can't remember what it's called, but a rounding between, so protects the cable. And then there is of course allowed for slack, so it can maneuver properly. And then the third one, I can't remember, but it's not the one we're going to go with. So I think we've come quite far there, so we've tested that for over a year now. But this is one of the things, of course, that we also would like to see the full effect on when you're deploying 6 megawatts and letting it operate for X amount of years.
Because they have already been connected in that Norway site that you showed.
It's grid connect, yeah.
Yeah, thank you for the presentation. Just one question. What is the distance between a floater to another one?
I don't know, but maybe like this.
But how you deal with the string? You mentioned you are using string inverters. For string inverters, you have multiple of panels connected to each other, and in general, in the market, the panel is well known between 20 to 30 centimeter, the panel cable.
Mm-hmm.
Are you doing? You're making extra connection cable?
Yeah, so we have a cable going, extra cable going through floater to floater.
So you're extending the cable between the panels?
Yes. Yes.
What about the losses? What happening with the losses there and?
The what, sorry?
The losses, how it affect once you're extending and put more MC4 cables between?
I have to draw the non-engineer card there.
So. And what about the grounding? How you deal with the grounding between the panels?
Yes, we have grounding, but Martinus can maybe I have my colleague Martinus in the back. He's a bit better equipped for answering these questions.
Hello. One more question. I noticed that your panel is installed at a
flat, yeah, more or less flat.
So all flat. Is it possible to have a tilted?
So we have a 3 to 5 degree tilt, but it's also important that because a lot of the areas we look at that is in, for example, typhoon areas or hurricane environments, if you have panels standing like this, you're going to have your system fly off. So it's also in order to withstand larger wind forces, basically. And once you go, for example, near shore, you will encounter winds. As I was at a site in south of Europe 2 weeks ago, and their design criteria is around about 40 meters, which is nothing compared to a typhoon, but it's still a lot in Europe. So.
So is it possible 5 degree?
Yes, at the moment the standard is 3, but we can probably do tweaks and twists, yeah.
Okay, thank you for sharing the wonderful presentation. Just one question I have that when the O&M operation and maintenance being carried out, how do you access the modules, like to check for anything, something got wrong with the connections or cables? Then
you sail.
Yeah. How do you access it actually? Each of the PV module.
Yeah, so you have a working platform where you can basically just.
Okay.
So where you stand and then you can look straight down to it, like you're standing on a.
Okay.
On a road.
Through the platform, you have the access of all the modules, isn't that? Like all the PV modules?
Yes, everything. We can access the entire system. Yeah.
Very nice. Good.
So, if there are no more questions from the audience, Nikolai, thank you very, very much for the presentation. Thank you. So I believe that now is Lars Brandt, that is the CEO of Seaflex, that is going to do his presentation. He's talking about safe floating solar with optimal cost. So Lars, the floor is yours. Thank you very much.
Thank you. So hello everyone. So nice being here. Thanks for Leadvent to letting me do this presentation. I did prepare it for a different audience. Well, floating solar, obviously, but a little bit more people that were new to this. I think most of you have seen this, right? So maybe I'll cut through. Who has not seen this presentation here? Okay, there's a few. I'll do this for you guys. The other ones, I'm kicking in an open door, so we'll see, and we'll change through those. I didn't put much effort into telling what Seaflex is, but we are only doing mooring system. But an important thing when we do these projects, and this was a Gallup that we did earlier years, to focus about different focus areas when you do moorings. One obvious one that we always come back to is, of course, keep it to the lowest possible cost chasing. Of course it is. Anyone here thinks that's not important? Hands up. Okay, so we're on the same page. They're great. Reliability, we need to do it in a good way. I mean, we can't cut costs down so that risk is, getting higher. Everyone agrees? See, this is fantastic. This is going really good. What's most considered being most important when I talk to a lot of people, and I guess everybody would agree with me, one of the most important things are the moorings, which I think is great. That's the only thing we work with. I'm going to cut through these quickly. What is a mooring system? And why is it important? Traditional cable, chains, catenary system, this is called, or you can add some clump weights to it. There are different ways of doing it. This is how we do it. We have a taut system, elastic system that's always taut. We don't touch the bottom. We've been doing this for more than 40 years, not with floating solar, but that's latest 15 years only. But this is a technology that we have delivered many years into thousands of installations. Environmental aspects has been focused all the time, that we're not touching the bottom. So extremely important for, especially in some areas where you have eelgrass and sensitive bottoms, you cannot use a traditional system. So this is how it looks. I also have a VR system with me. I'm not going to show it here, but I'll bring it out. So if someone wants to look at this, stand there on the bottom and see a floating solar platform moving up and down and look at Seaflex, how it works. We'll do that later, okay? I asked ChatGPT, don't we love ChatGPT? I asked, what's the single most important thing with floating solar projects? I love these answers. The single most important thing, anchor and mooring. Yoo-hoo. Hey, we're there. I'm going to come back with a follow-up when ChatGPT extends on this answer. That's even more absurd or good for me. So, this is what happens. Super important. If you don't have these moorings, what happens? Slowly but surely. It's floating away, right? So if you don't do this correctly, it's going to, something has happened in this world, modern world, that these things has been done in the wrong way. It fell over there. So we need to, hold strongly on these valuable assets. I mean, there's a huge investments in platforms and structures and panels and everything. Imagine if it could be this easy. But it isn't. And the thing with our system is you don't see it. You need to look under the water. Who does that? I mean, there's only a few people that does that. And when you do that on a traditional system, you often find something like this. These chains, sometimes they will corrode to a level where they are deteriorating to nothingness and going back to Mother Nature. So therefore, its limits is, it's costly. And then it's scoring the bottom in some cases, leaving it to, in some areas, in some countries, you can't use these kind of systems. Look, this is what ChatGPT told me. One of the best mooring systems. Great, isn't it? I love ChatGPT. I didn't train it, though. Someone else did. So top historical challenges, and those are the things I'm going to go down to a little bit more in detail. The uneven distribution of forces, that is a top priority. If you don't handle the forces in an even way, you are in trouble. Water level variation, some people say it's a challenge, when it's 10 meter plus. That's where we start loving it. We have a project now, 55 meter variation. Large wind speeds, I'm going to show you a video, one of the few, because when it's blowing a lot, you can't do videos because you blow away. And possible waves, of course, and how to handle that. Our solution is that we automatically balances the unevenness of Mother Nature. That's something that we do during installation time, so we can control evening handling of the forces. Okay? I'm going to show you a little animation of this to make it easier to understand. And a little bit of this stuff. Maybe I can say that. Oh, how do you back? There. We have done, and also others, third-party companies have checked, that if you use the load balancing system of Seaflex, you can cut away 70% of the peak loads. 70%. I'm also going to show that in the free decay simulation that you're going to look at. So harmonized distribution of loads, what is that? What is the cascading effect? Someone else talked about this already, so maybe we can cut through this. But this is a very common problem in the industry of cascading or domino effects when you have system that does not share loads in a good way. This is a top view of a floating solar CAD system, flat, nice bottom. The only thing, it doesn't look like this in Mother Nature, does it? There's unevenness in the height of the bottom and where you put these anchors. They are not put, all the same places. It might look a little bit like this if you break down one part of it. And if you look really closely, there's a couple of these lines are shorter than the others, right? Yeah, that's not good, because if you have a force acting on the system you calculate the forces to be handled by all of the mooring lines, right? That's what it's done for. But unfortunately, there's only a few of them that are shorter than the others. Therefore, they take up the predominant loads or creates unevenness in the floating structure. What happens if the loads are on those only and not on all of them? They're overloaded. When something is overloaded, it breaks, okay? It's going away. You see where we're going at this, right? It's not going to be better now when 2 or 3 lines are gone. Same thing, overloaded, domino, cascading, it's goner. Now it looks at the, where it was free floating there. And this is what has happened in some installations, and we cannot go back there. It must not ever be done like that. So when we have these anchors in different heights or depths and different places, there is an unevenness which we can calibrate when we do during the installation. Because depending on where these anchors are, we pre-tension all the C-flicks the same way. So therefore, we can control the uneven spreading of, and on top of that, we dampen the loads, which is, even better. Dampens, I mean, what is this? What's he talking about? It's a little bit tricky. Everybody has dampers in the car. Everyone uses it. It's a technologically very known fact that we have to dampen loads. And I think we should do that with floating solar as well, dampen out the loads. This is a critical line, red line, right? This is the capacity of the connection point of some plastic attachment or floating structure, the eyelets, the ears. And this example, it's 12.5 kilonewtons. If you pass the line, it will break. That's the maximum load you can load on those eyelets. If you do, it will look something like this. We didn't do this. It's without C-flex. But it's a good example of what can happen if you overload the ears and attachments of these plastic structures. So we need to keep under the line, right? This is a free decade simulation of a storm in a Hong Kong, very well known in the industry project that was severely damaged to the level it was free floating. Full domino effect, everything broke. Chains and everything. And we did a free decay surge simulation of this. And you see the peak loads well above the red line, right? So obviously this is what happened. So we did the same storm, the same, not the forces, but the same environmental input as this simulation. We changed the mooring system in the simulation to C-flex, and look where we are on the forces, under the red line. Totally coming away from the peak loads, more than 70%. Handling of water level variation, another big thing that we focus a lot on. I mean, we've done many of these installations with 20, 30, 40 meters variation. Like I said, now we're working with one with 55-meter variation in India. And we love that. So I'm just going to say that and then run through that. You know what the level variation is, especially in hydroelectric dams. This is, of course, a vital thing when you do those. This is, if you have a high water situation, you don't have these angles. I know that. I mean, there's you know, not the widescreen enough, but principle is there. But you have a catenary system to the left, and it's all fine and dandy, right, at high water. What happens in low water when you have a catenary system like that? It all curls up on the bottom, more or less, the catenary system. The taut mooring, you know, pulls back and is still taut at low water. If there is a force now from my direction, you know, it moves everything. And this is when you have almost a free floating situation, and you hit the end stops, and that's where the peak loads are. Well, beside that, it's moving all over the place. This is a typhoon, in Korea a couple of years ago. I can't pronounce, Sulik. It was well over 45 meters per second. Like I said, you're not out shooting videos at this point, but this typhoon, it actually ran over 3 of the installation we at that point had in Korea. At that point, we have more now, but at that point, that's when they ran over the 3 of them, and they were all fine. So this is what you can look at in the VR simulation, or you put on the goggles and you can actually go see this on your own, and you can walk around underneath the platform, and you can simulate the water level variation. You can see how Seaflex handles it, and you can look at all the nice fishes. Lowest possible cost. What's the most important thing to not incur more cost? You know, don't under-design it. That's the worst thing I can do. I mean, you know you have to pay not once or twice or perhaps more times or too much. So that's super important, and we need to do these things in the correct way. We need to have the design process in a way that these things cannot break away like they've been doing in the past in different situations. And remember, price is not the cost. Again, most of you have been hearing me saying this now for years, but it's so nice that this is picked up on and understanding the difference of cost and pricing. Levelized cost of energy, I'm not going through this, but use levelized cost of the LCOE. Don't look at the price per watt peak. I mean, that's totally irrelevant, because we have projects, and I can prove that mathematically. If you have double the price for a mooring system and something happens, the total cost is still lower than if it blows away, of course. A good example, I'm going to run through this away because most of you have seen this before, but this is an example of 2 inverters. Look, one is 10 cents a watt peak, the other is 13. Question is here, which is more costly than the other? Most people would say the inverter B, but most of you have seen this before, so you know that it's inverter A that costs more. And the reason behind that, and I can click it forward, I'm clicking. Any help clicker that can help me? Is it stuck or? No way. I still have 6 minutes. I know, I have the watch there. Yeah, but it will show you the reason, of course, that the inverter A costs more, despite that the price is less, is that the life expectancy of that one is 8 years and the other is 13 years. So the LCOE is actually lower for inverter B. So you have to look at life expectancy, life, you know. That's a super important thing. And we're still locked. Can you stop the clock as well at the same time, or?
This is not basketball.
Yeah, I had some other things that maybe we'll show. Another thing that everything that we do is we design and develop our system so that it will have very, very long life. I mean, we have customers that are still using the original C-Flex that was invented, installed 45 years ago, still using the same C-Flex, not in floating solar again, but in the marine environment. And that is the first version. Now our C-Flex is on a completely different development scale. It's the 5th version. So the quality that we're doing with the C-Flex itself is important to show, but I can't do that. This is another thing, checking and controlling and operating something. This is a small little thing that we have developed and are selling to the floating solar market. Everybody knows how costly it is to put out load cells and measure forces, right? This isn't the same thing. You can't log and you can have testing. Well, it doesn't compare to load cells. But this bolt has an integrated load cell in it, a battery that's worth for 5 years of running this. And it has it communicates with without wires. So what we do with this, we install it, and it monitors the structure or the structural capacity of the mooring system. It logs every 10 minutes, so it's not a load cell with 1,000 hertz, but it does give you every hour or so a very good check that your mooring system is okay. You can integrate it with the SCADA system. It has an API to it. You install these and you have communication that sends up to the cloud. Super important. Maybe a load cell costs, what, 3,000 euros perhaps? These cost, this costs around, 3,000 euros, and these cost 300. And it's working for 6 years to give you the forces. Okay, I can't do my presentation, yeah. No, there's still 2.5 minutes. Another thing that we're pushing hard is in the electrical field, where we are seeing the high cost of transformers, and meaning that most people are staying away from floating transformers because it costs too much. So then you have a long distance of transferring low voltage AC or DC, at least AC. And you have transformers on land. We are using a floating transformer that's floating inside the water, and that we're trying to push for. And really big news. We can cut the cost of that part with 50%. Last, 2 minutes left, is, and I had some slides on this, but the economy of scale, I mentioned that during the panel. We've seen this occurring now when we go to larger utility scale projects. It's staggering the economy of scale on the mooring system. We're talking 80% in one case that we have studied a lot. So remember that. Don't extrapolate the small little test sites, because the mooring cost compared to those is not relevant when you look at utility scale projects. Now the clock says I'm going, yeah. Okay. Thank you.
Thank you, Lars.
Just a minute for questions.
So sometimes the technology doesn't help a lot, so and it spoils more than it helps. But anyway, thank you very much for the presentation and for the speech and so on. Any questions from the audience? Yeah, at least we have one.
Yes, I have 2 questions. Thanks for the presentation first. The first question is related to your system. So it's elastic, so you may face creeping on your system. So creeping means loss of elasticity during the lifetime. Can you say a word regarding this?
Yeah, we don't. Yeah, we call it residual elongation. it's connected to the standard material properties of rubber. This is not a homogeneous rubber, though. It's not homogeneous, so it's not really rubber per se. It's also compressing the rubber inside. But there is a residual elongation due to the Mullins effect, which is called. That could be 20 to 25%, but that's absorbed by the pretension that we have in the system. That's one of the major reasons that we have a pretension that's much larger than we really need it to be, to absorb that residual elongation. You had two questions.
Thanks. Yeah, the second one is you said that you have hundreds or thousands of projects of experience. I'm wondering if you have any rate to share with us on the rate of not of failure, but at least of inspection and replacement of your system?
Yeah, I mean, that's the other presentation. Now I'm over time, but we can talk about that separate. But we haven't had any failures of that level, other than, you know, people running over it and putting anchors through it and fish lines and stuff. We have now, I guess, more than 500 megawatts installed in 50 plus installations. Oldest one is 15 years, floating solar. So there's many references and tests. All right.
Thanks.
Can I ask some questions also?
Well, that's up to you.
Or not? No, I'll move forward. You are showing the small thing that is over there regarding to measurement of the I would say the integrity or the forces or whatsoever. Can you explain a little bit more on what is possible to get in terms of data, how it can be installed, etc., for us to have an idea? Because I believe it's a very important subject, because as you mentioned, free floating is not an option, so it's important.
Well, it gives you the standard sample time is 10 minutes, and of course it's a small battery. You understand that. So, and it's there for 5 years. You can change the sample time to, you know, an hour perhaps, which is plenty. If you want to have a sound check on something that it's still there, you know, it's still doing its job. So if you change it to an hour, the battery time gets up to 7-8 years. So that's the only thing it gives you. It gives you that tells you how much force is now in the bolt, and it sends that to the controller, that sends it to the cloud.
Okay, good. There's another question over there, sorry.
Here, I have a microphone here.
All right, just wondering, the mooring underneath is movable, stretchable, but when it comes to, let's say, it attracts the muscles accumulate along the mooring, will it impact on that movement of this one?
No, well, of course, the predominant growth is, you know, up towards the surface, and the Seaflix is often below that. But the small little creatures, they don't really like to sit on the rubber, because you can imagine, you know, here's a cozy place to put down and start sleeping, and then this thing is elongating, you know. So they don't like to sit on it. So, but we often stay below where these is the most critical growth, and so that's often on the ropes that's, you know, closest to the surface. All right.
So, thank you very much, Lars, for the presentation. So, and now we'll continue with Daniel Reinhardt, that is going to do a presentation about the case study of marine floating PV in Maldives. Daniel is head of sales and project development of SwimSol. Hello, the floor is yours.
Thank you very much. So, good afternoon, evening, everybody. I think most of you already saw me this morning, but yeah, very happy to present to you our most recent projects in the Maldives. So, a brief background about SwimSol. SwimSol is a solar integrator for tropical islands. We're mainly active in the Maldives, in the Seychelles, We've done some projects in Southeast Asia and are looking also at different islands around Africa at the moment. The reason we focus on tropical islands is quite simple. Number one, they have very high energy generation costs because most of them use diesel generators to produce power. So we're speaking of a levelized cost of electricity of above 20 cents per kilowatt hour. Number two, you have abundant sunshine, very high solar irradiation. So actually a very good setting for solar. One challenge that we just faced very quickly is that space on islands is often very limited. And for this reason, we developed a floating solar system for marine conditions already more than 15 years ago. We have a strong R&D team at SwimSol, which is constantly advancing this technology, working on mooring and anchoring designs and other topics. And in addition to that, since we're kind of a one-stop shop for our customers, we also have a lot of expertise in the integration of PV systems with batteries into diesel grids. That's also a very important part of our work. I would like to briefly speak about the kind of setting that we're mainly in. So our main market is the Maldives, where we've installed more than 40 megawatt of solar. A lot of this on roofs and also ground-mounted systems, but now increasing share also on our floating solar platforms. So here you basically see the geography of the Maldives. You have basically atoll reefs, which shelter the inside islands from the very high oceanic waves. However, the atolls are often quite big, so you can have wind-induced waves inside the atolls of easily 2 to 3 meters. The water depth varies from very shallow lagoons with less than 1 meter to the inside atoll areas where you sometimes have a water depth of more than 50 meters. Our main client base is island hotel resorts, actually. And basically there are more than 200 of these resort islands in the Maldives now, all using their own generators, and we're basically helping them to get away from this and to reduce their energy cost. Now, when we look at a site, there's different things we have to take into consideration. So before we do any kind of floating solar installation, we always conduct wave measurements to get a good understanding of the wave situation that we have on site. We conduct current measurements, and of course we gather bathymetric and seabed information. And then finally, of course, there are some other factors to consider when you select a floating solar site, which is, for example, the visual impact when you're working with hotels. Unless the guests are maybe solar energy enthusiasts, they don't want to sit, of course, in front of a gigantic solar system when you're in their holiday. So that's one thing you need to take into consideration, and of course also some other factors such as boat traffic. To speak a little bit about our technology, so our system is what you call a space frame structure. Mostly made of aluminium. The floating bodies are the black things, here are the silver things that you see, which are basically made of polystyrene and usually encapsulated with HDPE. In some cases, we can also encapsulate it with aluminium, because in some places there are requirements for this. Our main design consideration has actually always been to elevate the solar panels above the sea surface to ensure that seawater never reaches the solar panels and the DC connectors. For us, this has always been a crucial consideration. And then basically we have two different platform variants on the market right now. It's the SolarC 1000 system, which is designed for short for maximum waves with short wave periods of maximum of 1 meter. And our SolarC 2000 system which was initially designed for maximum wave heights of 2 meters at very short wave periods. At one of the projects, which I'll present to you shortly, we actually then measured slightly higher waves of up to 2.5 meters. So we actually slightly reinforced and adjusted the platform, and it's now basically suitable for up to 2.5 meter wave heights at short wave periods. And when I say this, 1 meter, 2 meter, what I mean is that at this wave heights, we can guarantee that the waves and the seawater will never reach the solar panels and cause wave impact damage or biofouling or something like that. Okay, the first project I would like to present to you is an 880 kilowatt peak floating solar project that we completed beginning of last year. It's at a very small island resort in Maldives. Here we've conducted wave measurements over several of months in different seasons and measured maximum waves of around 0.7 meters. So over longer periods, probably maximum wave heights might be slightly higher. One thing that we noticed is that currents were actually quite strong because it's fairly close to the atoll reef. If I actually go back just 2 slides, it's actually exactly the hotel that you see over there, and you can see on the right, basically the atoll reef. Good. So for a mooring system, we're using a 4-point catenary mooring system with screw anchors, Dyneema ropes, chains, and some damping elements, pre-tension buoys. And basically, the platforms have 4 anchors each, but anchors are also shared amongst multiple platforms to make this most efficient. In terms of power evacuation, so below the solar panels, we have junction boxes where we combine the strings to 6-core armored subsea cables, which then are laid on the seabed to the shore in this case. So the inverters are on land, which in our opinion also makes sense to put the inverters on land. Generally, this is a very shallow area, shallow lagoon, which of course generally makes the installation easier, but it also comes with some complexities. So one thing that we've seen here a lot is sand movement. Depending on the season, sometimes the beaches at these islands are completely gone. And if the water is very shallow, of course, there's always a risk that also the installation area becomes more shallow, which could result in beaching, which comes with certain risks, specifically when you have rougher conditions. So this is something that we're monitoring very closely. The reason we have this shape is that actually some of the areas here were a little bit too shallow, and that's why we kind of left them out. So that's why we don't have like an even squared shape, basically. One other complexity that you generally have in this kind of setting is the whole logistics. You can see that this is a very small island. There's no harbor, there's nothing. So just bringing all the equipment there, installing this there is actually quite challenging. Second project that I want to present to you is kind of our lighthouse project. It's the one that you already saw in the first slides. So this is a 2.4 megawatt floating solar system at a very high-end resort in Maldives. Here, even though the area looks quite shallow, we measured quite strong waves here. We have measurements of up to 2.5 meter wave heights at short wave periods, which is actually quite challenging. Another very challenging element of this project was that we are very far away actually from the island. We're 2 kilometers away. It was not really possible to do this on a low voltage side. That's why we installed a substation platform. Mr. Brandt, if you have a floating platform that maybe we can discuss later. This one we built on piles. And then basically the transformers and the substation was lifted into the building when the roof was not there, and then we put the roof on top. That was also quite an endeavor, to be honest. And then we also laid the 11 kV subsea cable basically from the system all the way to the island. So this was quite a challenging project. However, I'm happy to say that it was successfully commissioned, that it's working really well so far, and that so far it has withstood all the rough storms that we have seen in the past year. So it's been operating since roughly 1 year now, roughly. Another point is that the installation site was actually 2.5 kilometers away. So here I have a few other photos of this project to show you. The way we do the installation is that we have a rail system that we install on the beach. There the platform is assembled and then pushed into the sea. Then we have a boat which tows the platform from the installation site basically to the place where it's moored and anchored. What you can see on the other side is the cabling. So here we have armored DC cables laid in PVC pipes for additional protection, running from the platforms basically to the substation platform, where we have the inverters inside, where we have the substation, and from there we then basically run the medium voltage cable all the way to the island. Good. Just to give you a little outlook, what's next for us. So we have 4 additional projects contracted where our team is working on, which will be implemented in the next 12 months, hopefully even a bit earlier. So to date, we have 5 megawatt peak installed over the last 10 years or so, and now we're going to add another 5 megawatt peak in less than a year. And our goal is to add at least 10 megawatt of marine floating solar every year in the next couple of years, possibly more. We actually have also contracted our first project in Seychelles, a small demonstration project with around 400 kilowatt peak. So we're kind of entering a new market with our technology, and we also see some nice potential there. Generally on the technical side, of course, our team is constantly advancing. Our platform design is constantly working on the mooring and anchoring, which indeed is actually the most challenging part of it, I have to say. And especially when you have very rough conditions, we still do regular checkups to see if everything is okay. And yeah, any advancement in the mooring and anchoring designs will I think, greatly also increase the feasibility of installing these systems also in other regions. Generally, we have some other product lines also available. We already, since a few years, we have a prototype which is designed for up to 4-meter high waves, which was also successfully tested. We didn't really advance it because in our main markets, the Maldives, we don't really need it because waves don't get really that high in this area. But generally, if there would be a project where we also see that the commercial feasibility is given, we could also basically bring this product on the market and then use it for some projects. We also have a product which is designed for very shallow areas. So one thing I didn't mention earlier is that you sometimes have lagoon areas which are extremely shallow, less than 1 meter. And installing in these areas is a little bit problematic because at low tides you have the risk that the platform during wave conditions basically hits the seabed. And we try to avoid such areas. However, there's actually a lot of good installation site exactly like potential to install. There's a lot of good potential to install in such sites actually around many islands. So we're working on a slightly different technology for this kind of setting. Yeah, that's more or less it. We are, of course, also trying to, we have installed a couple of megawatts, single megawatt scale projects now. We will install several more in the next year or so. We are also looking into some larger projects in the scale of 5 to 10 megawatt. Can't really say when this will happen, but once we have completed that, I'll be very happy to come back and present that to you as well. Thank you very much.
Thank you very much, Daniel. I don't know if there are any questions in the room. Yes, we have.
Yeah, thank you for a good presentation. If we can just take back the last picture, if it's possible. We didn't hear anything about the operational maintenance. What's happening if you need to replace a panel? And how do you clean the panels?
Yeah, so basically you can reach the platforms with a boat. You can generally go into the platforms. We have a special fixture which you can put in and then you can just walk below. So you can of course only do that during calm conditions. When there are rough conditions, we don't really recommend that. Then you can go into the structure basically and access all the panels from below. If you go there with the boat, you can basically also, if you want to clean the panels from the boat. That's generally possible. To be honest, we don't clean very frequently in Maldives. There's not a lot of dust or anything. The main soiling that you have is salt spray, but that is actually mostly also washed away when it rains, and it rains really frequently in Maldives because it's a tropical area. So we don't really clean frequently.
No, but doing replacement of one panel, you need to do.
Sorry?
If you want to do a replacement of one panel.
Yeah, you can do that. That's not a problem.
But you need to open.
No, you can do that quite easily. You can go there. You just during calm conditions, you go below. You can screw it off. You can take it off and just replace it. It's possible. We've done that before.
Mm-hmm.
You can also, what you generally also can do, we try to avoid that, but you can detach individual platforms, pull them out with the boat, take them to the shore. If you would need to do some bigger maintenance, you could do that, but we've hardly ever done that. Usually during calm sea conditions, you can do everything on site.
Yeah, and you showed like you were transferring the low voltage cables. It was many cables there. This one, yes.
This one here, yes.
What was the reason that you have many cables instead of one?
These basically each cable, just to go back, this is the system. We have 64 floating platforms.
Yeah.
Each platform has one 6-core armored subsea DC cable running to the offshore platform. So basically these cables here are basically all coming from like this platform array, going directly over here to the substation platform, and from there we then have one medium voltage cable going to the island.
Yeah, thank you.
Sure.
Yeah, I also had a short question about your last slide. I was just wondering, why is there a gap in the middle of each
Of the platform? Yeah, actually, the gap was initially planned for maintenance, but in our newest platform design, we don't have this anymore. It's not really needed. Basically, there's a ladder, so you can go into the platform, and there's a ladder with which you can come up. But we only tested this in this version, and we're not pursuing this anymore because it's not really necessary. Yeah. The other platforms don't have it. Yeah.
Thank you. Are you expecting more dust in the Seychelles?
More dust in the Seychelles. That's a good question.
I'm
not
expecting more dust in Seychelles.
Probably, yes, probably. I'm not sure yet. We'll see.
Okay, no more questions? Okay, no more questions. Thank you very much, Daniel.
Thank you.
So, what I was going to suggest is the following. We wanted to do a group photo with everybody, so I was going to propose for us to join the stage and to make a photo over here or over there, I don't know. It's up to you. So over here. Okay, so the idea is that if we could come all over here and to do a group photo, that was item number 1. And item number 2 is that with Joaquin we are trying to make a more interactive intervention after our photo. Okay, so the idea is to cover some aspects of financial strategies of the floating solar and floating solar development. So I don't know if everybody is after that interested to participate in the interactive section or not. So feel free to, because I believe that Joaquin will not bother with that, because it was talked already. So the idea is, let's make the photo, and who wants to participate will participate. Who doesn't want to participate can do a break, and we'll have the reception after that, okay? So, shall we join to have the photo? Thank you very much.
Good? Yeah, absolutely.
Okay. Some in the back, some in the front.
Big people in the back. Can this hold everyone? Yeah, big question. Not tested yet. No jumps, please.
Someone could come over here.
Our chairman is not biting.
Who knows? Who knows?
Everyone can see me. If you want to blink now, we will do the 3 photos. Okay. 1, 2, 3. One more here. One more here. And enjoy the last session and the evening. Thank you.
Thank you very much. Thank you, everybody.
They can use the module.
If everything's okay with your computer and so on, it's okay.
Good. Hello.
Number one is working?
Is the microphone is working, yeah. All right, so after a long day, interactive session, yeah, that's a bit of a contradiction in itself, yeah, I guess, yeah. So the good news is presentations are over. Well, interactive sessions about financial strategies and business models. So that's what I do for a living as an advisor, yeah. So as Antonio already pointed out, yeah, I leave you the opportunity now, well, obviously to leave and take a break, yeah, or stay on, yeah, and we will, well, develop that together, yeah. So I'm not gonna be presenting, yeah. I have a few slides, yeah, I prepared, yeah, based on discussions I had over the past day, yeah, yesterday already, yeah, during the site visit yesterday evening, and I guess, yeah, we can take it from there, yeah. Well, again, yeah, I am not taking this in any way bad. If you're leaving now, yeah, last chance, yeah, to leave and take a rest, yeah. Good. Well, I mean, talking about financial strategy and business models, yeah, obviously, yeah, that's a very, well, I guess, difficult topic, especially to cover in 25 minutes, yeah. So just to give you an idea, yeah, typically a financial strategy or a business model, to develop that, yeah, that's a strategy project, and it takes, well, depending on what is already available, yeah, it can take from 2 weeks, yeah, to 2 months, yeah, sometimes even longer if you go through iterations, yeah. So why does it matter? Yeah, obviously we had a lot of technical discussions. I also seriously enjoyed the site visit yesterday. As I'm an engineer myself, yeah, I always like to connect, yeah, with the nuts and bolts. Yeah, finance and business models, yeah, can get, well, very complex, yeah, very quickly, and it changes all the time, yeah. So you need to be flexible and adapt, yeah. Especially, I guess, in an application or in a use case, yeah, like floating. So, well, obviously, session goals, yeah, we have, I guess, already identified all the barriers, yeah. So I don't want to spend a lot of time on that. What I would like to focus on is surface best practices. Yeah, we've got a room full of experts. Yeah, and doing this on a daily basis. Long track record. Yeah, people who've been in this business, yeah, for a long time. And then just basically give you some guidance, yeah, and discussions. Yeah, so I'm going to be asking questions, yeah, or a lot of questions, yeah, and I rely obviously on your input for that, yeah. So just to kick that off, yeah, a bit of an overview about the stakeholders. Yeah, so when you talk business models, it's always important that you will consider the various stakeholders and where you would like to position yourself. Yeah. So it's the obvious. Yeah, there shouldn't be any surprises. Yeah, here on that slide. Yeah, you got the developers. Yeah, the IPPs. And maybe you could just indicate, well, who is actually active in that space? Yeah, who of you is acting as a developer or an IPP? Okay, yeah. So we got a fair share of that. Yeah, who is well, I guess active in the technology provider side of things. Yeah, I guess quite a lot. Yeah, or yeah, yeah. Okay, good. Yeah. So just to give you an overview about that. Yeah. So the typical way, yeah, you would start that, but we have already extensively discussed it. Yeah, you would talk about what are the barriers, yeah, what are the challenges, yeah, for a business model, and what are the challenges, yeah, for financial strategy. Yeah. So, well, I try to list them. It's obviously everything, and I'm talking now from an investor's point of view. What investors do not like. Yeah, investors do not like risk. Yeah, they like bankability. They like security. They like clear regulatory frameworks, yeah, and they like hard contracts, yeah, where everything is clear and no uncertainties. Yeah. Also, well, typically, even though investors typically have money, yeah, that's the nature of the business or the activity. Well, high capex, yeah, obviously is something different. Yeah. So I would say investors are typically risk averse. Yeah. Or anyone in the room who's made a different experience or can share a different point of view? I guess, yeah. So, well, anything to add, yeah, to that, yeah? Any other challenges, yeah, I've missed, yeah. That's a very good point. Yeah. Actually, obviously, it's a little bit of both. Yeah, depending on which side of the table, yeah, you are. Yeah. What would you say? Is it high capex or is it high LCOE?
Well, I'm just a poor researcher, but I would say high LCOE.
Well, obviously, it also depends. Yeah, with what you compare. Yeah. If you compare with a ground mount solar system, 300-400 megawatt, obviously LCOE well is different, and also the capex the capex is different, yeah. Yeah, I think you're right. There's a risk also to that. Yeah, we are now talking negative electricity prices. Yeah, especially on the wholesale side of things. Yeah. So again, obviously, that's a risk. Yeah. And well, with a business model or with a financial strategy, obviously, you're trying to mitigate. Yeah, you're trying to gain additional security, or you try to somehow fix that. Yeah. And you're right, here in Europe, electricity prices are very, very different, from country to country, yeah. Hmm? And we have less security, obviously, of a payback. Yeah, that's in a floating system. Yeah, it's the same whether you talk a hybrid system or whether you talk a pure play solar system. Yeah, yes, absolutely. Yeah. Well, I'm just trying to raise the awareness, for the kind of things, which get considered, by financial people. Yeah. I mean, the business model for solar used to be very simple. Yeah, it was a feed-in tariff, which was guaranteed in many cases by the government, for 15 or 20 years. Yeah. Now, obviously, that came with also some challenges. Yeah. But in the end, well, we are now living in a different world. Yeah. So that's an important point. Yeah. Anything else? Yeah. You would see on the challenges side, yeah.
So I think in terms of the due diligence to make project bankable, we know that our banks are looking at what is the track record question is, how long has this technology actually proven itself? So I think 15 to 20 years would be looking for it. The second would be, how can they offload the risk on operational risk? For instance, let's say on the anchors and mooring, on a guarantee. Who's going to provide a guarantee for that over the life of the loan? Right? So you kind of have to structure that solution around somebody who can provide a credible 20-year guarantee. So I'm just wondering to what extent this is a problem here. I know in our country there'll be a lot of questions about track record and de-risking the operations with guarantees and warranties around the various components.
Maybe I can comment on the guarantee there. I mean, I concur, obviously, as you understand, but we give 20 years warranty, economically backed up warranty on the mooring system for its, itself, its function, and it's going to survive at least 20 years.
So that's on the equipment, on the equipment side, yeah.
Yeah, but that's exactly, I think, just to add on this one, the fully wrapped, you need to get these things back to back. I think it's very important that you give indeed a 20-year guarantee on the mooring system. But the same goes for the modules, goes for the substructure, goes for the cabling. And that everything has to be integrated into a bankable EPC contract. So it means you're also looking at bankable EPCs. The contract itself has to be bankable, the O&M party in place, the transfer of warranties, for example. It's everything that these things come to play, because in the end, the investor will not directly deal with C-Flex. That will be the EPC. And that whole chain has to be there. And that's when you get to bankability. That's the only way to do this. So everything starts, and what you see now today, and I'm quite, let's say, skeptic to this one, is that you see a lot of investors trying to reduce cost. They're just going to buy the modules themselves, the inverter somewhere else, and then find some money to assemble everything together. It's not going to work. It's a huge, huge risk, and in the end, you hardly save anything. So low cost, what was it before? You're paying double at the end of the 20 years lifetime. It's overlooked how much value engineering, procurement, construction, integration, contract management can bring into this one. So this is, when you talk to bankability, it's a very big framework, but even insurances, for example, insurance, reinsurance, what do you do with module bankability today? It's a bloodbath out there. So if you choose the lowest cost modules today, you may be stuck in 2 years from now. You're screwed.
So something, yeah, which might appear, yeah, very cheap, yeah, to start with, yeah, might turn out, yeah, very expensive, yeah, in the end, if you have to replace. And well, I would agree. It's about the general contractor, yeah. Somebody at the end of the day has to take the risk, yeah. And that is, well, obviously equipment manufacturing is at the beginning of the chain, yeah. Engineering, construction, and then the operations and maintenance as well, yeah, in order to keep the system alive or, well, operational, yeah, for 20 years or for even longer. Yeah. And very quickly, yeah, when you talk in solar, when you talk about financial strategies, you talk insurance, yeah, you've made that point as well, yeah. So, well, it's not only about the equipment or to insure the equipment, yeah, with a warranty, but to get a reinsurance, yeah, actually, yeah, companies like Munich Re and others are providing that. And then, well, I agree, you made that point, yeah, you need to wrap that up, yeah, in an entire structure. Very good. Any additional comments, yeah, points?
I think one important aspect is as well maintenance reserve accounts, especially when guarantees are not fully available for the lifetime, the expected lifetime of the project. Or as we have seen in the normal PV market years back, where we had long-term service agreements for the central inverters. And then after 10, 15 years, the company was just not producing anymore. Or, so you had long-term service contracts, but no counterpart anymore. So you can overcome this situation with, let's say, not having guarantees over the full lifetime of the project with adequately sized maintenance reserve accounts.
Sorry, but I don't fully agree on this one. A maintenance reserve account is a financial hedge in order to get funds available when something goes wrong. When you talk about central inverters, for example, and again, I'm not trying to steer in one direction or the other, but in the end, it's about competence. Maintaining a central inverter is a hell of a job to do for an engineer. So when you look at those systems that we saw today mainly, most of them were based on string inverters. Now, I'm just going to be a bit too short out here in this one, but basically anybody can be trained to replace a string inverter in 1 or 2 days. Making maintenance on a central inverter, it can take you weeks, years to master that. So again, we're talking about risk management, and what we may not forget on this one is that, God damn it, but solar is becoming a commodity. I'm in solar since the time that we were still paying 3.5 euros per watt peak. Today it's 8 cents. That's the shift that we made the last 20 years. So the way how we deal with these things is completely different, but I still see contracts popping up in the market where exactly the same things were written in there as what it was 20 years ago. And MRAs is a security for the bank. It's not a security for the investor. Don't make that mistake. It's only for your bankability.
Yeah, just making the point for this, let's say, approach where we have difficulties with the guarantees for the products if they are not there, because we all would have, let's say, want to have this fully wrap up EPC approach and everything backed up with guarantees, but sometimes it's just not there.
Yeah, but that's the full package that I was talking about before. That's your back-to-back guarantee. As an EPC, you're going to have your warranties from your module manufacturer, from your mooring system. You bring that all together, but you make sure in the end, again, this is a legal process, that the warranty is being transferable to your investor, to the owner of the system. Because also that is often forgotten in this one, and then the EPC disappears, for example. So it's all about risk management. That's the only thing that counts. And you really need to make good choices on this one. What is durable? What does it require? How easily can I replace? Because technically skilled people, they're hard to find nowadays. I think we all know that quite well here.
Like what he said here, so we agree, me and you. I have been in the solar business 23 years. I hate string inverter. I'm consultant. I'm mainly for the first design or the engineering design coming out from us consultant here. And we put this first step like in a floating solar to just advise and put together the requirement document where we have putting our requirement so we can make a fingerprint on the floating solar. You have right, it's not only about maintenance, it's about also how much energy you lose once you have central inverter. Instead of you have string inverter, if you have central inverter, you have 2-3 megawatt connected to each other. You want to make a maintenance in one string, which is it's about maybe 800 volt, 1500 volt. You switch down the whole unit for 2 megawatt just to make a maintenance for in 100 kilowatt peak. So this is not only lost of high expense of maintenance, it's also loss of energy where you are looking and connecting that. This is one of the things that we always trying to advise as a consultant, like don't use string inverter, even for the ground mounted. So just to comment on what you said.
Well, I would challenge that, yeah.
Don't use central inverter.
Yeah.
Sorry.
If you're agreeing.
No, I agree with you.
Yeah, I I would like to challenge that actually. I mean, talking about obviously, well, what I would like to raise as a point is technology choice, or design choice, can have a severe impact on the business model and on the financial strategy. I think this is to just round it up.
Okay. On my side, in Malaysia, we normally develop the project under EPCC, but nowadays we move towards where we split the contracts. We purchase the equipment, major equipment by ourselves. A simple reason, because one of the reason is the warranty. So from day one, we choose the right equipment and then have that enough warranties for the plant until the concession period. That works well on our side somehow. Rather, we don't go with the full EPC turnkey project anymore. So we purchase the major equipment by ourselves to ensure the quality, but only limitations when it comes to bankability or financing, where you have to prove yourself that it works so that the bank's able to finance your project. In order to do that, at least you have to already done few projects with that concept. That is the issue. That is a tricky part. If you don't do that project, you won't be able to finance the project. And for you to start to do that project, you need a finance. So there is a chicken and egg there. But somehow, luckily, we managed to complete few projects with that concept. And nowadays, it's quite easy to get finance based on that, with the reasons of we are pushing on the quality rather than giving to the APC. They always push based on the costs. So once they lock the price, they will go with the lowest equipment price, which might not be the most high efficient equipment. So that's my personal opinion.
So you're saying it's about the track record, track record in terms of the technology you deploy, whether that's on the inverter side or also on the system side, and well, also what kind of references, you can provide.
Exactly, but that's the problem. For you to have that track record, you must start with a project with that similar concept. Getting project finance with that concept also is not easy. So somehow we managed to went through that with a lot of guarantees given by the parent company. And after that, it became very smooth. So on the financing part, it became very smooth because we already have that track record, implementing not full turnkey, but a splitting contract. It's actually cost effective, if you ask me. So we eliminate the margin that considered by the EPC contractor when purchasing all the equipment. It is. We did that assessment, and we managed to get a savings of 15%.
I don't agree with you. Sorry. All right. We are a human. He can mention one point that me and you will walk there. You can do it in a way that maybe fit you. I will do it in my way, which fit me. Both of us will reach there, but maybe you will be more tired than me. You get the point? You choosing different. Once you choose, this is what's like I was talking, because working with this one, like 20, 23 years, you have been with so many in your life, and you have seen so many mistakes in the design. Not now we're talking now floating, but talking about the solar itself. Once you're combining different component where exactly they don't match. And the end of the day, you're losing either more losses, more losing energy. You do something that it will not match. But when you leave, like you're ordering a car, just you order one piece from Volvo and one piece from Volkswagen and the other piece from I don't know what. So and you try to put them together. They may work, but they will not last. We can talk until tomorrow about this topic, but
I think there will be ample time here also at the reception to continue that discussion. Just for the sake of time, we've got a few minutes left. Maybe, well, we have already started doing that. So that's where I would like typically to focus on, basically on what works and what doesn't. So we have already had different views of people. From a developer point of view, I've given you some insights from the investors side of things. So again, at the end, it all comes together, and it's about the collaboration and the different stakeholders working together to find a model. And that has an impact on the business model in each and every case, and also on the financial strategy, and can make a difference, whether you can get financing at all, or whether you have to pay more or whether you have to pay less. That's the I guess, quintessence. It's about the collaboration and finding a working model for each and every specific case, and then build it up from there. And while talking about equipment manufacturing or equipment, and then technical due diligence, we have people from DNV, for example, also doing technical due diligence. Well, obviously investors, as they are risk averse, they like to make sure. So it's about assessing the risk, mitigating the risk, and that goes as a red line throughout the entire strategy setting, and then also financing and business models, etc. So with that, I was trying to capture some of the discussions I had during today and also yesterday to come to a close. What are the emerging FPF business models? And again, I deliberately left it open. So one thing, obviously, I saw and we talked a lot about is co-location with hydro or any hybrid type of systems. Well, we can, depending on the time, or we can continue discussions afterwards, discuss further about the pros and cons. Also, I had a couple of discussions. Obviously, it's also who is engaging with whom. So SPV with public co-investors. I guess that is also at least an option, or trying to address some of the uncertainties we put out in terms of legal uncertainties, regulatory issues, and how to overcome them. And well, floor is open to you. Anything else, which we should put up there? What other kind of business model, or working business model, do you have in mind, from your particular perspective?
Well, smaller project, 1-2 megawatt or something, behind the meter of industries. That helps building the confidence in the technology, and that's like what Andres said in the morning. That can be a step up to scaling up if needed, if uncertainties need to be taken away for governments, for example, regulators.
Well, that would be an example like the site visit we did yesterday with this drinking water company. As far as I understood, the offtake is all by the company itself. There is no feed in, no PPA with anyone else. Okay,
In that sense as well, we have seen now a lot of let's say water basins around agricultural, so greenhouses, for example. For tomatoes and all these kind of things, you need a lot of water on this one. And one of the things that I think we may not underestimate is the value of water. That is, for this kind of farmers, it's liquid gold. And there are more and more restrictions in certain areas within Europe where pumping up groundwater is more and more limited. So we've now experienced in the recent period of drought. Okay, the last few days now it's been raining, but it has not rained in the last 2-3 months. So based on this one, we will see this more and more happening in the future. That's almost a given. So that means that protecting water bodies that we have and protecting the whole food chain on this one, this is where also floating PV can play a role. It's a different model because it's usually indeed 200 kilowatt, 1 megawatt in that ballpark range. Very odd shapes and sizes sometimes, so not every system will be suitable for this one. But especially in Netherlands here and in Belgium, a lot of those have been rolled out already. And not because basically those guys don't even want the electricity. Because in most cases they have CHPs in place. They try to get rid of the electricity of the PV, but what they want is to limit the evaporation of the water. That is where their business model lies. That is where their value lies. That's the reason why they're doing this one. So it's a complete different way of thinking on these ones.
So that, that would be a vertical market, basically, very interesting, So, well, I mean, maybe to wrap it up, well, there's equal creativity to be put into the business model, than it is, in the technology itself, and I guess, well, only by the collaboration, of the different stakeholders, ways and means, can be found, to make it, well, to build up on the momentum, even further, and to grow and to make it to something bigger. Good, I guess. Well, I think we covered a lot. You've been very courageous. To stay on. Thank you very much. For that and to participate and engage. I like that a lot. And well, happy to discuss further over the reception or tomorrow whenever you have questions. Thank you very much.
Thank you, Joaquin. Excellent. Thank you. No, you can leave it here. Okay, so I believe it's my time now to close the first day, let's say that way. It's not easy to do a resume of what we have been discussing and doing during the day long, okay? We spoke about market, we spoke about money, we spoke about investments, we spoke about environment, we spoke about pros and cons about the floating PV. I believe tomorrow is going to be another day to discuss things, but I believe that there are a few takeaways that we should think about and that I'm going to challenge you to think about for tomorrow. First of all, the environmental aspect. I believe that everybody agrees that there is a lake of knowledge about data and about what we can do and what we can do and where we can do things. What do I mean by that? It's that it doesn't work like a one-size-fits-all. It means that each project has their own, let's say, things that we can do there and what we can do there and why we can do the things over there. That is the first point. Not only in terms of environment, but also in terms of investment, and also in terms of CapEx, and also in terms of OpEx. And I believe that those are the, let's say, the main points that we should take from today and that we should think about tomorrow, because it's not one size fits all. We have lots of challenges, but I believe that we are on the good way and on good track, okay? So, thank you very much for the first day. See you tomorrow. Thank you very much.
Last word from me. On behalf of Leadvent Group, I would like to thank all the speakers for their commitment and interesting presentation, and also to all the participants for coming here today and joining the discussions on this conference. We look forward to receiving your feedback on the event through the evaluation forms, and if there would be anything else that we as organizer could do, please do not hesitate to contact us. We will do our best to help you out. Thank you so much, Antonio, and enjoy the cocktail and your evening in Amsterdam. Thank you.